Give a second. All right. Welcome everybody. We are going to do Grasple Lecture 8 until however far we get. Yeah, you know the usual. If you see this video, you've probably seen some of my other videos, so you know the topic. So let's get started. Let's not forget to start timing this time. So we're going to start with Lecture 8, Statistical Models. Let's see. There's some. What do we get?
This one is like so complicated, and like it literally just says median is the value in the middle, quartiles are the values in the middle, between the start of the median, the end of the median, respectively, and the pth quantile is it's like the 0.5th quantile is the 50th percentile. That's like what this is saying.
Yeah, it
it's
just
like
needs to have a way to properly define it.
Yeah.
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 Let's see. Yep, the interquartile range, because you got like that makes sense.
Yeah.
Yeah, so you have like the median, the quartile 1, quartile 3, and then like this thing is the interquartile range, and then the whisker goes 1.5 times the interquartile range. Or well, it's the largest and the smallest value within 1.5 times the interquartile range. Okay. Random sample and statistical model. Random sample is a collection of random variables that have independent, same distribution, makes sense. A random variable is a heuristic depending on the random sample, and it's just called a sample statistic. Yeah, and if you have like a random sample consisting of multiple random variables, then the one that's like actually the random variable that is being simulated, or that's like being contained in that random sample, is called a model distribution. So you can have a random sample of 10 binomial distributions, and then the model distribution will be binomial. And that's all we need to know. Okay, that's surprisingly little for surprisingly a lot of exercises. So let's get started. Suppose you're giving the following. The chance of a number being less than q is about 0.15. It follows that the number q is the n percentile. So that's either 15 or 0.15.
Yeah. I would say it's 15, I think.
It's 15.
Yeah, because it's your percentile, so you don't have to add your own percent. Median can be found at the 50th percentile because it's the middle point. The quantile QP can be determined using the inverse of the distribution function. What is QP equal to? Let's see. And this makes sense when you think about it, because we have let's see, the chance of it being, I think this was the definition of a percentile, right? Wait.
It sounds about right.
No,
it's the other way around? Excuse me. Wait, let me actually get this one down, because this one's at least semi-important. So wait, what's this? Oh, this entity amount of entities, I guess. Yeah. So then we just have. Oh, okay, I guess makes sense.
No, P is like P is the quantile, I think.
So like.
And QP is the value.
Okay.
Right.
So you notated it right.
The first time, or?
What you just had was right. This is wrong. The other way around.
Okay, yeah.
The probability of x being a value, QP is the value in the dataset, and P is the percentile / quantile.
Yes.
In
Okay.
this case,
So
quartile.
this is like the value between 0 and 1, namely the for example, for the median that would be 0.5, and this is the number that is at, for example, the middle or whatever. Okay, that makes sense. Now we can rewrite this using the F notation, so we can have the F of this thing is P, and we want to put this thing. I hate how they use inconsistent notation. So they, like in those slides, they use Qn of P, and here they say Q of P. Whatever. But yeah, as you can see, you can just take the inverse of F on both sides, and you will get
Right.
you will get this.
F minus 1p.
So you have QP is equal to the inverse of the yeah. There we go. The inverse of the distribution function. The median.
So QP is X and P is probability, basically.
Yeah.
Quantile, not
quantile.
percentile.
That it's like
Quantile, yes.
0.5.
0.5.
Yeah.
Basically, quantile is just percentile divided by
That's always the question gonna got me. It's like wording question more than math
They're
question.
wording things. It's like okay.
The quantile of solace.
So you have.
No.
Okay. Okay, cool.
Are you in your car again?
Why would you guess that?
Bullet number Q is the.
Consider the environment noise you're having.
Yeah.
Yeah, I'll mute myself when I'm not talking.
That's 0.2.
Yeah, exactly.
Yeah.
So I remember that like here it says quantile, which doesn't have the sense, and the percentile is the one that already has the 0 point.
I mean, it literally got percent in the name.
Exactly.
Yeah.
So this is equal to the 0.5 quantile. Cool.
And yeah, 5 out of 6 good enough.
Compute the median of this distribution.
5.
Yeah.
Wait, no. Wait, yes. Oh.
Yeah.
It's
like the average of a set of uniform values picked between 4 and 6.
Is 6 plus 4 divided by 2.
No, this was just so
find
simple.
this for a standard normal distribution. Use 2 decimals in your answer.
So we just need the table from the
what we're asking here is we're asking for the chance that x is less than
0.67.
You know, less than or equal to. It doesn't matter because it's uniform, but whatever. Or because it's continuous. So this is what we're. Yeah, so this is what we're looking for, and to find that we can go to the formula.
No, wait, it's QP. So P is 0.67. So we have to find 0.67 in the formula sheet and get the X value from that. We don't know QP. We only know P.
Right.
Yeah.
We know the. Wait. Do we know the value or the chance?
Wait, what's the question again?
So we have Q of 0.67, which is what he has done there. Yeah.
Is it though?
So we have the value 0.67.
We have this, right? And this is the value that's given to us. Namely, oh wait.
Q of P. Which is the same as F.
God.
Yeah.
This is stupid.
Yeah. It is very stupid with the mixed notation stuff, but...
Okay,
yeah.
So we have to find this. Okay. Huh.
We just need
notation sucks ass. Change my mind.
Yeah.
But that doesn't seem to make sense.
Let's see, so...
Formula sheet is the second one.
Yeah. So 0.67.
No, we should look for 0.33 because
because it's the left tilt probability.
Oh yeah.
Yeah.
Oh,
0.33. So that's
0.44.
And you put it to...
No, wait. Well, no.
0.3300.
0.33.
0.44. The answer is 0.44 because we have to find 0.33 in the table, not on the axis,
okay.
whatever.
Fair.
So it's 0.33 corresponds to 0.44.
0.44, yes. So the answer is 0.56. Because it's 1 minus.
Yeah.
Is it?
Yeah, because the table given is P
0.67.
greater
Yeah,
than
yeah,
equal,
so
and
we
we're
are
looking for less than equal.
Yeah, so we have this, and then we take the 1 minus. So this, because this table has greater than or equal to, so then we have P is greater than or equal to X, and then we have 0.33. So I think it's not actually 1 minus. I think it's just
0.44.
Yeah.
I think
it's
okay.
just
So I may be wrong.
You don't have to invert it again, I believe.
Yep.
Yeah. We're thinking too much.
Okay.
Yeah.
I'll just do one more step.
Determine the X quantile. So they're asking for the number such that that percentage is above.
I think they're looking for the value that is that any value below has 97.5% chance.
Yeah, so
Yeah,
so probability of Z is less than or equal to.
Right. Z
Yeah,
is
so
less
this is
than,
actually a case where
Yeah.
Probability that it's less than set is 0.975.
Yeah.
And I just look on the table. It's 1.96 if you're needing it.
Yeah, let's see. So it's less than this. So that would be, again, because it's less than, and the table shows the right tail probability, so that's greater than. So that's going to be
0.025.
5.
And it's 1.96.
And this is 0.0. So that will be 0.03 then.
No,
you're looking at the value, and
Oh, yeah.
inside the table.
I keep misinterpreting it.
Inside.
So that would be 2.82 on the.
No, 0.25.
No, that's 0.0025. It's 1.96. 1.96.
You're right. My bad. Sorry. I just saw that 0.25 and oh yeah, that's it.
Yeah.
1.96. So let me. Yeah. Okay. So
Which remember that one? It's the value for the that comes out later a lot. It's called like the 95% confidence interval.
Oh, true.
They like to use that one, so it's like hammered into my brain.
okay, give me a sec. I'm trying to process this.
Story of my life.
Yeah, no. I just like, cause I know I'm going to fuck up a lot with this. So I'm trying to make sure that I actually understand what's going on and remember instead of just copying you guys.
I swear, I'm
yes, okay.
sure I'm
That
gonna
makes
fail
sense.
this.
Because we're working with percentages, and the percentages are always after the equal sign because
0.
Yeah. So which Z score? What the fuck is a Z score?
Z score.
It's standard normal distribution.
Normal.
Okay, fair.
It's equivalent. It's how.
So what's the expectation of the standard normal distribution?
It's the mu minus xi over Z score is also equal to mu minus xi over standard deviation.
Yeah. But
Square root of n.
Because we have nothing else here, we just have we assume it's about a standard normal distribution if they just talk about Z-score, nothing else.
Yeah.
Well, the thing is, everything is approximated to a standard normal if you use Z-score.
Yeah.
Yeah.
And one Z-score is one standard deviation away.
All right. Challenging questions about quantile.
Hey. How
Compute the
challenging it's
median
gonna be?
of a par 3 distribution. Use the decimal in your answer. Okay, that one's not too hard, honestly.
What is par distribution? It's a Pareto one?
Pareto, yeah.
What you do for the par is you go up here until you see something that looks like it. Hey, there we go.
Yeah.
Very important. So, this is the, Oh fuck! They don't let me copy it, motherfucker.
Yeah.
Okay, so we have f of. Let's see, that's the thing again. 3. So we have f of x is equal to 1 minus x to the power of -3. The person with the background noise, please mute yourself if you're not talking. Thank you.
That's Amon.
Okay.
Yeah.
And again, so what this is saying is, what is the chance that it will be up to or and including this number? Or yeah. So fx of infinity will be 1. Okay, so it makes sense. So out here on the right side is the chance, but we have okay, and we want to calculate
The median.
yeah. So we know fx.
So the median is when the probability is 50.
Yeah, you have to invert the formula.
Yeah, I know. That's, we just proved that a bit ago, but I'm trying to like truly understand it as well. So let's see. This thing is the chance, therefore. Yeah, okay. So f inverse of x. Let's see. Just to invert this for a bit, let me see if I can
Wait,
figure it
I
out.
mean,
So we have y is
should
equal
we-
to this.
Why we have
around.
to inverse
You don't
this?
have
I don't
inverse.
quite get
You
it,
don't have
because
inverse.
fx just equal to 0.5, right? Because it says median.
Exactly.
So fx is equal to 0.5. So 0.5 equals 1 minus x to the power of -3.
You're looking for the median.
Yeah, you can, but then you invert it. You can either invert
Oh yeah,
it
yeah.
and
The
then
output,
input, or you
the
can
output
input.
is the output is the what's it called?
Yeah.
The
0.5,
chance.
yeah.
Okay, I
Quantile,
messed
yeah.
that one up.
But
so
also,
if we add these
it
together,
would
then we have
give the same result. It will always should be a question of either you input and then invert, or invert and then input.
I mean, it's always
okay. Then we
simpler
subtract.
to input first.
Then we
I mean,
subtract
yeah,
1
that's
from both
simpler.
sides. Get rid of the negative sign. There we go. So then we have x is equal to 0.5 to the power of. Let's see. Thinking about that, that would be
Minus a third.
minus 1/3.
Basically, 1 over x to the power of 3 equals 0.5.
Yeah, and
No,
we can.
No, it's 1 over cube root of 0.5.
No, I mean, in the other,
Yeah.
that's
Wait.
the same thing. Dude.
Yeah, that's the same thing.
Yeah, so we just have the cube root of 2.
Oh yeah, you say minus 3. Yeah.
Or I'll just write it down like this.
Yeah.
Use 2 decimals in your answer. Haha, you.
How about
Oh, you use more.
6 decimals?
Compute the 0.10th quantile. So it doesn't say percentile, quantile of the x per 0.4 distribution. So again, we can just take the take this one. We have the fx is equal to this. So
It's like,
let's see. We have fx is
calculate
equal
the
to 1
value
minus e to the
at
power
which-
of minus lambda x. We know our x in this case, or our lambda in this case is 0.4. And we want to set, because out of here comes the probability, and we want to find the probability 0.1 of this. So we just say is equal to 0.1. So this is what we have to solve. I will subtract 1 from both sides, get rid of the negative sign. That will bring us to like this. We will take the natural log of both sides. That will give us this. I will get rid of the minus sign here, and I will divide both sides by 0.4. There we go.
You forgot the negative.
You forgot the negative.
No, he didn't. He didn't.
Oh,
it's the
okay,
negative
yeah.
in front of the ln. So in
And
front of the
they-
fraction. Yeah.
And there we go. Okay.
Watch out, the
that's-
next one is out of order.
Yeah. So this is basic
So-
practice questions. Okay. Practice now. Suppose you're given number of elements in data that is less than x over n. So let's see. I'm being thrown off because I usually use F as like the this F, but this one is a different one.
Sounds like an effing chat, but
This is I think empirical cumulative because it basically
that's
for
not
every
a-
X it adds on top of it.
Yeah, exactly.
Yeah.
Yeah, that makes sense. So what this truly means is this is like the yeah,
You
so this is
actually,
like a
like,
quantile,
explain
but
the-
you actually take because you can't take based off one thing. You take a sample, and then you divide by the amount of things in a sample.
Yeah.
Okay.
Like, I actually don't
it
understand this
ends at
question.
one.
Like, what does it mean? Like, does it mean like?
Like you're drawing a graph, and your graph
Yeah.
goes the number of elements in the data set that are smaller than your value.
So you.
divided
Oh,
by
okay,
the number
okay.
of elements
At
in the
the
data set.
size,
So
yeah.
it goes up as you go because, of course, like the bigger the x, the bigger.
Yeah. And it
So
ends
that's a
at
CDF.
it
Oh, I
ends
see,
at
I
one.
see.
And
It's
it ends at
basically
one.
the statistics equivalent of like what was it called again? Not the mass function, the other one.
I was going to say distribution function, but I'm not sure about that one. Density function, maybe?
Yeah.
No, density. Yeah, I
No.
think so. Yeah, commutative
No.
density function or something like that. The small
Okay.
f.
But basically here is just number of elements in data set less
So the
than
bigger,
x
yeah.
over n. In this case, that's 2. We have 6 elements, so that's 2 over 6.
Yeah.
Kernel density estimate provides, let's see, a less smooth, an equally smooth, or a smoother.
A smoother. Histograms are
smoother?
cut in different sections, whilst the
Let's see,
kernel
let's see,
density estimate is a line.
Yeah, it's like a.
Go back up.
Does
I
it
think
ever
it's
even
all
fucking
just
mention that?
slides.
it's like
I
sand. It's like
No,
building
it's a bit further
sandcastle
down.
out
There's
of
like a. Don't scroll that fast. Yeah.
Kernel is building a sandcastle from statistics.
No, a bit further down. That was one, I think. Yeah, that is.
Look, that.
It is relatively smoother.
I
It
see.
is definitely
But you-
smoother.
Yeah.
Yeah, okay, I see.
But it's a line, whilst the histograms is bars.
Yeah, okay, makes sense.
Because you're keeping the values from the previous sections, basically.
Yeah, exactly. Like this is discrete, and this is like commutative.
Yeah, and also you could theoretically just take all the points and draw a smooth line between them, but you can't really do that. Or you
Yeah,
could
like
try to do that in
you
histogram, but
could,
it would be
but
less
it would be
accurate.
very, very misleading. Say like that.
That's kind of what the kernel one is.
I think it's up and including. So
Yeah,
that
including,
would
not
be-
including the number.
That would be 5 out of 6.
Yeah.
Which is like only 11. That's more.
Okay, so yeah, here indeed there's 5 that are less than or equal to 9, so
Yeah.
it's 5 out of 6. So this is just like indeed the normal density function, but then like empirical, which that makes a lot of sense. You've collected the exam results for last year, probably statistics course. Everybody fails. Which types of data visualization would be most suitable to visualize the data set? Well, we realistically just want like to see the discrete data points. So I think just a histogram would be best for that.
Yeah, I mean, we know it because everyone like checks them on the Saris and stuff.
Yeah. So now we have the challenging questions. Were they out of order?
No, they were fine. It's because there was.
It's just that the
practice question.
non-TUD practice questions were before the basic questions for some
I
reason.
see. You're asked to represent these data in histogram. Use standard deviation to compute the approximate bin width for the histogram.
Right, that's
There's
a formula.
yeah, 3.49 times something.
That was only given in the book, right?
Yeah, that's the only one in the book. Like, you can search in Discord chat. Like, someone mentioned it, I think.
Yeah, I think it's pinned in the PTS.
Are we
channel.
talking about the length of a standard
No, it's not
deviation?
pinned. It's not pinned,
No,
unfortunately.
It's Tim's PTS summary. That's what I meant. The Google Doc.
Oh, is it?
Yeah, it's linked. It's pinned. It's the first thing that was pinned in the channel.
Wait, so.
Wait, where is it?
Go to
A PTS channel
Mistake.
pins and
Yeah.
then Tim's message.
Oh.
Yeah.
Google Doc working
Where
on summary
did
for
he-
Discourse.
Yeah. It has all the slides plus extra.
Oh, damn. Nice. Ooh, it looks fancy as well.
Yeah.
Yeah, Tim
This
put a
is
lot
so
of work
good.
into
So
this, I
good.
can tell.
It's also because it's Google Doc, you can just jump between sections because it has the Google Doc has automatic
true.
index function.
So we have, let's see,
Oh, I couldn't find it, to be honest with you.
Histogram, it should be at Histogram, I think.
Histogram.
Tim,
Unfortunately, no.
Tim and
Either
Jan
I'm
are
blind or like
Yes,
I think
yes,
I'm blind, to be honest.
It's something with 3.49 times something.
Yeah. Wait, it's not 3.41, wasn't it?
I'm pretty sure it was 3.49
No, not
times
not 0.3,
times the cube
3.4.
root of n.
Yeah, maybe we can
I
ask
don't think it's
Tim.
in there. I think it's in the book.
Just Google it. Just
And
Google
I
it.
remember
Just
someone
Google.
mentioned that they only saw it in the book. No, you can't Google it either because I tried Googling it and then didn't actually give me that like
It
the
was
answer that
Histogram
they
like
expected
equation. Add an equation in the end.
Yeah.
A formula or whatever. Yeah.
Yeah. 3.49 times interquartile. They want us to use 3.49 instead of 2. But that's the formula.
okay, so this is the formula, other than that they use a more specific value, namely,
Yeah.
yeah, okay.
Yeah.
So the,
So for some
then
reason, I don't know where 3.49 comes from, but it's just what they use.
So, wait. 3.49. Okay.
With it didn't put a space. Yeah.
okay, so we have h is equal to this number times the interquartile range times n to the power of, yeah. Okay, so this is all the data.
This part is a lot of just learning formulas. Just write down all the formulas there are, learn them.
So if I order this data, it would be minus 131, minus 126, minus 112, minus 86, minus 18, 31, 83, 173, 253. Recompile.
Yeah.
That's the total. It's 1, 2, 3,
Yeah.
4, 5, 6, 7, 8, 9. Yep.
9. So 10. Just do 10 divided by 4, which would be 2.5, and so on.
Yeah. Okay, so we can get the median pretty easily.
Yeah.
So you're looking for the interquartile range. So that's
Yeah.
Where are you looking for the median?
lower quartile.
We're not. It's just simpler to find the interquartile range because
Yeah,
it's an odd number of samples, but not odd enough.
Yeah. So again, IQR is equal to what was it? How did they note it again?
Upper
0.75 minus 0.
Yeah.
Fuck off with your Microsoft fucking
Microsoft being big brain.
Quartile minus lower quartile.
Yeah,
Yeah.
minus.
Yeah. Yeah.
Yeah. So basically, we want the number such that 70%. That's like it's 75% of it is less than or equal to that number, minus the number that's 25% of it is less than or equal to that number.
Yeah.
Okay.
So
let's see.
the
We have.
mean between two and
That should be
So
the third. The third and the seventh.
the 2.5th and the 7.5th value.
Oh, yeah,
So
the
you have to
2.5th,
calculate
yeah.
the in-betweens.
The mean between 2 and 3, and the mean between 5, 7, and 8.
Yeah. So we can say that the QN
No, it's not exactly the mean though.
is equal to the difference between let's see.
83
between this
and
one, that is frac 83 plus 173 over 2.
I am now
which
here
is-
without awful amounts of noise.
I'm honestly gonna keep Wolfram Alpha open because this should it can evaluate
Yeah.
my
You serious?
notation.
Like they both end with 3. It's not that hard.
Nah, dude. You don't understand. I'm actually very lazy.
Aren't we all?
Calculating in my math course? No. Oh.
There's a reason we took computer science,
I
and that
don't
is
think
laziness.
that's exactly how you.
So that's
We
126.
do be
I
allowed
believe that's how you
calculators,
calculate the
We do be
quartiles.
allowed calculators, but I don't think Wolfram Alpha is considered a calculator.
Yeah, it's
Sadly.
yeah.
Somebody
It's-
saying
Yeah,
that's not how
also-
you calculate quartiles. I do remember indeed
Yeah, I'm
something.
It is. It
I'm
is
pretty
how you
sure it's
calculate
isn't it n plus 1 times p, and then you have to take the integer part, and then that's the number,
No,
and then the after the comma times the difference between that value and the next value.
No.
No, I do get what he's saying. Because I do remember this from, I think that was lecture like 1 or something.
yeah,
Or
so,
they went
so
over how to-
basically take
4.75, you take the fourth one, and then plus 0.75 times the difference between the fourth and the fifth. Oh wait, the fifth and the fourth rather.
Yeah, but that's basically the same. I mean, we only have.
we have 9 data points, which means that
Well, we have
the
9
median
data
is at 5.
Yeah, we don't
The
have
lower
10. That's what I
quartile is at
said.
2.5,
Oh,
and
right. Fuck, I thought we had 10. Remember?
No, 9.
Yeah, I said bullshit then. Sorry.
Yeah, but it is good to actually train it. Like if we don't get that
Yeah.
question, I do want to test it with a data set which has 10 points or a different amount of points because I do want to be able to do that on the test.
Yeah.
So let's see.
Well,
The difference between these two is
for us-
14,
wait.
7, that's 119.
Yeah, but that's not valid then.
Then, no, but that's
9
because.
points.
Yeah, because that's for 10 points. So for us, it should be 6.75.
No,
Because
it's for,
0.75
no, it's for we did it for 9 points because we did 9 plus 1 over n, which is and then 9 plus 1
No.
over 9 plus 1 over
No.
4 and 9 plus 1 times 3 over 4 to get the quartiles.
They
That's accurate.
Yeah, which 10 over 4 is and we have 9, so 10 over 4 is 2.5 and and 30 over 4 is 7.5.
Guys,
Hmm?
I bought a set of stationery, and I think it came with a staple, but no staples.
let's see.
Not really what we need right now.
Yeah.
Unfortunately, yeah.
Wait.
Wait, no, they can't. They're here. I found them.
Cause
Right,
I
sorry,
remember
I thought-
something
I
like
thought
what
you
you
said
guys
there
were
were
saying
10
being
data
explained,
points.
yeah. But I'm not sure where.
I think it's in lecture 8.
I think it's in the lecture recording. I don't think it's on the lecture slides. I'm pretty sure I remember Erdal doing it.
Yeah, I remember like my
Google how to
my lecturer doing it as well, but I
quartiles.
can't find it anywhere.
Just
If
Google
it's
how
only
to
in the lecture
calculate
recording,
quartiles.
then fuck this course, honestly. But
So okay, so
I mean,
this,
that's
this
about
data
the
set-
thing they
Fuck this course
explained.
regardless.
So this data set has 11 points. If you do 11 plus 1 over 2, that's the median. That's the sixth value, so 5, and so on. Yeah. See,
Check the general voice channel.
yeah. So the low quota, yeah. That's what
Oh,
I
it is
said.
n plus 1. Okay, never mind
Yeah.
then. Sorry about that.
okay, but
It doesn't count for intermediate values.
yeah, like this only works for when there is an. Actually, I
No,
will
you
use
take the.
I will use this for
you
now.
take-
However, I will check it for like the
Yeah.
Yeah, I will also do this for the for a data set with more values and see how that works. So right now, if we have a 4 times 10, that would be the 7 or the 2.5 terms. That would be the average between these two. So that was correct. And
Yeah.
same goes for this one.
Yeah.
That would be the 7.5 term.
Yeah.
So for this
And- yeah.
question, these two are correct. And then I can take the top one, which is 128, minus the bottom one, which is minus 119, which changes into plus 119, which is equal to 247. So the interquartile range is 247.
Yeah.
Yeah.
Okay, and then we can use that to calculate the bin width. So then we can say the bin width is equal to 3.49 times 247 times 9 to the power of minus 1 over 3. And that's just literally all gained from filling in stuff in this formula here.
Yeah.
Mhm.
I mean, you could just put that in Grasple.
No.
No,
I think it's a bit too
it doesn't
complicated.
understand this part.
Yeah, if
Yeah,
you want,
Grasple should I understand it though.
I don't
I'm
think
pretty sure
so.
Grasple
We'll
understood it
see,
when I put it in.
Yeah, Grasple understands it. Yeah, just replace the dots.
If I replace this, then perhaps
Yeah.
this one, and maybe this will work. Compute the
Yeah.
standard deviation.
What?
It's not the it's not the interquartile range. It's the sample standard deviation. But I was in a minority, so I wanted to check.
Maybe just skip it. Like, just skip it and check the
Yeah,
formula
just
first.
see
Maybe.
what
Like
it,
it's the same formula, but instead of the interquartile range, I think it's the sample standard deviation.
I'm gonna be honest. How the fuck do you calculate the sample standard deviation?
I think it's
It's
interquartile range
pretty
divided by
simple.
2 or something.
You just take you calculate the mean, and
Yep.
then for each value you do the value minus the mean, then square that, sum all of those square differences together, and then divide it by I think it's
Okay,
n
so-
minus 1.
Yeah, that makes sense. I remember.
I
something
remember
like that.
this
So
formula was such a fucking pain.
No,
Yeah.
what he's
Calculate the
saying. What
variance,
he's saying
then
makes
you
sense. So
use
what he's
square root
saying
it.
is the standard deviation is the average of the squares of the differences, which makes sense. So let's have a look at at that. So if we have this data set here,
No, but
we know-
then you have to square root it because we want the standard deviation of the variance. You have to square root it at the end.
Yeah, but
Yeah.
first you have to get the sample standard
Yeah.
variance.
yeah.
Anyways.
So let's see. For this sample, let's see. The average here is. Wait, is it from the average or from the median? Or
Yeah, from the
Mean.
average.
From the average.
okay. So then we have to take the average of this one first.
Well, the mean, yes.
Yeah. So. Wait.
Just feed the values.
Yeah.
This course is
My
such
computer's being
bullshit.
really slow. Oh wait, I'm recording. Yeah, that makes sense.
At least there's no greebling.
Hey, that. Oh, okay, yeah.
That makes sense because
Yeah, no, because there's a bunch of negative numbers. I'm like, no, that doesn't make sense, but it does. So that is 7, and that's 4/9. Can we just take the difference between these and 7, 4/9?
So you take the difference of the squares of those. So
No, you
square
take the
mean,
differences
square-
and square those, right?
Yeah.
Yeah,
Yeah.
so you square the mean, you square the values, and then you take the
No,
difference.
you
No,
take the
no,
difference
you
and then
take
square
the
that.
square of the differences. You don't take
Yeah,
the
not the
difference
difference
of
of the
the
square.
squares.
Why don't you just write it as 67/9?
Yeah, I could.
Yes, that's actually better.
So then we have, and so the differences is that like the absolute value of the difference, or just actually one minus the other?
Well, the squaring is actually meant to get rid of the absolute value.
That's
section.
true. That's true.
Yeah,
so it doesn't matter
you
what order we
square
do it.
Yeah. Just
Actually,
do like
have-
that minus.
It does matter, but
This thing minus. I'll just write it down first for myself so I can actually understand it. So what we're doing is we're taking the sum of all the numbers such that the this number, so the median or the mean minus every number squared, then we sum those and then we divide that by n.
No, but you need to sum the squares, which is not what you're doing right now. That's not the same as doing x minus mean squared plus x2 minus mean squared. You're summing the values here,
Yeah.
and then you want to subtract that from the mean and then square it. But what you need to do is subtract each value from the mean and then square the difference.
Yeah, but that's what I'm doing, right? So I for every value, I take this value, subtract the mean, square the whole thing, and then divide by n.
Oh wait, never mind.
Yeah.
Okay, so this here is correct.
What?
Okay. Now, I've seen people talk about calculating the standard.
Oh, sorry, I'm stupid.
No, it happens.
Wait,
It happens.
it's the other way around though. It's value minus the mean, not mean minus value.
It doesn't.
True, it doesn't matter because it's being squared, but
Oh, true.
but you know,
Doesn't
good point. It is good to like
Yeah.
have one way of writing it. So yeah, we sum all the things here. Okay, so let's do that then. Minus 131. Can I not just write a program that does this for me and then put the answer into Grasple?
Yeah.
Probably,
But
I
we
think
can't
probably
use it
will
in
Yeah, but
the
we can't do it on the
easier.
exam. So
Dude, I made a fucking Excel sheet that would calculate it for me in high school.
okay, I'm just going to assume everybody can understand how to do this because I CBA. So let's see.
Understandable. Just 1 point. I'm pretty sure that for the sample standard deviation, you have to do n-1 because statistics is weird and not divided by n.
Let's see.
You can Google that though. Sample standard deviation.
Fucking hell.
Yeah. For some reason, divided by n-1 is the maximum, or is either unbiased or is the maximum likelihood estimator. I have no idea why, but it just is like that.
I can already tell that I understand why this course has such a low pass rate, but
30% pass rate. Yeah.
we're 40. Yeah, no, it's actually 37 or something like that. We're 40 minutes in, and I already don't understand the shit. There's 4 num in num.
First lecture as well.
Yeah. So then we say total plus is the average, which is 76 divided by 9 minus the number squared, and that operand type. Wait, why can I not put a float to the power of an integer? Pow this thing, comma 2. Okay, and then I can take total divided by n-1, which is 8. And then this thing, and we want to have the standard deviation.
So that's the square root.
Also, I will say that this
the
is
square root of
the
that.
sample standard deviation. So then I take.
I think that number sounds a bit high.
Yeah, but that's because we haven't taken the square root yet.
Yeah, but even for.
Existence is pain.
Yeah.
Even
The-
then,
so-
that.
No,
wait,
yes,
wait.
that fits.
No, the
Look
standard
at the
deviation it makes a
values.
lot of sense because these numbers are all over the fucking place.
Okay,
Look
yeah.
at the values. This
Yeah.
is the average distance from the mean. And
Yeah,
if the
so-
mean's around 0, like you've got minus 112, 250, that fits.
I
That fits.
suppose.
Yeah.
Yeah, I see. I agree.
Okay, so then this would be, in theory, the number.
Oh, it's n minus
replacing-
1 because the mean is already accounted for. You accidentally put the mean in the I think you accidentally put the mean in with stuff which you shouldn't have.
Well, no, not really, because the mean.
Oh, it will just be 0. Yeah, it will just be 0.
Yeah, exactly, and not only
Yeah.
that, but the mean isn't a sample point. That's
True.
the median, which is a sample point.
Oh yeah.
So it's just statistic work.
It just
Okay,
says
so
this.
compute the
It's
binwidth,
just
use one
statistic,
decimal place
yeah.
in your answer. So we have this magic number times the sample standard deviation that we just computed with fucking Python times the numbers to the power of minus 1/3. Praise the Lord!
Let's
Oh
go.
god.
Oh my god!
I really wish we could use Python during the exam because that would be a
You know-
pain
you
in
know,
the ass just to
fuck this
calculate it.
Fuck this course and all the math involved.
Yeah.
Oh my god.
The thing is, I'm saying it's just formulas, which is the worst part of math. Like,
Yeah, no, I will actually
Yeah.
screenshot this and post it somewhere where I will remember it, but Jesus Christ.
They don't
We have
even
spent-
give it
Do you want
to
do you mind just
developer.
posting Discord chat maybe? Just post
Yeah, I put it in the,
Yeah,
I
he
put it in the
did.
VC channel.
It makes no. There's no logic behind it. Like, okay, I actually skipped this, but I don't see anywhere where it explains where the number 3.49 comes from either. And
Yeah.
it's nowhere
No,
on
it's
the
just
internet.
from
the
book.
worst part
Did
is
someone ask you? Oh, it's from book.
it's not even in the fucking slides, so I wouldn't have known about this if it weren't for you guys.
mhm.
And the
So
Grasple
fucking
exercise.
stupid.
Because if it didn't show up in the Grasple exercise,
Yeah.
then you wouldn't even have known it, because
Yeah.
no one would have told you.
I learned it by failing the Grasple exercise.
Yeah.
Based.
Yeah.
So
Yeah,
let's see,
you
this
learn
is
from
a
your mistakes,
histogram
right?
with the following bins. What is the empirical distribution function at t is equal to 8? Yeah, so the distribution function
0.5 0.05 times 2 plus and so on.
No. Why would you multiply it by 2?
No. I think
Because it's with it's from 0 to 2 with height that the imperial distribution function is for each integer up until the end.
Oh,
But
Right, yes,
the histogram
yes.
is the histogram is so you have to adjust for the like width.
yeah.
Width of
So
the thing.
because
Yeah.
what I was thinking, right? A distribution
true,
function
it's the
always
area.
ends with 1, but
Yeah.
these added up don't end with 1. So you're right. So it is.
Yeah.
Yeah, because you're dividing over a
Because the
bigger
probability
area.
is the area of the histogram.
Yeah.
So you have to
So then it's not
compute
2, but 3, 4, 5. So that's 3 times 0.15.
No, oh yeah,
Yeah,
it's
that's fine.
5 minus 2 because it's 2 exclusive. You can take it's 3 because
Yeah,
it's
and then 1 times 0.03. And then we have 7 and 8 times, so that's 2 times 0.08.
Yep,
Yeah.
and that should be right.
Yeah.
There we go.
Hey. Or we can just
Yeah,
Yeah, you can
Oh,
also just have 1 minus.
Let's do
No.
it again.
It's the same number.
It's actually no, it's the same
Same number,
value.
same number, same numbers, guys,
Same,
same numbers,
it's
same numbers.
exactly the same.
Just don't forget to do C dot and the minus.
Yeah, I'm not sure if the minus actually fixes anything, but Grasple, I just like to be sure. Let's go!
Woo! We have to do it again.
Okay,
Ooh, smashed it. No,
If
I
you
wouldn't
want
have
green, just copy it again. It's probably
How about you stick one up your ass? Okay.
yeah.
It's the
I
exact
prefer
same
not.
question.
Okay.
And I think this was the basic.
Also, within the
No,
PTS
that was
summary
the-
published by this thing here. So this is what I was looking for about the quantile. So I will make a and this is just for practice because fuck. So also in case so we have I'm gonna create a set 0 0 1 2 3 3 4 5 6 7. How many is this? 1 2 3 4 5 6 7 8 9 10.
Oh no, they hate me.
Okay, yeah. So this doesn't round well. So say I want the 0.25 quantile or the 25th percentile. Let's see. Meaning the value. Yeah. Okay. So let's see. The quantile is the number at the case position plus a times the difference between the two numbers, where k is. Oh wow. Okay.
That's the
Okay.
integer
Realistically,
part.
let's first think about what this k is. So, k is p, which is in our case 0.25 times n plus 1. We have, what is it? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's 0.25 times 11. 0.25 times 11. 2.75.
Rounded down.
Yeah. However, we round it down, so indeed it's 2 in this case. And then the alpha is... Yeah, so the alpha is the integer part. Because we are taking the number
K is
minus
the integer part.
the... yeah? Kun je hem net pakken en dat doen? Kun je hem net pakken en dat doen, want ik zit in mijn ding. Had ik het niet al gedaan? What the fuck? Alright, so let's see. Yeah. So k is rounded down and a is the integer part. That's good to remember. So then we have... What this really says is this says the p of 0.25 is equal to the second number plus the what's not the integer part, but the, how do you call that? The
Decimal part. 0.75 in this case.
Yeah, so we have times decimal part times x3 minus x2. Okay, this makes the formula a lot more understandable for me.
Yeah.
So yeah, we just have the lower number plus the decimal
You
part
need
times the
brackets around
difference.
the
between the two.
0.25 to make it look nicer.
God.
It's also pretty intuitive.
No.
Well, let's just try and get lecture 8 by the end of the hour.
Okay.
Yeah.
Okay, so now we
we have
also
10 minutes
understand.
left.
Let's also just do this in practice. So the decimal part here is 0.75. The second point is, and the second point is starting at 1, right?
Yeah, start counting at 1.
Yeah. So the second point is 0, and the difference is between 0 and 1. So this is literally just 0.75. And of course, I'm bad, so I should have put brackets around this. But yeah, the 0.25 quantile, or the 25th percentile, is equal to 0.75 in this case.
Just to fuck with you.
Yep. Okay, cool. The formula of the bin width can suck my dick. That's a really, really annoying formula. Why is it 3.49?
Good question. Someone just posted a paper in the Discord chat. If wondering, we can just read the paper together and wondering, huh?
They're this motherfucking
It's
Pretty sure.
Yeah,
As someone who did
I'm pretty sure the
physics,
academic
someone-
grade
yeah.
paper will be
Yeah.
more understandable than this fucking course is.
Yeah. As someone who did, as
I
someone
tried
who
to
did
read
physics,
it, not understandable.
as someone who did physics, I just stopped questioning constants. They're constant, just plug them in.
Curse you, David W. Scott.
Yeah.
It's literally the most complex thing I've ever seen.
Yeah, it just shows
Is it
that
like
when the paper
a
guide.
year?
It's
Every time
here.
I use this-
It's here.
Optimum age.
It's here. The paper checks out. It's literally there. Why would we not
Yeah.
trust it?
Yeah, citation, you'd trust
Back to
me.
lessons. What else do we need to do for 8? Oh wow, we're almost at half of 8. 50 minutes.
Wait, do you just wait? Oh, okay.
Yeah, we skipped this one because that's like the duplicate.
Yeah.
Scatterplot basics.
Okay.
Okay. Suppose you're plotting two different variables in scatterplot. The blank, the data points are to a straight line. The blank, the linear relationship between the two variables.
The closer, stronger.
Closer, stronger, further away,
Both are
weaker.
right.
Both
Yeah,
are
but,
right. Yeah.
Like,
Yeah.
yeah. Okay, so they're just both right. Cool. A
Select all
scatterplot is
that
used
apply.
to. Yeah, and we actually
Whoa,
see
I wonder what this one is about.
Yeah, no, but actually we've seen scatterplots before, and they're used to show
Yep.
correlation,
Yes,
but not
Yes.
correlation.
not
not
dependency.
causation.
Yeah, so
Actually.
Hmm?
No, wait, never mind.
like I mean, it depends, right? You can for example guess or see dependency in a scatterplot, but like correlation is actually like the measure of is there a right line going, for example,
Yeah,
from
yeah.
bottom left to top right, and
No,
dependency can be
I
like
got confused for a second because like every dependency is correlated, but not all correlations are dependencies. That's why I got confused for a second. But yeah.
Suppose you want to visualize the relationship between two data points, so like literally the last question. What would you use?
We should use a box plot. Yeah.
Imagine if there were like one
Also,
scatter plot
I
with a
think it's
space in
the other way around, by
between.
the way. You can have a dependent but not correlated, but not correlated but not dependent. Yeah.
Yeah.
Okay. Suppose you're given several parallel optimization, a data set that contains two variables called bivariate. You can also trivariate data sets. Please don't.
Dimensional axes.
No one. It's just gonna be XYZ diagram, I think. If you try very.
Well, okay, yeah, but you can't like doing a scatter plot of a quad variant would be more annoying.
I mean, you could theoretically go 6 by just using the negative axes of the three-dimensional of R3.
Not really, because you can't plot a point simultaneously at +3 and -3.
I mean, yeah, true.
That would show the things between like 3 variables and 3 other variables in different parts of the graph, but it wouldn't show between like one of the first 3 and one of the second 3. Either way, measures of
it's time
center.
to send to a 4-dimensional. Oh wait, no, never mind. Don't gain 4-dimensional consciousness. I don't want to do more complicated math.
Yeah.
How hard can this question be?
Ooh.
It's Python time.
Yeah. So if we take the power of 4.2 to the power of
Huh?
no, I'm kidding.
You actually get me there for 1 second. I was like, hold up.
So. Huh? 7.5. If I had
Is there
that
any
on
reason you're not typing the exact same thing just into Grasple instead?
yes.
Python superior.
Medium.
Yeah, no, I'm getting there. No
Medium. 1, 2, 3, 4, 5.
The sample median. A median is the middle point.
Yeah.
Yes.
I
And you
love
will
how
order
it's
it
like
first.
compute, but it's actually more like order and look.
Yes.
So we have 4, 4, 6, 7, 9, 11, 12, 18, 22. Let's have a look what the center point is. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Center point is 9.
5. Yeah.
Woo! Let's go. Let's go.
Woohoo!
Is this the
It's a
exact
goal!
same question?
Yeah, I think that's
Yes.
the exact same question.
No, wait, no, the
No,
last point was removed.
You lied to me.
It's
You lied to
it's
me.
8. It's
Oh,
8.
it's
It's
wait,
8.
1, 2, 3. Oh, it's only 8.
The 22
Yeah, it's
got
9 and
removed.
7. Yes. Okay. Yeah.
Yeah.
Let's see. Yeah, okay. No,
It's the
no.
8.
8.
It's the following 5th.
8?
It's between 9 and 8. It's because the medium. It's you only have 8, so it's average
I
between
see.
9
Yeah,
and 7.
average.
Yeah.
Okay. That makes sense. Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we take 14 as our number. Let's make this an
Yeah.
ordered data set. I think this one is not too hard now that we actually understand the formula. Is this already?
Yeah.
It's already an ordered
I think
data
it is
set.
already ordered.
Let's go.
Oh,
Wait. Fuck. I just counted, but I forgot.
Easy.
Oh, it's
13.
14. It's 13 value and plus 1 is
Yeah,
14.
so 13, so we have 14, so we take the k is equal to 14 times 0.25 is equal
5.
to, it's like what, no, that's not true, 3.5?
14 times 25. That's 3.5.
Yeah,
Yes.
3.5, yeah.
So
So
then
it's
what,
case
then what
3
we have is we
after
have
0.5.
the q, it actually rounded down, so k would be 3, but you know, I do my own rules. So we have q of 0.25 is equal to x3 plus a half times x4 minus x3. Okay, like once you use the formula once or twice, it becomes kind of intuitive, which is nice. But
Yeah. Which is 32.5.
yeah, let me actually write it myself. So we have this one, and then we have yeah, so we have indeed 32.5. Next one, we do the same thing for 0.75, which is 3.5 times 3, which is 10.5. So we have x10 plus 0.5 times x11 minus x10. Yeah, okay, that seems to make sense. So we have x10, which is 0, 1, or 1, 2, 3. Fuck, programmer type shit, huh? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 51 and 52. So we have 51 plus a half. That's 51 and a half. Yep. So we have 32 and a half, 52 and a half. The interquartile range is the bigger minus the smaller one. So that's 51.5 minus 32.5, which is equal to 19. Yeah. Let's go!
Let's go!
Reddit.
Easy 10 out of 10.
Yeah, dude, I'm going to get
I
a
can
10 on
see
this
it coming.
exam. I can already know. I can already tell it.
We're gonna get an 11, you know.
So this is an important one to know because Sn squared is used to describe d. So Sn
Simple
is actually
variance.
the sample standard deviation, but because
Yeah.
we square it,
Squared
the
is-
deviation squared is variance.
Yeah.
The mean actually no.
Oh.
Oh, okay. Hi. So this is yeah, this
I
is
wonder
the
what's
sample
this-
variance, and to get standard deviation, you take the square root of this.
Yeah.
Yeah.
Mhm.
Yep. All right. It's good. It's nice to actually show us the formula, and we don't have to pull it out of our ass.
Yeah.
Yeah, after you were supposed to use it.
Woohoo!
After we use it, and we know the formula. Nice.
Wow. People are receiving their TU Delft socks. Holy shit. I want to see enough programmer talks. Can I just like?
Oh
vote
yeah.
them?
Oh,
Wait, there
Yeah,
are?
Not long enough.
that's what they talk about the
just
gifts
have
that
short,
they will
just
send
have
you.
short legs. Just have short legs.
Ooh. Damn, this guy's good. No,
I need to cut off about half my legs, then they're good.
yeah, exactly. What's
mean,
the median? Ooh.
Program subs are supposed to be knee high if you have low knees.
1 over
So
lambda,
okay,
I think.
median is
Or we can-
a
no, wait, never
data
mind.
point from a distribution of this thing. The expected. Let's see, it was x. I mean, the expected value here is just 1 over x. Would that be equal to the median though?
But that's not the same as the
No,
median.
the
That's
median,
No,
we
that's-
have to do the quantile thing that we did in the first task.
Yes.
Yeah.
So
Just
basically,
take the
use the
distribution
fx.
function and put
Yeah,
it equal
0.5 is 1 minus e to the lambda
Minus
x.
e lambda or whatever the stuff
Okay.
is.
So
Yeah.
we want to get f of x is equal to, let's see, 1 minus e to the power of minus lambda x, and because because this is f of x and like a percentile or
Okay.
or like a chance comes out of here, and we want 0.5 here, so we have 0.5.
Okay, I
equal
might
to-
sound stupid for a second, but wouldn't the median and the expectation be the same?
No.
No.
It
They
depends
are
on your
in
distribution, but
normal
generally no.
distributions.
The median
Normal
isn't,
distributions they are,
median
that's
isn't, is like basically,
I mean,
a
they
mean is
could be
something
the
like
same,
a
but they
weight
won't.
median, yeah.
Yeah, it doesn't have to be.
In
It
standard,
can be the same. Like
yeah,
for uniform distribution, I think the
or
median
normal
is
distribution. Yeah.
yes, all the number. Yeah, but it's not
Uniform
necessary.
definition, of course, because like, bruh.
It's like
Yeah.
if you have the graph, the median is where like is like the average, but like the mean is literally just the half line, where half the data is at the y-axis, basically.
All
They
right.
should be
The
the same,
mean, the
but
highest point
probably
in the
not.
graph.
Yeah, no, the mean not for exponential distribution because
So wait,
Yeah.
we are
Okay,
okay.
never
Yeah,
mind.
what we're looking for now is to express x in a way of lambda. So we have 1 minus e to the power of minus lambda x. So then we have I subtract 0.5 from both sides and I divide by the minus sign. So that when we have this minus lambda x. Then I will take the ln on both sides. I will also divide by -1 here is equal to lambda x. So then we have x is equal to negative ln of 0.5 times the lambda.
Yeah.
No, that's not true.
Why not?
over lambda. Divided
Yeah,
by
exactly.
lambda.
Yeah,
That's the
divided by. Oops, into
Yeah.
the divisions.
So this is
Yeah.
my answer.
Yes.
Yeah, and we did it before, and then our answer also looked something
Yeah.
like this. So
Yeah.
let's go. Oh,
That was easy.
No, that was pretty straightforward.
yeah, no. As we say in Dutch, die stoppen we in het zakje. Oh yeah, I think I clicked to exercise more. Oh no.
Oh no.
No, how do I get out of there?
Just put the
Actually,
same thing
scroll
again.
up,
Just
scroll
copy
up,
and paste
scroll
it
up.
again, paste it again, paste it again.
I'll do
Let's
that.
go!
Practice
Okay, so,
Let's go. Don't just practice one.
dude, we are like so good at this. Okay,
know,
so
right?
yeah,
We
here
almost
here
finished the
they
first
are
lecture.
like practice. Okay, yeah, practice and then basics.
Oh, that's a challenging.
Wait,
Oh,
this
we
was
already
challenge-
did. That was the challenging question. That was a challenging question. What?
What? Okay.
It's the same thing we did before. Just what I realized. This
Okay,
concept.
so what is the height of this bin? Oh, and this is the capital F. So yeah, okay, what this makes sense. So this is the distribution function, and we want the density function. I'm not sure if I'm using the right word. Probably not. Don't assume.
I don't think that's exactly what they're asking for. They're just asking for the height of the bin. Not
Yeah,
for
I
the
know.
Not for the density function.
Yeah, I
it's
know. I'm not,
literally just yeah.
Yeah, just read it off.
uh,
Exclusive 8 though.
so wait, it's the height of the bin. Yeah, no, but this thing
yeah.
goes to 1.
It's
So
it's
I need to
Oh,
take
it's basically
yeah, okay.
this one minus that one.
Yeah.
Yeah, this
exactly.
one times 3. Times 3.
Is it times 3
Because-
though? Because
Wait, what are you
Because
doing?
for the empirical
yeah.
distribution function, it's divided by 3. So it's divided by
Isn't
the.
it
yeah.
11 minus 8? Like
Yeah,
the value
11 minus
of
8
11
is
minus
3.
the value of 8? No. Oh, never
No,
mind.
it's 11 minus 3 because it's exclusive.
Yeah.
Yeah, that should be it. Huh?
I've been speaking for like 5 minutes. No one heard me. That's great.
Whoops.
Always fun that, isn't
Maybe
it?
0.07 times 13?
13?
No, or times 11 maybe. I'm not sure. So
Yeah, now we're
no, because it's divided by n for the thing. So I'm actually not sure. I did this before. Why can't I remember?
So it's
Uh,
I did
Will just be-
0.07.
Wasn't it
that was-
divided by 3 instead of times 3?
Yeah, isn't it divided by 3?
There
Because you
we
want to have the same
Yeah, you
area.
divide by 3 because
The area
bigger
of the
area.
histogram bin.
See, that's what I was saying when I was. That's what I was saying when I was muted. That's useful.
We can still get green if we get everything else right.
To be fair, I can appreciate this question. This is a good question
Yeah.
because this formula is going to be a bit.
Piece of the formula that 1 we gave you completely before, and 2 you had to use before that.
True though. True.
And this is the sample variance, and the standard deviation is the square root of this.
Yeah.
The most sensitive is going to be the mean, because the median is actually the middle data point, and the mean is actually the average. So if you have like 1, 1, 1, 2, 2, 3, and 1,000, then the mean is going to be a lot higher, and the median is just going to be like 3.
True.
I love like when I give a little speech on why I think I'm right, and then I get it wrong.
0.0713.
0.07
Gives us hope.
So again, like the height of the histogram, or the height of the bin of a histogram, is given by the chance divided by the width. Then.
Yeah, because like if you think about it, the histogram, the area of the entire histogram has to add up to 1. So like the histogram is a bit like a probability density function in the sense that the area of the histogram gives you the probability. So if you know that 0.07% are between 8 and 11, then if the histogram is 3 wide, then you have to divide that by 3 so that the rectangle has the area that's equal to the probability. At least that's how I think about it.
Yeah. I mean, honestly, that makes sense. Next subject. Random samples of statistical models. Okay. According to law of large number, when n is large, the average of a bunch of random samples approximates the mean. Not the median, the mean.
Or the
if you're tired of typing LaTeX for Greek letters, just do what I do and switch your keyboard to Greek.
Base. Consider the following description. A collection of independent random variables, all of the same probability density function, is a random sample. That's like per definition. Another measure of variability in addition to the sample variance and standard deviation is the MAD. It's the... I'm 100% certain that it's not the mode. Because the mode is absolutely irrelevant to like anything statistical. Okay, not really, but wait, what is the mode again? The thing that happens most often?
The mode is
the mode
it's the
value with the
value
highest
which
frequency.
happens the most.
Yeah.
Which I think we've never covered in the entirety
I
of this
think
course.
it's the... So
What
the variance
because
is
the median is not affected by variability.
Yeah. Yeah, it's the mean of absolute deviations.
Yeah.
Oh? No,
What do you mean?
Oh, wait. Yeah.
Wait, why? Huh.
It's just a thing we have to know for some reason.
Okay, fair.
They're describing standard deviation is the mean of absolute variability, and here they're describing the MAD, which is the median of that. So
Why are they fucking giving me this one again? I already did this one and I had it right.
They said they like to do that.
What a nerd. Back to lessons. I just don't trust
No
this shit
green
anymore. I think
percent.
okay, yeah.
We're not going to do a full green run.
No.
Yeah.
Truly sad.
So the sample mean is this. What should be the expectation of this distribution? So this is the average of 200 different rolls is 25. So then the expectation would also be 25.
I mean, okay, yeah, depends on what kind of experiment you do, but 200 can be a large sample size. But it can also be a very small sample size.
Yeah.
Depends on the context.
Well, I mean, like in general, if you just have something where the deviation is like relatively small,
Yeah.
or
yeah.
yeah. So this is, I think this would be like relatively good.
Yeah.
Let's see, what's the sample statistic can be used to approximate the expectation? Not this one, not this one. So yeah, we just want to approximate the explanation. That's just sample mean. Yeah, this one's just, you know, we get a bunch of numbers. We take the average. That's likely to be the average of what we do. Like for example, if I have 100 d6s, which I actually do, and I throw all of them and I just add the number, divide by the total amount of dings, I will get approximately 3.5, which is the expectation of a uniformly distributed 1 to 6.
I can assure you, if you have
that is the only
roll those
acceptable
for
number
damage, you're gonna get like.
Yeah.
If you actually roll those for damage, I can assure you, you're not getting higher than 150.
Yeah.
Consider the following concept. So we have the sample variance and the variance itself.
The way it feels, I don't think a 20-sided dice has a 1 in 20 chance to land on 20. Feels more like 1 in 100.
That's just like a psychological thing then.
Yeah, I know, but still.
So let's see. We are looking at the distribution feature. The sample variance is actually not a feature of a distribution, but a feature of a random sample, where the variance itself is actually a feature of the distribution used to generate our sample. So it's going to be the variance.
Let's go.
Let's go. One more.
One more.
I thought it would take like 2 hours, but
one more.
Okay.
It's also the longest one, so shouldn't we do that?
Let's see.
Why are there so many people joining today?
Because nobody fucking understands this.
Nobody understands this.
I mean, at least 2 of them have like literally deafened themselves, so they're kind of just vibing.
We don't even know what we're doing in life.
Okay, so we have the exponential distribution, and this is a which kind of graph? So this is the f of n. So this is equal to the capital F. Where is it? So this is what we're. Is that true? Yeah. So this is what they are. They're working with.
So we know the mean is ln2 over lambda. So ln2 over lambda should collide at 0.5 in the y-axis, basically.
That
would then we can calculate lambda.
So it's ln2 over lambda, but lambda, like, you know, depending on what we want. You know, for example, if we want the median, we can set lambda to be 0.5. So then we have ln of 2 over 0.5,
which is approximately 1. Sorry, not that.
No, it's 4.
It's 1.3.
Also, it's not 1. It's like.
Wait, what are you doing 0.5? We said it was minus ln of a half divided by lambda. But lambda is what we're looking for.
So this is 1 over 2, which is 2 to the power of minus 1. You can get the minus sign out. So this is practically just ln of 2. And then you divide that by a half, which is apparently like 1.4-ish. And the average here is at approximately 1.
A bit more like 0.75 or something.
I would approximate that to 1.
Yeah, I'm gonna be honest. Like they will most likely ask for a whole number, and it's not going to be 2, and it's not going to be 0. So it's going.
So just put ln2. Ln2 should be the answer. Yeah. Oh, okay.
What the fuck?
What the fuck? What whole number? You know, just ln2.
Rounding. True. True, but that's some next level rounding. Holy shit.
Based. The data shown in the empirical distribution function corresponding to the data set containing 200 data points. The graph is approximated from a. Well, we can see that the average here is approximately 5. So, again, it is n of mean, comma, variance. And we know that, what is it, 65% is within one standard deviation from the average?
Yeah, so we can approximate that to be like
1.
Yeah.
It's pretty narrow.
Yeah. So, like, when we have 5, the only options are 5 and 0, or 5 and 1. And we know it's not going to be 5, because then the graph will be, like, way wider.
Yeah.
So it's just going to be n of 5 and 1.
Yeah.
The graph
I'm gonna
shows
show
kernel
you.
density
In the
estimate.
actual exam, it'll be 5.1, 5.2, 5.3.
Yeah, I will cry. I mean, to be fair, with, like, the thing that you can get one standard deviation away, you'll have approximately 65% of the thing. You can get pretty far with that. It's not ideal, but it's something.
Sure.
Alright, so we have the kernel density estimate corresponding to the data set containing 200 data points. The graph is generated from an exponential distribution where numbers should be on the position of the question mark. What the fuck is the kernel density estimate? Is it just like...
It's
like an approximation for the probability density
It's
function.
a histogram, but with points instead of bars.
Okay,
Yeah.
Isn't kernel density the one with the sand? Like that basically looks
Yeah,
like,
it's the sand one.
Yeah.
It's like a statistical approximation of the density function.
Yeah.
It's a histogram.
I love how you guys keep talking about the sand one. I have no fucking clue what you're on about.
Because sand kernels,
that's the example.
they're metaphorizing.
Oh, okay, so they had like they had an example or a metaphor for it. Cool.
Yeah. Well,
And
like,
the
think
graph
of
generated
every,
through an
like...
exponential distribution. So this is the exponential distribution that we should be looking at, like this one. So that makes sense. Now the thing is, this gives us some pretty clear clues. If we go to this
it's at 0. Yeah.
Yeah, exactly. So if we fill this in, that's, oh god. So then we have lambda e to the power of minus lambda x.
But we have a point where x is 0, so we can use that point where it's just lambda.
Yeah, exactly. So when we fill that in, we
Which
get
is where,
lambda,
yeah.
which is approximately
0.33.
0.33. So that's 1 over 3.
Yeah.
God, I'm good. Okay. Okay. So we have... Yeah, so we have a box plot with the average at 0. It is very fucking symmetrical, so this is going to be a normal distribution. The average is 0, so it's either n01 or n04. But because, let's see if I can enlarge this. I'll open into a new tab.
Bigger.
Because there's like
Bigger.
a bunch of numbers, like there's outliers all the way up here. This is like what, 1.6 or something?
Yeah.
And let's see, from the middle onwards,
And 0.25, if I remember correctly, was something like 1.96 or something like that. So, for the normal standard normal distribution, so
yeah,
the
I don't
zero
think it's going to be
distribution,
this one, because then it would be way more spread out. Like,
Yeah.
almost everything is within these, like, what is it, 1.5 apart from 0. So it's most likely going to be this one. Cool. Oh wait, yeah, no, I'm dumb. 4 is the square of the standard deviation, and the standard deviation is what you take. So, yeah, it's approximately 2 away, which makes sense, right?
One thing to note here is this one looks a lot like a uniform distribution, but if you have the outliers points, then it's not a uniform distribution but a normal distribution.
Yeah, because the uniform distribution only has numbers between.
Yeah.
Actually,
but also uniform distribution.
A uniform distribution would technically have outliers.
Not really.
No.
The chance of it, like if you have uniform distribution between, for example, here -2 and 2, there is no points in the entire thing that will be away from 0. Like,
And
of course,
also,
if you
like the
if you have a
quartiles would be the quartiles would exactly be at 0.25 and 0.75 of the thing. So the area within the box would be the same as the area outside the box, which makes, and that means that 1.5 times outside the distribution is outside the data set that is like most likely.
Oh,
So
yeah,
there
yeah.
might be outliers, but they're super fucking unlikely.
yeah, but even then, like, if we have, you can't get anything outside of the parameters. So, like, if it was something like this, then it would be a, like, what is it, -6 to +6 uniform distribution, and that just doesn't seem logical. Like, with how densely everything is populated around 0, I very much doubt it will be a -6 uniform distribution. Okay. So again, this is a normal distribution. Well, okay, fuck, that's given. Okay. The average is 0, so it's n 0, comma something. So let's see. We know just to put just actually use this fact for once. 65% is away is like one standard deviation from the middle. That is like, is that two-sided? So is that like the mean plus or minus standard deviation? Everything within that has a, okay.
And I think it's 62.5 to be exact.
Is it?
That's just approximate
I
65.
think so, yeah.
Okay.
And tasks like this, you don't have to
I
be too
approximate
exact.
it to 50% whenever I'm eyeballing things. So.
Okay, fair. So we have this part, and then it's like 60% of the points should be within one of these standard deviations above and one of the standard deviation below. So
0.2.
Yeah, I guess that's like 2. Yeah, I guess that's like -2 to 2. So I guess that would be 0,41.
Yeah,
that sounds about right.
and this is too wide for 0.1.
Yeah, yeah, and the fact that like
Definitely too wide.
you can definitely like if we, hey, copy image, paint. You know, if once you start opening paint, you know it's gonna be good. So
Oh yes, all the
oh god, that's such a blurry fucking image. So the two
Perfect
choices
straight
here
line.
were either this one, that 60% of the points was in between here, which you know makes sense to me, or that 60% of the points were in this tiny area, and yeah, you can just tell that this is just not 60%. Oh, theoretically, wouldn't we be able? Yeah, we would be, because it's a fucking density function. Why am I doing so like so hard? So you can just literally see about 65% if I actually draw my line skid is between this. Yeah, okay, you can literally see that the standard deviation here would be 2 and the variant would be 4. Does what I just drew make sense for you guys? Because I'm not getting any feedback.
For me, it does. This is a really simple way of looking at it. Why the fuck did I not think about this?
Yeah, I thought it was like, oh, cool.
Thought about it. Like, what the fuck?
Hmm?
I never thought about it like that. It makes so much sense now.
Yeah.
This is such an easy way to do this.
Yeah, no, I was looking at that, I was drawing the lines of like, about 60% is within here, yeah, I guess. And then I looked at the left side, I was like, wait, we have the numbers. We can literally just draw lines. Okay, cool.
Yeah.
If they ask this question on the exam, I'm definitely just grabbing a couple pens and laying them on my monitor.
Yeah, for sure.
See how pissed the proxering thing gets. What the fuck are you doing?
The data shown in empirical distribution corresponds to a data set containing 200 data points. This is not an exponential distribution, let me tell you that much. And it's a normal distribution. Fuck.
Are you sure about that? Are you sure that it's
That's a
not
normal
exponential?
distribution with
0.1, yeah.
Yeah, it's 0.1. It's definitely not fucking 0.
Yeah.
Wait,
Yeah.
guys,
way too narrow for 6.
It looks a bit too narrow to be.
Guys, no, don't worry,
not
don't worry.
be one.
It's actually a 0.6 one, because if we take square root of 6, that's 1 point something. So you know, this is this is about 60%, right? Right, guys, right?
right?
About 60%, give or take, give or take.
Give or take.
A bit more, but less maybe.
Yeah, you know, I'm very good at eyeballing, guys. You don't understand.
I think it's actually closer to like 50%. We need a bit more.
Actually, I'm so bad at maths because I was like, yeah, you know, the square root of 6 is like 1 and a bit. The square root of 2 is fucking 4.
Bro.
So it's about this. This is about 60%, right, guys?
That's about 60%.
About 60%.
Yeah,
I'd say it's closer
60
to like
plus
50.
or minus 35.
By the way, I just want to say we're drawing lines, deducing numbers, and they're like, yeah, most of it is around this part, so it's probably 1. No, no. Fuck you guys.
This is
There we go.
accurate you can get with purely
Let's
eyeballing
go!
things.
Let's go!
Do we want to do lecture 10 before going to lunch? Probably. Like. Just
Actually, I
keep
think
the ball
lunch
rolling.
might be a good idea.
Yeah.
Because I'm pretty hungry.
Again, why are we so good at timing it that like for some reason lunch is always at either the exact
Well,
same
because
time
we
or
have like
it's
an
at 2
hour
minutes?
interval where we can stop, so it's like somewhere between
No,
12
I mean,
and
like,
1.
always at like 12:45ish.
Lunch until 13. Fuck. It's just wait no. Haha. Okay. See you guys in a bit.
That is a very speedy lunch.
Have a good lunch.
Adios.
One thing.
Okay, so Pathfinder one shot. Gone.
Yes. You want to do this here? Sure, dude. Okay.
I'm thinking 3 sessions.
Okay.
And your hint for the theme is 2011 Justin Timberlake.
Sure.
Have you any clue what I'm referencing?
Absolutely not.
Excellent.
I mean, I do know the name Justin Timberlake, and this year rings something. But you know.
I think it might be a good one. I think it will work well. Hopefully.
Should I come prepared for danger? Because we're talking Pathfinder here. So
Well,
if
I'm thinking of making this 50-50 roleplay danger level. Like, I'm definitely not taking the entire story from somewhere else.
That's not what I'm saying. What I'm saying is, should I make my character OP? Because I can.
Probably
Like,
not.
You
I
have
haven't
idea.
even decided the context and levels and stuff. I haven't even gotten started. I just had the idea. I'm giving myself like a month to do all this.
Okay. I'll send you resources if you need them.
Right.
Well, like honestly, the worst part about this course isn't how like terrible the organization is, or like it's not just the organization for like how they teach it, but rather just the fact that it's an interesting fucking course. Like statistics and probability is fucking interesting. You can do a load of shit with it, and it's super nice, but it just fucking ruins it. Like the concepts are legitimately so fucking cool, and it's like the basis of so much analysis. Is anybody else in like Delft right now and doesn't get any Wi-Fi?
Well, based on the fact
I'm
that
in
we're
Delft.
talking, clearly
Plus,
you have
you're on
I
some.
mean,
Discord. You do realize that.
you do you do know that like hotspots exist and like mobile data is also a thing.
True.
True. But I wouldn't
Which is
expect
what I'm
people.
doing.
I wouldn't expect people to be using that to.
Honestly,
No, to be on
to
Discord,
watch
no,
a
I wouldn't
Yoda
be
lecture.
surprised.
I mean, I'm doing it.
Fair enough.
It's so weird because like for the apparently like since Friday, there's a bunch of like places in Delft, The Hague, and so forth that are like from like Ziggo and like with Duo that the internet is just fucking dying. And like I just hope they fucking fix this shit until Friday. Because if it fucking dies halfway through a Grasple exam, you're literally fucked.
Oh man, that would be terrifying.
Like they're literally just gonna disqualify you. There's nothing you can do.
Ah, yes, chess.
Yes. Chess.
With a particular theming.
I'm in a very bad situation right now. Still doable. Still doable. I just need to get that game. Fuck, I should have moved that. Well, it's too bad. Oh, I lost. Well, too bad, I guess. Oh god. Okay.
is this?
This is Chess Evolved,
Uh-huh.
which is basically chess, but you got extra pieces that can do different things.
Chess 2?
Chess 2, I'm not sure I'd call it that, but...
Chess is that great, why isn't there chess 2?
Yeah, it's been like 400 years since the last time.
Oh yeah, Conrad.
Yeah,
Conrad.
yeah. But I mean,
Yeah.
this is from the modding community. Like, it's
Conrad.
pretty active.
Yeah.
What do you know of 2011 Justin Timberlake?
Nothing.
Excellent.
I was 9, like, what am I supposed to know?
He was popular then.
Yeah, I remember hearing his name and stuff, but like, I was connected with it with shoes because
2011 JD.
yeah.
He made that one song and then
Yeah, the one that everyone seems to love, but I just fucking hate because it's not a good song. I hate it. It's bad. Why does everyone love it?
Which one?
The one that was like he didn't like. I think 2014
Are you thinking of
or
Mirrors?
2016. I think.
Are you thinking of Mirrors?
No,
Cooler.
this one I think like dance something. I don't know. I don't know the name. I hate it. I don't want to listen to it ever again. But I'm forced to constantly.
That sounds like
I'm gonna make sure during the entire one shot, the only music will be Justin Timberlake.
You know, I can just mute the music.
I will make the music be a part of the game. You'll have to play with the music.
I can just mute the game.
Then are you playing my one shot?
Well, at this point, should we be playing a one shot?
Yeah.
What is the red and the blue square?
Sorry? Red squares are squares that my enemy can attack, and blue squares are squares that I can attack.
But, trust me, you'll see what I mean when I say 2011 Justin Timberlake.
I probably won't because.
Okay, have you heard of the movie In Time?
Yeah.
Heard of it, yes.
Have you seen it?
No, but I know the entire thing.
Okay, do not watch it.
I know the premises. Oh, it's, we just did she reenacting In Time.
Yeah, I'm gonna take the system at least from it. Of time as currency.
Oh, that movie.
Yeah.
Never mind, I don't want to watch it.
I wasn't talking about you anyway, so that's fine.
Good.
It's like.
Samurai. Why are there two timers?
There's one timer and one timer. Oh, right. Because you have the first 30 seconds for each move, and if you go over 30 seconds, you gnaw into your actual timer.
Ah.
Yeah, and I won. And killing the king does not win you the game instantly, but it reduces the enemy's point to so low that they're gonna die.
Yeah, isn't that also the rules of normal chess? Like different pieces have different scores and stuff.
So basically, every piece has a value, and
checkmate only ends the game and gives you tons of points, but it doesn't mean you win.
Like basically, every piece has a value. So like this one has a value of 4.
Can you change
The king as a value, well, doesn't cost anything to put in your army because it's automatic. You can't play without king.
Yeah. Like for example, if you have one rook left, or like and the other person has like almost all the pieces left, and somehow managed to get a checkmate, you still won't win because the other person has all the points.
Basically, the way it works is that when you play, so let me just start up again. You start with points equivalent to your army's value, and say you lose a piece. So I'm just gonna send this dude to his death. This dude has a value of 5. Right? So kill it. He has a value of 5. So if the enemy takes it, which is he's definitely gonna do, I lose 5 points. When you lose the king, you lose 25 points, and the king does not count within the value. It doesn't give you any point. I think you have the starting. No, the king doesn't give you any point on your HP total. So you actually lose before you lose all your pieces. And so different pieces promote to different things. Like if I do that, but I just like 2 human players, whatever. So say this one, for example, that's a bat. It has weird movement. So the bat moves. It can move like a horse, but not attack. It can move sideways, and it can only attack backwards. So say this one moves forward. The bat can attack like this. The bat actually has like every piece has different stuff. Like you have this one, for example, which has night movement, and then can set up an explosion in 6 turns. In 6 turns, you'd be surprised how often 6 turns, like how fast 6 turns actually go. So like the bat promotes to a vampire, which can basically just attack every fucking where because it's a vampire.
Oh, okay.
But yeah, like the pawns automatically promotes to bishop. So what the explosion does also is it pushes every character that's next to it one spot, which can be useful for terrain control. Then you've got abilities such as like.
And where does it push them if they can't be pushed anywhere?
No, they just stay where they are. You have this one, for example, which has the ability to defend from one attack and then lose the ability. Like these ones, for example, have ranged attacks, so literally they don't move when they attack. This one allows to TP your pieces around. Like it's stupid. There's a bunch of stuff. And then you can have like, this is a pawn plus, so he can move 2 forward if he wants.
Oh my god.
Yeah, sure. There, and promotes to.
This truly is the Dark Souls of chess.
Wait,
this is the modding community. You have 2 ways the modding community go. You have one way which is more pieces that do bullshit, and you have the second way which is 5D chess with multiple time travel.
Chess is so much better than this.
Guys,
oh yeah, 4D chess is so fucking cool.
Guys, I have an announcement to make. My TU Delft programmer shocked came in.
Yeah, mine are Delft.
I really like them, unironically. They're not the thickest, but they're pretty cool.
You know what? I think we need to wear them to actually effectively study for this. I'm gonna go.
Everybody, if you got them already, go put them on. They will help you understand material better.
Let's see, the Queen's worth 21, and he's got 16 left. Die before you're out of pieces. Die if you're gone. Anyway, stupid. Let's get back to study people.
I don't study people, people study.
Yeah. I mean, theoretically we have a minute, right?
I mean, that's not enough time for me to play a bullshit game of chess.
That's enough time for some things, but not for chess.
Actually, bullet chess is terrifying.
I know.
Yeah.
I hate it.
Like, if you've actually ever played bullet chess with someone who knows what they're doing, oh my god.
What is bullet chess?
It's chess with a timer of 1 minute.
Hyper bullet, it's 15 seconds.
Hyper bullet is ridiculous, dude. Like, you have to understand, in like grand championships of chess, it's considered difficult to have games with 40 minutes as a timer.
Yeah.
per move, not for the whole, per move. Like, chess is ridiculous.
Okay, boys.
All right, it's 13 o'clock, so we are continuing.
Programmer socks on.
Good. Okay, lecture 10. Let's check out what it's all about. Let's see.
All
lecture 10.
about that base. About that base.
Oh no. So we have the we have estimators and the most square most significant. I don't fucking know.
Least squares law.
Well, I would think least square, but MSE is what is something else.
Oh, mean squared error.
Mean squared error. Thank you. Let's see. So
Isn't that like something similar to variance though? Because like
Yeah, it's variance, but for a
sample. It's just sample
yes.
variance.
The slow regard of silent things just arrived.
all right. So suppose D is an estimator with parameter lambda with expectation this thing with the following statements. So if we want an unbiased estimator, we want the expectation to be equal to the parameter. So in this case, we have ES is equal to 1/2 times D minus 1/2. Filling in T gives wait, what's that one again? No.
Theta. THETA.
Thank you very much.
Again, just have a Greek keyboard.
And beta.
You do realize that for Greek keyboard, you actually need to know where it is, right?
Yeah, it's at U. For an English keyboard, it's at U.
Yeah. So basically, we want if we have an unbiased estimator, we get that the expectation of the estimator is equal to equal to the parameter.
Technically, because we only give them S, ES is a half ET minus 1.5 because
yeah,
of the
my
way
bad.
expectations work. But like, that's
Yeah, I see.
like,
That's my bad.
calculative, that doesn't really make that much of a difference.
Yeah, you're right. Or actually, I could put another intermediate step. It's the expectation of 1/2t minus 1/2, and then we can apply the change of units formula to get this. Yes.
Yep.
No,
Yep, there we go. Now it indeed is a lot more correct. Let's see. So we have an error containing blah blah blah. Okay, fuck that. A real value t that only depends on the
But
data set.
be like drawing balls, am I right?
Ha! Furry artist. A real value t that only depends on the data set. So that's like, yeah, t is a heuristic of the data set. And that is used to estimate a fixed unknown parameter lambda. It's called an estimate of lambda. And then t is a random is a realization of a random value variable, which we call the estimator. So we have the estimator of t, which is a heuristic provided on some random variable, and then when you realize that, then you get a number out of that, which is your estimate. So let this be an estimator based on a random sample. Probability distribution called a sampling distribution of t. Okay. Unbiased estimator for mean and variance. So we have a sample from a distribution with a finite expectation and a finite variance. So this will be the model distribution. Then the average is equal to, all the sum divided by n, and the variance is, the formula we did before, which is again the standard deviation squared. Yeah, and they're unbiased estimators, which makes sense. Oh, hey, they actually explain why. Wow,
Oh, damn.
this is fucking luxurious, guys. I know we were complaining before, but damn. So, the estimator may
It's
seem.
just a bit late.
Yeah, okay, true. It is pretty late. Maybe they expect us to do like to read all the lectures first and then do all the exercises or some shit. Or it's like in a different order than it used to be a few years before or whatever. Yeah, either way, it may seem more natural to estimate, but it's biased. Okay, so it's literally just the fact. Okay, this one is biased, sucks, but. Okay.
It's just a correction.
Yeah, it's just the way it is, and yeah, okay. I can live with that. The fact that now that I have a reasoning why it's n-1. Like I don't understand the exact computation, but like now I can say, oh, it's n-1 because just n would be biased. Okay, cool. And let's see next one. Mean squared error is the estimator of the is the estimate, not the estimate, the expectation of the squares of the errors of the estimator. That's a lot of words.
Yep.
And it's also a formula that you're never going to use.
Hmm?
And it's also a formula that you're never going to use because you're more likely to use the second one. It's easier to get the variance out of it and then see if it's biased or not.
Yeah, fair. Okay, that makes sense. So, yeah, but like it is pretty important to like be able to look at it like, okay, the mean squared error is the expectation, so the average mean of the square of the error, which it's literally the fucking name, but whatever. If we have two estimators and the mean squared error is so if the mean squared error is smaller, then it's more efficient. Makes sense, because if you have a smaller error, it's better. And then if you have two unbiased estimators with the same parameter, then the variances also work. Yeah, but that makes sense, right? Because if it's unbiased, then this expectation is equal to this parameter. So then the mean squared error is just literally equal to the variance, and then you can just replace the mean squared error with the variance here.
Exactly.
Yeah, cool. Okay. The series. Huh. Yeah, okay, makes sense. So, unbiased estimators might not. Yeah, like they don't have to be like symmetric or anything like that. So this one is unbiased, but it's arguably probably worse than this one because it's a uniformly distributed. That's fair. I guess that you can. Yeah, I guess you could check that with these formulas as well. So this one is the thing divided by 3n, and this one is divided by n squared plus 2n. And that is obviously, this one grows a lot bigger. So the variance of this one is smaller, therefore this one is more efficient. Yes, okay, cool. Let's see. If the variance of S is less than the variance of T, then S is more efficient than T. Wrong, this is only the case for unbiased estimators. Because otherwise you're forgetting about that, that opening brackets expectation of T minus thing closing bracket squared. And if S is unbiased, T is biased, then always variance of S is less than variance of T. No. Like.
Yeah, it just doesn't make any sense.
Yeah, no, that doesn't make any sense. It just, comes from the fucking. Yeah, it just falls out of the sky. That's it? Huh! Okay. I was looking up a lot more towards this thing, but apparently it's not that bad. An estimator unbiased if the expectation is equal to equal to the parameter. Suppose you're giving the following ordered data sets. Compute the average of the data set. So, can I copy this? Ugh. This probably takes more effort than actually doing it, but I don't care. Is there an average function? No. Sum divided by len. Hey, it's 4.5.
Wait, really? There is no average?
I'm not sure, but I don't think so. Because it's just such a simple computation.
Yeah, you could just
Wow.
Yeah,
you could just
I
implement
could just say def average
Yeah, you
x
barely save any time.
return sum x divided by len x. Now there is.
Nice.
Yep. Probably could have made a lot for that as well. Suppose you have collected the following data sets and you would like to estimate t is the realization, then the random variable is the estimator, the t is the estimate. Yeah, and it's not both. That doesn't make any fucking sense.
It's like the Holy Trinity. It's more than one thing at once.
Suppose it's an estimator for the parameter and it has the following property: the expectation minus the thing is bigger than 0. Obviously, it's fucking biased, like, because if you add 0 on both sides, that means the expectation is bigger than this thing, but the only way it's unbiased is if they're equal. So, in case this says greater than or equal to, we couldn't have said that for sure, but because it's greater than and there's no way they're equal, we can say that they're biased. SN squared, so the standard deviation squared is an unbiased estimator for the standard deviation squared. This is, by the way, not the actual standard deviation squared. This is this is an estimator for. Yeah, that was kind of bad of me explained. My bad, but yeah. Next one, next subject, practice questions. Okay, what's the bias of
Isn't it just 3/2?
Yeah.
Yeah.
I was just confused because they gave us like the other one as well. I'm like, what?
Yeah, T1 is unbiased.
Yeah, exactly. And the estimator T is an estimator for the parameter. Is a biased, unbiased estimator because you know. Yeah, literally definition. You're giving the following for our parameter is this sample from blah blah blah. An unbiased estimator. The expectation, standard deviation, the variance. Well, this is obviously just the expectation because it's just the average. Suppose you're giving the following formula that we already know. This is an unbiased estimator for the variance. If we wanted to get the standard deviation, we can take the square root of all this. Next subject. Challenging questions. Ooh. Alright, well, so this is a Bernoulli distribution. I think they've given that this is an this is always an unbiased thing, no matter what your distribution is, right? So I would just say unbiased.
Yeah, with a sufficiently large sample size.
Yeah.
Which is implied by
upper limit. It's not necessarily.
I think it's unbiased nonetheless.
Yeah. No matter like how big your sample size, even with a sample size of 2, it is just an unbiased estimator. It's just not going to be a very good estimate.
Yeah.
True.
And then we have the other one, which is the minimum of these things. That sounds biased as fuck to me. Like you just roll 6 die, and you're like, wait, okay. To be fair, now that I think about it, I didn't even look at the fucking Bernoulli thing. Okay, yeah, but thinking about it logically, the Bernoulli trial is just like either 1 or 0. But if you take the minimum of this, then you just either get 1 or 0, which is.
Yeah.
Yeah.
That's your die example still holds up. It's just a binary die.
Yeah, exactly. Like imagine just throwing. Imagine just flipping a coin 100 times and just seeing like, oh, I got like 50 ones and 50 zeros, but it had a 0, so the average is 0. What?
What?
Calculate the bias as an estimator for P. Ooh. Okay, so let's think about it, right? So the bias is the expectation. Let me actually write this in my own in my like thing where I can keep it. So we have the expectation of t is equal to theta plus b, with b being the bias, right? So then let's see, we can calculate, or I'm gonna give them subscript 2 because of t2. The thing is, how do we calculate the expectation of the minimum?
Well, just the lowest value of all of them. It literally just is the lowest
Well, I
value.
mean, realistically, we can look at this as a okay, so I'm going to think about this as a more high level than just a monkey filling in formulas level. So T2 has two options, namely T2 is 1 if literally all of them are 1, so that is p to the power of n, and 0 if 1 minus p to the power of n, right? Because we just any of the n variables is 1 with a chance of p. So if we want them all to be 1, it has to have a chance of p and p and p and p, so p times p times p times p, p to the power of n. And so
Yeah, but if
now
you're
we know what
calculating
this...
if you're calculating the expectation, then wouldn't that mean that you only have to take then p to the power of n? Because 0 times 1 minus p to the power of n
So
would be 0.
indeed, the expectation can be calculated using 1 times p to the power of n plus 0 times 1 minus p to the power of n, which is equal to p to the power of n. And by the way, the estimator, like we are estimating p, so I'm actually going to change this from theta to just p. How do we? How do we calculate the
Expectation
bias
of
for
p
this?
to the power of n. You just take the expectation of p to the power of n then, no? And then you see what you get, and then you're going to get p plus something.
Why would I take the, like, we already, this is already the expectation of T2. Do we take the expectation of that again? Why?
No, it's for the bias, we just need to take the expectation of the estimator minus theta. So in this case, that would be p to the power of n minus p.
Oh, wait,
Just
yeah, that makes sense, because,
formula.
like, if we have this bias, we can just get rid of
p
this
to
one
the
to
n
the other
minus
side.
p.
Yeah,
Yeah.
so it's basically the bias is the expectation minus p. So then we have p to the power of n minus p. Oh.
Oh.
Interesting. That was a good exercise. I like this exercise. Consider the random sample from blah blah blah. You want to determine which constant A or B. The estimator is unbiased for. This is the case when. Well, okay, this is a pretty obvious one.
Monkey brain.
Yeah, A is going to be 1. Because we know that an unbiased estimator for sigma squared is equal to 1 over n squared, 1 over 1 n minus 1 times the sum of the differences of the sum of the squares of the differences. So yeah, this is just going to be plus 0 with an A of 1. Oh, actually, oh, that's cool. So what do they do here? So it's
just a lot of extra
oh yeah,
steps.
okay. So they just take. Okay, yeah.
They actually calculate it.
Yeah, they basically take, okay. We take the estimate of it, both sides. We use the linearity formula. Then we get A times the expectation of this thing, which is sigma squared. And then we just have A times sigma squared plus B. I want to set that to sigma squared. Cool. So basically what we did, but then with a little bit more thought behind it, and we just kind of went intuitively. Okay, let's see. So we have... Shut the fuck up. We have xi is equal to yi plus. What is this letter?
What?
Delta.
Delta.
Yeah,
Cool.
delta.
Yeah, that's
So we have delta plus yi. Yi is distributed with an exponential thing. Mn is the minimum. You may use the fact that the expectation of that is this plus 1 over n times. Yeah, okay. What is an unbiased estimator for sigma that uses Mn and the average? Okay, so we want an unbiased estimator. So what that's saying is we want the expectation of t to be equal to delta. Let me see if it actually uses the right delta here then.
It's the lowercase one.
It does! I thought it would use like the weird triangle thingy.
It's uppercase delta.
That's uppercase.
Maybe if you change the D to an uppercase D, I think that's uppercase delta.
Huh, would it?
Yeah.
Damn! LaTeX is cool! Okay.
LaTeX can do lowercase and uppercase letters. There's nothing it can't do.
Yep.
Wow.
So this thing here is actually an approximator for the or an estimator for the average. But if we have this exponential function, okay, I'm going to write out what I'm trying to say. So we have this bar x n is equal to the fraction of the sum of x I over n. All right. However, it should be uppercase. However, we know that x I is actually equal to delta plus yi. So I'll say delta plus. Oh fuck! I did it on the wrong side. So it should be delta plus yi. However, what we have here is we have n times something over n. So we can actually get this delta out of the bracket, and this will just be delta plus the average of plus the average of y. Is there a so the average of this thing will actually be the expected value, and for the expected value of an exponential distribution, that's actually equal to 1 over lambda. So for the expected value, this is not exact, but for the expected value of this, we can get delta plus 1 over what's it called? Lambda. Okay, so now we have both of the formulas in a something that is at least more nice. So we want to get something in terms of this and this that is just equal to this. So
you don't want it to in terms of the expectation of Mn. You want to use Mn itself, I think.
Yeah, but because of linearity of expectations, we can just take these expectations and then align them in such a manner that the result is delta. Sorry, yeah, delta, yeah, delta.
I mean, wouldn't it just be...
Wait.
So for example, if you multiply the minimum by n, then you're going to have n delta plus 1 over lambda. And if you subtract xn, then you're going to have n minus 1 times delta, and then you've gotten rid of 1 over lambda.
Okay, I'm so confused.
So think of it this way. You have mn and you have xn, and you have to find some, like, expression with these two where the expectation will just be delta. But because of linearity of expectations, what you have to think of is like, what can I multiply by these expressions and then sum them together such that the end expression is delta.
Yeah. One of the annoying things here though is like both of these have a delta plus something. So
Well, I would first maybe get rid of 1 over lambda. See if you can do that. Because that's the one thing that we don't want in the expression. And then if you have to manipulate it in some other way to make it only delta.
Yeah,
then...
that's a good point. So we have this 1 over lambda. What if I say, okay, n times bar x n. So what this will do is this will be equal to, oh, that will not work. That will be equal to n times delta plus 1 over n lambda.
No, it's not. If you do
n
times
sorry,
bar
that should be
xn,
above
then
here.
it's n divided by lambda. Yeah.
Yeah. So, but we actually wanted to have it on the bottom. So I should actually, instead of saying n times, it should be divided by. Okay, and this will be delta over n as well. Okay, so this should be, yeah, that's correct. Okay, cool. Now we can subtract this from that. So then we have this original thing minus m of n. And so that is this thing on the left side here minus, or right side, and minus this thing on the left side. So then we will get is equal to I will actually copy that from here because it's easier. This thing minus opening bracket delta plus 1 over n times lambda closing bracket. But however, we can see that I hate when it does that. We can see that here we add and then we subtract the same thing. So we can basically say this is equal to fraction of 1 fraction of delta over n minus delta. And we just have to find a way to get only delta here, but that shouldn't be too hard. So if we take the leftmost and rightmost part here. Okay. Oh, I gotta get rid of an equal sign, so that's my bad. Wait, why is this one here? Yeah, no, I don't know why that bracketed there, my bad. So then we have this. Then I'm going to multiply everything by n, which will give me.
Or you could just pull out delta, and then you'll have a factor, and you can divide everything by.
Oh yeah, that's a good one actually. That's a good one. That also works. So here we have, because we have, yeah, okay. So I can say this is actually equal to delta over 1 minus n minus 1. Because, you know, this is just multiplication. And then we can say that delta is actually equal to
This is going to be a very pretty expression.
Yeah, this is a very pretty, amazing, graceful expression. And then we get this. I'm very tempted to just multiply top and bottom by n for neatness, but I mean, theoretically you don't have to. I'm just going to do that though. Okay, it gets rid of a lot of fractions. So then we end up with xn, so the average minus n times that estimator over 1 minus n is equal to this thing. Or well, we should say, because I have not been very exact, we should actually say that the expectation of this thing is equal to the parameter that we're trying to estimate. And this is our yeah, and this is our estimator t. So if I do it like this, oh, okay, I didn't mean to press enter there, but it worked.
Whoa. Okay. Right.
Nice. I like this.
Yeah, that was a really big computation, and I'm glad I got it right.
I don't understand any of it.
Yeah, so basically, what we were doing is, okay, do you understand it until this part?
All a
Can
bit.
you just like go through it from the beginning?
Yeah, sure, I will. So, what we do is we have this one. I'm going to start with this one. So this is just, you know, an unbiased estimator for the average.
Yeah, sure.
What do you mean?
Yep. However, this is currently in terms of x, x1, x2, x3, etc. And we want to bring it in terms of y, and we know that x is equal to sigma plus y. So we basically just substitute that in, right? That's this first step.
Yeah. Okay. Yeah.
Okay.
Yep.
Then here, what this practically does, and this I didn't completely finish the summation, but what the summation should say is I is 1 to n.
Yeah.
So basically, this sums x in this case y1 sums it up n times and then divides by n, but then just every time it's of course something different because it's a random sample.
Right. But
However, here this is a constant.
delta.
So we just
Right.
sum a constant up n times and then divide by n, we get the constant. So that's what we do here. So we get this constant plus the sum of y1, yi over n.
Mm-hmm.
However, we know that the sum of yi over n, this is just the expectation or the average of yi, or well, not yi, but y. Yeah, just the y in general. Well, I guess yi. And we know that this yi is distributed as an exponential function with parameter lambda, which we could look up to have an average or an expectation, say like that, of 1 over lambda.
Okay.
Oh. Yeah. Right.
Okay.
Yeah, then
So
we just
yeah, and once we have this, we just have one formula in terms of lambda and delta. We have another formula in terms of lambda and delta and n as well. And we want to get rid of the and we want to make something that basically only has delta here, which we do by just first subtracting them. Then we get that magically, or actually first we divide this one by n, which you know, it's literally just this one divided by n. Then we subtract one from another, which will give us this thing, and then from this we need to go into something in terms of delta, which we do by getting a 1 over n minus 1 out of the brackets and dividing by it. And then here I multiply by n to make it a little bit neater, but I should have done that in its own step. But yeah.
And there is just one tiny bit of hand waving. On the left-hand side, we say things like xn divided by n is equal to delta n and so forth. It's actually the expectation of that.
Yeah. So every time,
So
basically,
that's
what
the
I said on the left side, I should have written expectation of.
The expectation of, yeah.
Yeah, so I fixed that over here, but I didn't fix it on the rest of the line. So basically, the expectation of this thing, the expectation of this thing, the expectation of this thing, etc.
Yeah.
Because we can't say, if we could say the expectation of x is equal to lambda plus something, that would be really nice, because that would just mean that it's a uniform distribution with a constant. If it's always the same thing, you know, that would be really nice. It's a lot of fun to work with, but unfortunately not the case now.
Okay, that makes a bit more sense.
Okay.
Right.
And the good stop me. Like at any point if there are any questions, just please stop me, let me know, because I'm here to help you guys as well. Like I learn a lot from it as well, but you know, I also want to help you guys. Okay. Suppose T is an unbiased estimator, and the expectation of T is Huh? Oh, I guess it's an unbiased estimator for sigma squared, or I keep calling it sigma. But
Theta.
for
That's
theta squared.
No,
Wait.
it's not.
No, because it could be minus theta. Wait, no.
No, theta's
No,
not.
I don't think it's about that. It's just the fact that Jensen's inequality.
Yeah.
they're linear. You can't treat a square root as if it's like a multiplication or something. If you take this, the expectation of the square root of t is not equal to the square root of the expectation of t.
Yep.
It's actually larger, I think.
You can also think about it in terms, what they said, in terms of just the sample standard deviation and sample variance.
Yeah, so they give a good example here, because if you take like, if you use, like we know the formula for Sn squared, which is 1 over n minus 1 times the sum of the differences, etc. But if you just work with only the square root of that, that's biased. Whereas that's biased when you're estimating just sigma. But if you work with that square with the variance, then it's not biased, and that's what they say here. I didn't know that before this, but apparently it's true. So.
Yep. It's so confusing that we do 1 over n minus 1 for the sample standard deviation, even though it's still biased. But I'm going to go ahead and guess that it's maybe the maximum likelihood estimator.
Yeah. Let's see. Following is given. A random sample is given for which it's not known. We know that the expectation is mu. Yeah, makes sense. So m is the minimum of them. You can use that. This implies that m has an exponential n lambda distribution, for which c is t is equal to c of m, an unbiased estimator for lambda, for mu. A bunch of shit is said here, but nothing is actually really said. So I'm going to write this down in like more mathematical terms.
Yeah.
So what we want is the expectation of t.
T to be equal to mu.
We want it to be equal to mu. What that means is the expectation of Cm is equal to C times the expectation of M to be equal to mu. Because T is literally Cm.
Yeah.
And I'm going to try to actually stick to the proper way of writing this stuff with the expectation. So if I fuck up there, just let me know. However, we can say that the expectation, because M is exponentially distributed with an M lambda distribution, we can go here and we can say, okay, the expectation of, let me see. Yeah, the expectation of something with parameter lambda is 1 over lambda. So with parameter n lambda would be 1 over n lambda. So we can say C times the expectation of M, which is actually 1 over n times lambda, is equal to mu. That's what we want.
Yeah.
Let me see if I actually wrote that correctly. Yep. However, this mu is actually the
expectation.
Yeah, that's basically the expectation for one of these, which actually has this thing. So this mu, we can actually indeed replace this with the expectation of xi with one of them. It doesn't matter. So we know that all of them are from an exponential distribution with function lambda, or with parameter lambda, and we know that the expectation of that is 1 over lambda. So we know that this is actually equal to 1 over lambda. So this is the actual equation that we're trying to solve. What I'm going to do here is I'm going to divide by 1 over lambda. So that will just make this equal to c times 1 over n is equal to 1. And then when we multiply by n on both sides, we get c is equal to n. Yeah. When c is equal to n. There we go.
That sounds like a pretty overkill way of seeing that c divided by n lambda is equal to 1 over lambda when c is equal to n.
Yeah.
Complete mathematical rigor. I love it.
Yeah, no, it's you can't just say proof QED. You gotta put in some work.
Proof by dude, trust me.
Yep.
Proof by bro, it's fact.
Proof by I left it as an exercise to the reader.
Proof.
No, the best is gonna be proof by
intuitively
intimidation.
obvious.
Proof by bro, just look at it. So we have the variance of an
American
estimator
induction.
and mean squared error.
Proof
Okay,
by use
which
stupid.
estimator is more efficient?
Proof
we know
by why
if-
not.
Proof by this should be obvious, do it yourself.
So we have these two mean squared errors, and we know the one with less error is more efficient. Not a rigorous proof, but it sounds logical.
I mean, it makes sense, right?
Okay. Suppose there are two unbiased estimators for a parameter alpha, which are given the following. However, you cannot just say that with the variance. But because they're given to be unbiased, we can say that okay, the one with lower variance also has the lower mean squared error and is therefore more efficient. So the answer is T1. Suppose you would like to compute the mean squared error when the for the unbiased estimator, you're given the following. Okay, so the mean squared error is actually yeah, okay, so it's saying it's unbiased. Recall that the mean squared error is actually calculated in the following way. Mean squared error of t is equal to the variance of t plus the expectation plus, let's see, the expectation of t minus whatever you're trying to do. So in this case, it's theta squared. I already know this formula. This is so going to help me. So this is true. However, in the case of an unbiased estimator, we know that the expectation of t is actually equal to theta, which therefore just gives us is equal to the variance of t. And this is only true in the case of an unbiased estimator, but in this case it is given to be unbiased, so we can just fill in 5.2, press enter, and there we go.
Damn, we're so good.
Yeah, you guys are so good. Thank you guys for helping me so much.
Yeah, like honestly, I don't know how you could do this without my help.
Yeah. Same reasoning, unbiased estimator, variance is given, damn. Okay, holy shit. They just asked the same question 5 times. I wish they could do this on the exam. Given that I actually know the answer to the question. If they ask something 5 times and I don't know, I'm gonna cry. Wow, next subject. So this is practice.
It's like a Bernoulli distribution. You either fail or you pass. No in between.
Yeah, I mean, to be fair, if the grades were uniformly distributed, the pass rate would be 5.5 out of... it would be like... Passing is a random variable distributed with a Bernoulli distribution with a parameter 5.7 out of 10. Yeah, that would make sense. So this is a random sample from a Bernoulli distribution with a parameter p, where p is between 0 and 1. You know. Motherfucker, give us the definition of a Bernoulli distribution.
Thanks, guys.
Wow,
like we actually have something for that called the homework sheet.
Okay, so this is an estimator, and we want to calculate the mean squared error. Okay, that's good. So we have the MSE of A is equal to the variance of A minus the T of minus the expect. Is it minus or plus? I think it's plus.
Minus.
It's
minus.
Oh no, yeah, plus. No, you're right.
Plus.
Okay, there we go.
Plus,
So the
plus.
expectation of T minus sigma squared.
Because,
so this is just the definition of.
Like the lower it is, the best.
I
So
keep using
if
fucking
there's a
sigma. Okay.
difference- If there's a difference, it's like because you're squaring, it's always going to be positive. So if there's a difference, it's going to be a positive number. So you don't want to subtract because
Yeah,
if
okay, that
there's
would make
difference,
sense.
that means you're not as accurate. Therefore,
Yeah, so the better it is, the lower the second term will be, and therefore the higher the overall result will be.
The lower the second term, the lower the.
Oh yeah, that my bad. Yeah, because we're working with the error. The lower the second term, the lower the error, the better the result. That's what I meant.
Exactly.
Okay, so we have this estimator of p. This is just. I don't want to say it in a way that sounds like, dude, just trust me. But this is given to be an unbiased estimator for the expectation of a thing, and we know the expectation of a Bernoulli distribution is p. So therefore it's unbiased. Therefore we only need to calculate the variance. So this thing will fall away.
Yep.
So we need MSE of A is equal to variance of A. And we know that the variance of a Bernoulli distribution is actually equal to P times 1 minus P. So therefore, the MSA of A is P times
It's
1.
the variance. It's the variance of the average, not the variance of the individual one. Or is that equal?
Oh,
Wasn't
yeah,
the
you're
variance
right.
of an average the variance of the individual one divided by n, I think.
Yeah, you're right. So
yeah, if the variance of the sample is p1 minus p, then the variance of the of A, which is the sample over n, is just that over n.
but A isn't the sample over. Oh wait, yeah, it's the sum of the
Yeah,
sample
it's
over n.
yeah.
So it would be n times the variance of a single one divided by n squared. So yeah.
Yeah.
So just variance of a single one divided by n, since they're independent of each other.
Yeah. So basically, the answer is this.
Think
Yes.
I see. From this, it follows that MSE is n times. Why is this over n squared?
It's exactly what we did, except
Because
multiply
there's
both
an n
sides
on
by n.
top. Because there's an n on top.
The sum of an independently identically distributed sample is just n times the variance of a single one, and by I think it's like the rule of change of variables with variance. If you multiply a constant with a random variable, then you can take out the constant if you square it.
Oh,
So
okay,
r
wait.
times
So I see what we're
x
doing.
is r
So we
times
have the
variance
variance of
x.
A is equal to fraction of, or no, we have, yeah, it's equal to the variance of 1 minus n times the sum of xi, which we can therefore say is equal to get this fraction 1 over n outside of the thing, it will actually be fraction of 1 over n squared times the variance of the sum of xi.
And xi is identically independently distributed.
Yep, so the sum of actually I fucked this up, this is a capital X. However, this is the step where I'm struggling a bit. So the variance of n summed things, how would you get that to something more logical?
Because the variance of the sum of two random samples is the variance of one plus the variance of the other plus the correlation between the two of them.
Yes.
But because they're independent, they're not correlated.
I see. Okay, so what this basically is saying is this is equal to 1 over n squared times the variance of x0 plus x1 plus x2 plus ... plus xn. I'm not sure if they start counting at 0. I don't think.
No,
No,
they
you start
don't.
counting at 1.
Yeah. Yeah. Okay,
Now
makes
you
sense.
have
'Cause you have
x1.
an
Now you have x1 twice.
oh, my bad. And these should
Also
these
capital
should also
X.
be capital X. Yep.
Yeah.
Okay. So then we have this, and because this is actually because these are independent, which is given, the IID thing, this is actually equal to the variance of x1 plus the variance of x2 plus the blah blah plus the variance of xn, which is therefore equal
Because
to.
they have the same distribution, they have the same variance.
Yep.
Exactly.
So this is equal to this times the sum of.
And they're independent, so we don't have to. So the correlation is equal to 0.
Yeah.
Because usually the variance of a sum of two independent random variables.
Yeah,
would
you
be
can't always
variance
do
of
this,
one,
but because they're
variance of
independent,
the-
you can.
Yeah.
Yeah.
Which is almost always the case in the examples that we do.
Yeah. So.
We don't usually take a sample of different.
Yeah, like
variables.
if you have a sample of like dependent variables, you can't really do too much with them. Or at least
Basically
we
can't
can't
do
yet,
shit
I
with
don't
them.
think.
Yeah.
So then we get this, and then we have, because they're all independent, this sum will actually be equal to n times, so we have the fraction of 1 over n squared times n times the variance of xi. I actually used x1 there, should be xi. And then we just take the variance is equal to p is n. Yeah, so this is equal to frac 1 over n squared times n times p 1 minus p. And that's how we got to the answer we did. Because usually, sometimes I just fill in what you guys are yelling at me, but like, I kind of also want to understand it, so then I just go over the thing again. And now it makes sense.
What do you mean? What do you mean yelling? Yella isn't here.
Ha, funny.
We're yelling at you.
Ha. So hilarious.
I think all these puns are just a bit jarring.
So we have two unbiased estimators for the parameter beta. Estimator is less efficient than estimator T2 if the variances, they're unbiased. So if T1 is smaller than T2, then
That
T1
means
is more efficient.
Yeah, so it's false.
So it's false.
Double negative there.
Yeah. Cheeky.
R and L.
Now the question is, okay, yeah, we have one more. That wasn't challenging yet. Okay. To be fair, now that I'm actually like looking at the material and stuff, it's actually not that hard as I expected. But it was really fucking daunting. Okay.
It is extremely long.
It's like 1 or 2 new formulas per lecture.
What I would say is it's just weird, peculiar.
Down based. Suppose the dataset is the realization of a random sample from an exponential distribution. We would like to estimate 1 over lambda. Consider the following estimator. Let's see. So this one is actually, yeah. So what this one is, this one estimates the expected value, which is for an exponential distribution is 1 over lambda. So this one is pretty good. And this
but
is
mu always stands for average or mean or expectation.
Yeah. Yeah, mu is actually always the average. You can't just I don't think you can just say mu usually stands for the expectation, but I do say it like that because
Yeah. In distributions, the expectations. The thing is, the expectation is always distribution dependent, but you can have a mean without a distribution.
Yeah.
I mean, the minimum of the values does not sound like the best.
Yeah.
They're both unbiased. But they're both unbiased. I think we have to calculate the mean squared error of both of them, because both of them are unbiased.
I mean, it's easy. Basically, the mean square error is just huge for the first one, because you're taking from the minimum value.
For the second one, you mean?
For the second one, you mean?
Yeah, the second one.
Yeah. Like, I can go and try to calculate this, but, like, anything where you take the minimum,
yeah,
it's going to be like, yeah.
Times n.
So this one is logical, and this one is just what the fuck are you doing? Like, the reason this one is here is because theoretically the average is the average checks out. It's the thing one estimate, but
they're both unbiased.
They're both unbiased, but this one does suck ass. But they're both unbiased. So T1 is preferred.
Yeah.
Yeah, that's right. No shit, dude.
They're preferred by a factor of fucking n.
Oh damn! That's like a factor of 2.
Yeah.
It's
okay.
Amazing.
So we have a random sample from a Bernoulli distribution.
I mean, it's assumed that n is at least 2, so like.
No, it could be 1, so it could be less than a factor of 2.
No, it is also assumed that a sample size is more than 1 entry.
Yeah.
I mean, if you have a sample size of 1, then your minimum is just going to be your entry.
G fucking G,
exactly.
yeah.
So yeah, at that point, it's not a factor of 2.
Yeah.
I
hate, but all of maths has an implied for all.
Okay, let's see. So we have a random sample with a Bernoulli distribution, and we say that this estimator, which is just the minimum, it's So there was some
Compute
like
MSc.
there was just some kind of weird thing where you could when you have the minimum. I think somewhere in the book it said that you can then take there's some kind of formula to have the expectation of a minimum. Because there's like no.
Yeah, but
Actually,
this is
in this case,
this is a
this is
Bernoulli
Bernoulli.
distribution,
Never
so
mind.
the minimum is 0.
Yeah, no,
So,
this is Bernoulli again, so we know how to do this. We've done this before. We are smart people.
Yeah.
To the last statement there.
Okay, we
Yeah,
are
very
relatively.
stupid.
Okay, to be fair though, guys, you're on a fucking university. The fact that you're still here in like the last quarter, even though like already 40% have dropped out.
Actually despise being
I
stupid.
dropped down from last year.
Well, yeah, but you know, you're still here as well. Like you didn't give up, so that's like props to you, man.
Did you say 40% dropped out?
Nah, like I think eventually, like this course had like a 50 or 60% pass rate, right?
On average, there's a 60% pass rate
Yeah,
the first year.
more or less.
Yeah, no, I know. Like
shit.
sometimes I think about it and I'm like, holy shit, I'm in the last
Like,
quarter
yeah.
of a year that has a
You
40% pass rate.
What
the fuck?
15 to 20% people dropping in February, and then you got the rest just not getting the BSA.
Yeah.
Yeah.
Oh,
Like,
Like,
I something like, oh shit, I failed some courses, I might fail this year. But like even if like I'm still set to have 45 credits, so like.
Yeah, like as long as you get 45 credits, you have basically
Yeah.
passed your first year of a course where.
Yes, I-
You need 14 this year, guys.
Yeah.
14.
Cool. I know.
I'm
Yeah,
a third year here, and I passed calculus this year, and I hopefully pass PropSet too.
Hey, nice.
But
You're
yeah,
third
I'm
year.
a third year,
Oh,
so
yeah.
don't worry.
King shit. No,
Yeah.
I'm doing pretty well. I've got like an average of 8.2 now, so. But that's honestly, the only reason that my average is so high is because I'm doing these sessions with y'all.
Yeah.
Because I would not be getting those grades if I didn't do these sessions.
Yeah.
Not by a long shot.
By
No,
the way,
I mean,
And also, to be
yeah.
fair, that's something I'm
probably
quite afraid of. Like, if online,
Yeah.
if like real life education that they use, I do want to keep doing these, but I'm afraid less people will show up and my grades will get worse.
I mean,
Actually, still quite a few people would end up showing up.
Yeah.
That's true.
I technically also. Yeah.
I promise I'll show up for you, my boy.
Oh, homie's got
For
me.
people who care, I'm gonna probably do a session on linear algebra like this weekend for people doing the reset.
Nice.
I'm gonna
Good
do
luck.
that too. Yeah. Oh, but
When nobody's got me, I know
yeah.
Ammon's got me.
Yeah. I mean, I technically
Even
have
though
like.
wait, fuck, no, I won't, because I probably won't be doing any of the courses at the same time as you.
Wait,
He's
why
doing
not?
aerospace. He's doing
I'm doing
aerospace
aerospace
actually as
next year.
well. Both at
Oh,
the same time.
I'm not dumbass. Who's
damn. Even Ammon's dropping me.
Yeah.
What do I have
Yeah.
left in life?
Nothing.
I guess.
Fair.
Yeah.
Okay,
You
so
have depression.
guys, let's go and
Yeah.
let's go and work with this. So, let's see. T is the minimum of all of these. Therefore, T is 1 if and only if all of them are 1. This is not a good way to write this down, but I don't give a shit. And T is 0 if 1 minus.
Just to
B.
slash right arrow.
You do realize if and only if you put 2 Fs, right?
Yeah.
No, it's actually just if. Now, honestly, what I can say now, I can say that that capital T simulates a Bernoulli distribution with parameter p to the power of n. This is some big brain play, so now we just have something we can work with.
Wait,
Because it's
so-
only 1 if all of them are correct. Okay. So, now we can calculate the mean square error of this. So then that is MSE of t is equal to variance of t plus
E.
the expectation of t minus p squared. Wait, I literally just wrote this down above here. Also, this should be a. Okay, so we can literally fill this shit in. So the variance of t is actually equal to ft. That's the Bernoulli distribution. The variance is equal to p of 1 minus p. So because our thing actually isn't p, it's actually p to the power of n. So this is going to be p to the power of n times 1 minus p to the power of n plus And now we get the expectation, which is just p to the power of n minus p squared. So this is the mean squared error. Let me close that off and recompile. There we go. So this is, from what I can tell, this would be correct. And we what do we have to do?
What was the question again?
We just need to calculate the mean squared error. So theoretically, we're done.
Should be it then, yeah.
Yeah. Give me a second, and I will just fill this in.
If n was 2, then these two would be the same. Pn 1 minus p to the n would be the same as Pn minus p squared.
Oh yeah, but if n was 2, then
if n was 2, yeah.
Then this one would fall away, and then there would be an unbiased estimator.
Yeah.
Wait,
well, no, it wouldn't fall away.
And
it would
it would have
be
to be
cubed p to the 4 minus p. Yeah.
Wait, okay, yeah, that's actually pretty fucking logical, because if n is 1, then t is the
The
minimum. Yeah.
Big
Okay,
brain.
fair. But let's just enter this, see if it works.
Then variance would also be 0.
So we have p to the power of n times 1 minus p to the power of n plus p to the power of n minus p squared. Let's go! The fun thing is, I remember seeing all these exercises coming through the PTS channel, and I just remember thinking like, "Holy shit, this is so hard!" But then I realized it's not actually hard.
Why exactly are you doing p to the n for Bernoulli?
Okay. So what we had is so this random variable t is equal to 0, left right arrow. So if and only if p and p and p and p, etc. So that's only if p to the power of n and t is equal to 1. If and only if one of these is not true, so 1 minus p to the power of n.
Yeah.
And if you just look at this, you will see that this is basically just a Bernoulli distribution with or Bernoulli trial Bernoulli distribution with parameter p to the power of n.
I think you mixed up the zeros and ones.
You mixed up 0 and 1.
My bad. That's my bad.
Wait. Okay, wait. So I'm confused. Sorry.
Okay, so the minimum, like t is the minimum of a Bernoulli distribution with probability p. Therefore, if any of them are like 0, then the entire thing is 0. So the only way that the minimum of all of these is 1 is if all of them are 1. So you have n times that all have to be 1. The chance of them to be 1 is actually equal to p. So we need to have p and p and p and p and p n times.
Right.
And that's just because they're independent variables, they can just... Yep, exactly.
Okay, that makes perfect sense.
Yeah. I swear to God, if you don't do these graph exercises, you're not going to get it at all. Like, doing the test without it, oh no.
I mean, that's also the book exercises.
Well, yeah. Like, if you do any of the exercises...
Imagine using a book, couldn't be me.
Couldn't be me. I haven't opened the book a single time.
Imagine doing anything but watching Yura's videos. Couldn't be me.
Yeah. I mean, to be fair, all I do is for most courses, I just show up to the lectures. For stuff like CN or for like PTS and stuff, I actually do the web lab as well. And then I just do these sessions. That's all I do.
Same.
Okay, so we have a Bernoulli distribution P. This is an estimator. We have this thing. Well, we know this is an unbiased estimator, so we know it's actually the mean squared error here is actually equal to the variance. And then we can do what we did before. So we have MSE of T1 is equal to the variance of T1 is actually equal to, and we've done it before, so I'm going to go through it relatively quickly. But then we have the variance of 1 over n times the sum of xi. And this is equal to 1 over n squared by the chains of variables formula times the variance of the sum of xi. And because the xi trials are all like independent, they won't be correlated, and therefore the variance of x1 plus x2 is actually equal to the variance of x1 plus the variance of x2. So we can say that this is equal to the fraction of 1 over n squared times the sum of the variances of xi. However, there's just there's n different ones of these, so we have 1 over n squared times n times the variance of xi. However, because these are distributed with a Bernoulli distribution, we can look at the variance of xi and see that it's actually equal to 1 over n squared times n. I will actually get rid of an n here. Times the variance, which is p, times 1 minus p. Which is equal to... So this whole thing is equal to the variance. However, because it's an unbiased estimator, this is also equal to the mean squared error, so this thing is just equal to the mean squared error. Blah. Everybody understand that?
Yeah, we basically already did this one.
Yeah,
so.
we literally already did this, but just to make sure.
Oh, okay. Okay.
Okay. And split. Green
Nice.
percent, boys.
Yeah,
Might
I love
actually be able to do this by the end of today. Wow.
Yeah. Also, I love how these LSE stuff things always center around like Bernoulli because it might get too complicated otherwise.
Yeah.
Well, like the
Yeah.
p to the power of n stuff, like imagine doing that with a normal distribution.
Yeah, like taking the minimum of n Bernoulli trials, easy. Taking the minimum of n normal trials,
Yeah, because Bernoulli trials have a definite minimum, 0. Normal
Yeah.
trials don't.
Yeah, exactly. Like when it's a
Normal
uniform trial, then
distribution allows for infinitely deviant outliers.
yeah, like maybe for example, you could say that if you have infinite pools from a uniform trial, then your minimum is going to be the lowest bound. But you can't do anything like that for a normal distribution.
Yeah.
Okay. So let's have a look at. Oh, I love the fact that we can just skip 12. Ah, like
What was 12
this
again?
thing is the only big thing standing in our way, and for the rest it's just
I have no idea what even was in lecture 12.
me neither. We are going to go through lecture 12 and stuff. Like I don't just want to cover the things. I want to actually understand the material.
Yeah.
So let's see. We were
Lecture 12 was about parametric bootstrap. That wasn't on the exam last year and last before that, so not sure. Is it going to be in here?
This year.
I mean,
somebody
I'm
go to
pretty
the
sure-
probability
I'm pretty
theory and
sure
statistics
that-
channel and ask if lecture 12 is going to be on the exam. Thank you.
I'm pretty sure that like it's even if it's not on the exam, it was probably mostly also just to tell us what real world applications look like. Because I don't see someone calculating the fucking mean squared error of a fucking unbiased estimator fairly often when you could just like
computers.
do it with a fucking computer, yeah.
Yeah.
Like simulate it.
But, I mean, we're also not going to do what's it called binary search every day. Software company, so.
Fair.
Wait,
You're not going to do this every day. Does not mean
binary
it's not going to be on the
search
exam. But yeah, let's just continue. So we have lecture. If somebody else can ask that, that's great. Meanwhile, I'll continue. So lecture 11 is a maximum likelihood, and also the log likelihood. So let's see. This is a real. Say that this is a realization of a random sample from a discrete distribution with a probability mass function. The likelihood is a function. Oh, so likelihood is basically just the chance that you got what you got.
Exactly.
Yeah.
The probability that you got these values for a given parameter.
Yeah. So imagine if I have a uniform distribution, or a normal distribution with average 0 and variance 1, and I pull twice and I get 1,000 and negative 1,000. That chance is going to be really fucking low. But it's possible.
Like
It's
conditional
not zero.
probability, but for statistics.
Yeah, it's basically the probability that you got what you got.
Yeah.
And then we have, let's see.
It's the probability
realization.
of the statistic. Basically.
Okay, yeah. So this is the likelihood of a continuous density function is just. So here you just have the discrete function. Here you have the continuous functions. Usually to get like actual chances, you integrate this. However, here you just multiply them.
Yes. So it's like technically not the probability, but it kind of is.
Yeah, it's the probability that you got what you got, ish.
Yeah. Continuous distributions are weird.
Yeah, continuous distribution. You know, the chance of getting actually, fun fact: the chance of getting what you got is 0.
Yeah. So.
Yeah, you know, hate to break it, the chance of getting what you got is 0. The chance of you being exactly how tall you are, literally 0.
Yeah, impossible.
Impossible.
You couldn't possibly be that tall.
Exactly. Yeah. I mean, then again,
Inconceivable.
then again, like the concept of exact numbers in the real world is inherently flawed. Like you can't say I'm 1 meter 80 because you're probably gonna be like one atom more or less. Well, you know, more than one atom more or less. Anyways,
that's why I always tell girls that if there's a 0% chance.
Could we count stuff using like what's the constant for the smallest distance possible?
Planck constant.
Yeah, couldn't we just like I'm X Planck's constant
Well,
tall?
The Planck constant isn't even like exact.
Yeah.
It is standardized, but it's not. It has an uncertainty about it.
Also going to be really a lot. Like I am 1,000,000,005
Oh yes.
Planck's tall.
Yeah. Actually, fun fact, I'm actually 1 Planck tall by the fact that I have some wooden planks in my backyard, which are exactly as tall as me. Next question. So we have the maximum likelihood estimate, theta hat, little hat, of theta is the value that maximizes the chance that you got what you got. The value is a function of the data, which makes sense.
With a very silly pointy hat.
The corresponding random variable is the maximum likelihood estimator for theta. And that makes sense. So yeah. So basically, you got some numbers from, say, for example, I pick some die, and I roll like 2 3s and a 4. Well, the most likely fucking thing is that I'm rolling d4s, right? Like I'm not gonna be rolling d100s and getting 3 3s and a 4. So.
Well, you could be rolling 6s. Or...
I mean,
well, yeah, true. Yeah. Like it will give me one number, and then like having that n-sided die is going to be my maximum likelihood estimator, and my maximum likelihood estimate is going to be, for example, 6. If I had a die distributed function.
Yeah. Okay. It's a bit weird for uniform distributions, but yeah.
Yeah. Uniform distribution can suck it. So, yeah, the they just completely skip over log likelihood. Basically, the log likelihood is the log of the likelihood. Thank you.
Yeah.
So
the
reason they do log likelihood is because your likelihood, your L of theta, is going to be some kind of product. So we'll have P. It's yeah, okay. So it's going to be theta of x1 times etc. So I'll actually say 2 ... Fuck. ... So I added 1 ... too many, and I just skipped 2. 2 doesn't exist. So yeah, we have this. So
has anyone ever proven that 2 exists? I think not.
Oh, you can use that proof that 1 exists and then double it. So
2 is a met.
But
Don't
first you have to
them.
prove that you can double 1.
Yep.
And proving that 2 is double 1 is not actually that hard.
I know.
So this is basically what we're doing when we take the log likelihood, and I can also say that this is just the sum of P theta of xi. However, if we take the ln of L theta, this will actually give us the ln of a sum of P theta xi. However, I forgot a closing bracket. However, when you take the log of a I fucked that up. This shouldn't be a sum. This should be product.
Product.
Yeah.
So big pi.
I think it's either product or prod, which will give me capital pi. It's gonna be prod. Oh, what? No! Okay. No! Fuck. Why is this UI so shit, man? Okay, so then we have the actual product. And the ln of a product is actually equal to a sum. So then we have... There, so this is basically the important step. So the logarithm of a product is equal to the sum of the logarithms of the things you're multiplying.
I think the log likelihood also often shown as like a squiggly L.
Like this squiggly L. Oh, wait.
Yeah. I think that's supposed to just be the
Squiggly
lower
L LaTeX.
LaTeX.
ELL.
Wait, what?
Command is ELL.
Like this?
Or EEL.
Oh, no, it's ELL. Wow, cool.
L, and L.
So, wait, redo. And this is actually equal to ELL of theta. Oh, and recompile. Yeah, okay. So the log of the chance that you got what you got is equal to the log chance that you got what you got is equal to the sum of the logs of all the individual chances, or all the chances with an unknown parameter.
Yeah,
you recall it. That's why we always did base 10 logs in school.
It's just
even though in maths you always use natural logs.
It's not that it's the same, Jure, it's that the maximum is at the same location.
Oh, hey, Yellow, since when are you here?
I am here since I've got my new Ryzen 7 5800X 32 gig RAM water-cooled machine running.
Yeah, you got a new PC today.
Are you wearing the TU Delft sponsored gamer socks?
Right now,
programmer
yes.
socks, I mean.
Absolutely.
Okay.
Finally got delivered?
Yeah. They're getting delivered like
first try, color.
Nice.
Yes. Which was good because I already put the AIO on.
Okay. Okay, so let's see. Basically, indeed, you're right. This log likelihood. Well, I mean, to be fair, everything I'm saying here so far is correct, right? I'm just taking the log on both sides.
Yeah.
It's just that they're not the same thing.
You said they are the same, like with words.
Oh no, I didn't. I said the log of the chance that I got these is equal to the log of the chance that I got these.
Then I could be wrong.
Yeah, no, that could be me as well, though. Like, that's what I meant to say anyways. So, then we can differentiate this, which, differentiating singular terms is a lot easier than differentiating a bunch of shit.
Yeah.
Then you check if it's the maximum, so either by checking the double thing is, the double derivative is less than 0, or just filling in +1 - 1, see where you get. And if this is the case, then it's the maximum likelihood estimate. Money is point, Bog!
Yeah, and then you integrate either the likelihood or the log likelihood to get the...
What? No?
You're differentiating.
There's an important point, though. This only works if the log likelihood function is differentiable at the maximum. Which in the case of for a uniform distribution, it isn't differentiable.
Yeah.
Cool. I didn't know that. Thank you.
At that point, so it doesn't always work. If you do it for a uniform function, you're going to get theta equal to 0 because it's not defined. And then in the case of uniform distributions, it's kind of intuitive that you just take the maximum. But we'll cross that bridge when we get to it.
Yeah. So we did a likelihood function. Well, this is just going to be the this thing for all of my data points. Those are going to be filled in by into x, and then we multiply them together. So that's just going to be this one. Let's see. The likelihood function L for discrete distribution is this one. For continuous distribution is this one.
But they are functionally the same.
Yeah, like in theory they're the same. However, like you do have, or not in theory, but in practice, I guess. But they are like a little bit more more quirky. The maximum likelihood principle is a general principle used to construct estimators.
Also, you can't really do it with the Bernoulli distribution because it would just be 0.
Yeah, fair.
It would be 0 any time you do it.
Yep.
Except if p is 1, which would just be stupid.
The relationship between a likelihood function and a log likelihood function can be expressed as the log of the likelihood function. Woo! It's almost as if it's in a name, boys. Yeah. Wow, guys. Whew.
Yeah.
That was really hard.
Lumberjacks love them.
Ooh.
I'm seeing I didn't miss much in the past 3 hours.
You did.
Okay, cool.
Yeah.
I would recommend I'll recommend watching it back if you can. Suppose you're given the following. Am I still recording? Yeah. Suppose you're given the following likelihood function for a random variable. That is distributed this way. Compute the log likelihood. Okay, yeah, we can. You can simplify this shit. Okay, cool. Let's see. So this is the likelihood function. Wait.
Ln Sn.
No. Let's see.
They probably want you to
technically correct is the best type
This
of
is what they're looking for.
They probably want you to simplify it. As in.
God damn it. But it doesn't say it. It doesn't say it.
Yeah, plus ln Sn plus S ln P plus.
Yeah, they might want something like this. Because you multiply stuff together.
Yeah.
And then this is also multiplied together, so you could say
S times ln P.
Yeah.
And you can go even further. You could take this S out of there and put it in front. It doesn't like
LSN.
S times ln of P plus n minus S times ln of 1 minus P.
Yeah.
What the fuck?
It's the exact same thing. I know. It's so fucking
yeah, I was about to
annoying.
say, like,
Just to add it
mathematically, it's
again.
literally the same thing. Why are you complaining?
I mean, if you get everything else right, we still get green % because of the repeat question that counts towards the total.
Okay.
Yes, I'm a real gamer.
So this is the log likelihood, and we want the maximum likelihood. Okay, yeah, this is literally just. Woo! You
Take the differential equal to 0.
Yeah, so we have 20 ln of theta minus 15 theta squared. And that's equal to. Was it Li?
Okay, we need 300 and no, we need 32 more people.
EOL.
Yep.
L of theta is equal to this thing.
Yeah.
Therefore,
we need 32.
the derivative of L of theta is equal to.
Oh, let's see. This is the controversial part.
Hmm.
And you have to set it equal to 0 as well.
So this is. Yeah, but this is just like we don't like if we just say this is correct still, we could just set it to 0 later.
Yeah. 20 over theta minus 30.
The derivative of an ln was 1 over, right?
Yeah. 1 over theta.
You forgot. Yeah, it's 1 over theta, so it's 20 over theta.
Yeah.
Yeah.
Minus 30, obviously. We need 32 more people to join the server so that we have 666 members.
Oh, Paul.
Nice.
And then we set this equal to, and then we can say the this thing is equal to 0, and then see what theta we get out of it.
Not 30 theta, just yeah.
Yeah, 30 theta.
Yeah.
Oh, it was squared, yeah.
Yeah.
Right.
So
Yeah.
then I'm going to, well, okay, this is equal to 0. Then
I,
I'm going
I
to
thought you
multiply both
didn't
sides by
already.
theta.
Yeah.
Then I'm going to bring this 20 over to the other side. So it's going to be minus 20. Then I'm going to divide by 30.
No, it would be positive because you have minus 30 theta equal theta
Oh
squared
yeah,
equals
I didn't see
minus
the
20.
minus sign there. Good call.
Yeah.
And then I'm going to take the square root of this.
Your theta's
Seeing
imaginary.
seeing that in a mantissa, negative and positive also denoted by 0 or 1. Again, I'm just here for 0, 1 checks.
Yep.
This is my one purpose.
Yeah. Next one. Compute the maximum likelihood estimator. Okay, simplify this thing. Wait, we want the maximum log likelihood. Oh yeah, so this thing is still in here. Okay, cool.
Yeah.
So we take the. Okay, yeah. Okay, I think I'm seeing where it's going with this. So we have L of theta is equal to n times ln of. Oh, it's actually lambda. My bad. So it's L of lambda minus lambda times sum of xi. Then the differentiable thing of that is equal to 1 minus or n divided by lambda minus the entire thing. We want to set this equal to 0. This thing is what? Oh. Okay, my bad. I just said fraction of lambda instead of fraction of 1 over lambda. So that should be better. Yes, this seems to make sense. Okay. And then we want to get this out of it. So
Oh,
once we
wow.
set this
Okay,
equal,
that's fine.
yeah. I can already tell where they're going with this. So once we set this equal to 0, then we can put the then we can multiply both sides by lambda. This will give us this 1 over lambda will go away. This will be this thing. I can bring this to the other side. Therefore, this will be n. And then to get this, we get oh, this should be normal multiplication, and lambda will be n divided by the sum of all the data points, or 1 divided by the average. Do they accept this notation?
I think they do.
yeah.
They do!
Hey.
Damn. Grasple kind of sucks, but sometimes their notation acceptance is quite bog. Because I'm quite sure
Yeah.
that like bar is not quite the right one for this. Like to.
I always just use bar.
Yeah, me too.
I think bar is
They
the
have,
right
like, a
one.
button for
Is
it? But they also accept
I think
latex.
it is.
Pog. Ooh, okay. So now we get to do the log like. I'm gonna be honest. I actually really enjoy these things. So we have to compute the log likelihood
They're
function.
very therapeutic.
Yeah, exactly. So we want to take the ln of lambda to the power of n times e to the power of minus lambda times I'm just gonna say indeed s because it's a sum. Okay, and then we can simplify this quite a bit. So because we here have a multiplication, we can say that's equal to the sum of the lambdas, and here we just have like an ln and an e, so that cancel each other out. So then this just becomes minus lambda times the sum, and here we have an ln of lambda to the power of n. That's just going to be n times ln of lambda. And therefore, this is my final answer. Because I don't think we can simplify this any further. So we have n times ln lambda minus lambda times f.
Yep.
There we go.
Let's go.
Let's go. Complete the compute the logs like. Oh wait, we just did this one. So this is ln of Sn plus ln of p to the power s plus n minus s times ln of 1 minus p. Or, yes.
Yeah.
Quick maths!
That's
then-
not hot.
And then we get the challenging question. Woo! Oh. We allow you to shorten this to the letter S. Okay. You get a realization of a random sample which is parabolically distributed.
No.
Pareto.
Pareto distribution.
It's parrot distributed. So this parrot is. Okay, so realistically speaking, we have L of theta is equal to the sum of, or no?
Prod.
Wait, why? Like, I know the capital L is the product, but why do we need this? Because eventually we'll use the sum, right?
You'll find it. Just do it.
Sure.
Just keep
To
it
be fair,
as
that makes
the,
sense. So we have the product
just
of
keep it as the log. It's probably gonna be simpler.
f of alpha of x. Let's see. So that's the normal likelihood function. Oh, and actually it shouldn't be x, it should be xi. Okay. Then I will actually make this into whatever function they use here. That is actually equal to the fraction of a times, or alpha over x to the power of alpha plus 1. I might replace that x by xi. Wait, why is it complaining? Oh, it's complaining because I didn't close this one. So yeah, this is just, I will actually make this xi, yeah, because x is not constant. So yeah, so we have this, and then I can take the log likelihood function. So then we get the ln, let's say L of theta is equal to ln of the product of this whole thing. Okay. So far we're good.
I can take alpha out because alpha is going to be alpha to the power of n.
Yep, that's a good one. I'm gonna do a step in between that because I have a little bit of a monkey brain sometimes. So let's see. We have the product of alpha times this fraction. And since alpha is a constant, this will actually be just equal to alpha to the power of n times this product. Oh, and I can get rid of the c dot. And because this is alpha to the power of n. Okay, no. Wait, okay, so this is the product. So I can actually say this is actually equal to plus ln of this product. And therefore you get n times ln of alpha plus ln of 1 over x to the power of alpha minus 1. However, this 1 over x to the power of I, or x I to the power of alpha minus 1 is actually equal to oh no, wait, my bad, that's plus 1, so it should be minus alpha minus 1. And then we can get rid of this thing. So then there we go.
Why minus alpha minus 1?
Because I am getting this.
Oh.
Yeah, so this, I'm just taking this 1 over into a minus top here.
Yeah.
And then I can, because this is in the numerator for all of these, or in the numerator, in the exponent for all of these, I can actually take this out of the bracket as well. And that will give me this thing. And I can also take the minus sign out of here, so then we get alpha plus 1 again. Because it looks a little neater. Okay, so then we have it's n times ln of a minus alpha plus 1 times the ln of the product. I hate the fact that they use s is equal to the product. S is the sum, fuckwads.
Yeah.
Anyway, so we get...
They can't really use P here.
Well, maybe capital P or something like that. A plus 1 times ln of s.
Right, alpha.
Fuck. Oh no. Actually, it doesn't care.
Oh wow.
I'm so close, but A is literally the per definition alpha. Yep. A and alpha are the
Fair
same
enough.
letters. I don't understand why those Greek people had to make everything so difficult. Just use A.
Exactly.
I don't think
They're,
that's quite
they're
how it
massive
works.
drama queens.
I don't think that's quite how it works.
Oh yeah, it is. Yeah, it is. So now we have.
Yeah, just travel. Just travel like 1,000 years into the future and use that letter.
What the fuck?
Duh. Have fun.
Thank you. You sure must be glad that I'm doing this, not you guys. Fucking hell.
Oh yeah.
So this is actually equal to the product of fraction x over theta squared times e to the power of minus the fraction of 1 over 2 times x squared over theta squared, closing bracket, closing bracket, closing bracket.
Oh, that's beautiful. I can barely even read it.
Yeah, wait, let me help you guys. There we go.
No, it's not you.
Okay.
I mean,
So I
we
can start by
do this
taking out a
step by
few
step.
of the constants, right?
Yeah.
So over here, this is let's see. I'm
X
going
to the
to
n.
separate this product into like a few steps. So we have 1 over theta squared times x, and I'm also going to take this 1/2 outside of the top of the fraction, and just put it like to the left of the fraction like this. And therefore, since and I'll put a C dot here to not make it confusing. Okay, and then since these two are also their own things, I can also just take this e to the power of negative 1/2 out and put that up front here. All right, and not only that, but I can also get this e to the power of 1 over theta squared. Oh, so this is going to be 1 over theta squared times x squared. And like basically the only, by the way, I'm using x's here. These should be x's dependent on I, right? Because they are like the realization of random variables, and they're like I different x's. But yeah, so then we have this. Then I can take this e to the power of x theta squared. I can take that out of the out of here as well. So that leaves us with e to the power of Okay. So now we have a bunch of shit related to theta and a bunch of shit actually related to e. I can actually throw these two e to the power of together. So this is going to be...
I think you forgot an x in the third line. In the power.
Did I? Oh yeah.
Now you have 1 squared.
You put
No,
one
no,
instead of x there.
I did c dot x squared instead of c dot x squared. Yeah. Okay. Okay, cool. So now we have this bunch of stuff. However, that means that when we get, we can take all of this outside of the product.
Yeah, we can take all the
And like
constants
all
out
this will be just all of this
to the power of n.
times the product of. Yep.
Yeah.
And I can actually make this a little easier. So this, taking this step by step, 1 over sigma to the power of 2 to the power of n will actually become 1 over sigma to the power of 2n. Sorry, theta, not sigma. Then we have this thing, which will become e to the power
Don't
of
forget
minus
the don't
n
forget the
over
squiggly
2.
brackets.
Oh yeah, I forgot my my curly brackets. My bad. Okay, so that gets rid of this square thing. Let me get rid of this bracket as well. Okay.
Jura,
Hmm?
would you mind like putting the variable under the sum or the product?
Yeah, sure.
Because right now I just spent like a whole while looking at why are you taking that out of the brackets, but I now see that it's because of it's a product of terms in relation to x, which means
Yeah,
that
yeah.
theta
So
is
I can
yeah.
say this properly. It's gonna be like e is 1 to n, where it's actually xi e to the power of xi squared.
Yeah, that's a lot clearer.
Yeah. I did some exercise before with this, but then I just started leaving it out. But I can include it if you want. So this is what we have now.
Yeah, if you don't mind leaving it in, it does make it clear.
Yeah. So, and actually,
I
because
think this
it's negative, I can actually turn this into a fraction of 1 over e to the power of blah blah blah. This whole thing.
I mean, there's sure.
And ooh.
Bruh.
Oh yeah, I should have included this 1 over. There we go, and we can also
combine the two
combine
fractions
the two.
theoretically.
So then I can get rid of this part.
Aren't you going to separate them anyways when you do the log of it?
Probably, yeah. Now that you mention it.
I mean, yeah.
Okay.
Whatever.
When we get there.
Yeah, now we just differentiate this. No.
No, we
no, we don't.
I have a question.
Yeah.
Maybe it's just me not being able to math anymore, but like, if we had changed the e to the minus as a 1 over earlier, before taking it out of the bracket, wouldn't it be like?
If we change it
about what happens. Oh wait, no. Sorry, no, you're right. Oh, well, I'm just tired.
All right, no worries.
Jura.
Yeah.
So we want to know the place where the never mind. I was
we want to
thinking,
know this
what if we
place
just
where
plug in infinity?
Where this expression is maximal.
Yeah.
Yeah. I was wondering what would happen if we plugged in infinity for a theta.
Yeah, a lot of actually it would be 0.
Yeah.
Yeah.
It would approach 0.
Yeah, hell, that makes a lot of sense. It will do so in every case because the chance that your parameter is infinity is going to be 0.
Yeah.
Yeah, I hate to break it to you, but
Now we have to take the log. Woohoo!
Okay.
I mean, not always. In this case, yes, but in like the variance can be infinite in a normal distribution, right?
Yeah. Okay. Fair. True. So now we take
distribution with infinite variance just be a uniform distribution or something.
So now I take the log of all of this.
Well, it would be very close, but not quite.
Oh, and Yoda, just one small thing.
Yep.
Since we don't have any theta in the product part of that, we can just leave that inside the log, and it's anyways going to disappear with the derivative. So we can just chuck the entire log into the entire product part of it into a logarithm, and we don't have to like completely separate it out.
Yeah, good point. Okay, so now I by the way I accidentally put a comma here, a flying comma, but I removed that because it's not supposed to be there. So now we have this. Then we can separate this stuff into the first part plus the ln of the second part.
And change the product to a sum.
We can, however, this thing is not in terms of
Theta.
sigma, so theta anymore. So the moment we differentiate, all of this falls away.
It all becomes
how
0.
handy.
Yes.
And you
then
can, if you want, you can remove the division and just do minus.
yeah,
from
exactly.
that.
So this 1 over can
Yeah.
also go away. This will just be 1 or minus the ln.
Yeah.
Okay. Okay, and then I'm going to separate this into two parts. So we have this e to the power of blah blah blah. That's going to be one of the ln's. And then it's going to be minus the ln, because this is minus a plus b is going to be minus a plus minus b. Okay, and then this first part is obviously going to, ln and e cancel, so this is just going to be n over. Oh, did I removed one too many? Did I not? Yeah, okay, that went well. Then we do this thing. Then we have this minus ln of this, yep, and this.
You can take the
Yep,
2
you
and
can take
out.
the 2n down.
Oh yeah, that's a good one. Nice. Okay, so then we. Oh, did I add one too many? Okay, yeah, makes sense. And then this theta to the power of 2n can be changed to 2n times ln of theta, which is nice. And there we go. So now, when we take the derivative of this, let's see, first of all, this big ass product term goes away because it's not in terms of theta, so it's constant. Lovely.
Bye-bye.
Ah.
Good fucking riddance.
And then this thing will turn into, let's see. So this will be c dot 1 over.
Minus 2n over 2 theta to the theta cubed. Yep.
Yeah, so this is c to the power of minus 2. We subtract 1, put it up front. So then we get minus 2 c to the power of cubed. And then this ln theta will just turn into 1 over theta. Okay, and then we can cancel out these 2's, we cancel out these minus signs.
N over theta cubes.
Yeah, the 2 on the bottom and the top also cancel out.
Yeah.
Yeah.
Oh wait, did
You
I?
forgot the. Yeah, you forgot the 2 in the first one. It was minus n over 2 times 2 over.
I removed the wrong 2. My bad.
Yeah.
Lamo. So I got rid of this minus sign, and this minus sign, and this 2, and this 2, and then this n can go up here, and then this should all. Oh, that's not an m, that's an n. Yeah, I'm not sure if there's anything else.
Yeah, equals to 0, and then
Oh yeah, good point. Good point. Forgets the rest of the computation.
Literally just leaves the expression.
Yeah, no, that's it. That's it. No, okay, so this is our final thing.
Now you need to set it equal to 0, and then isolate for theta.
Yeah. Okay, let's do that then. So we have is equal to 0. Okay, so first of all, I'm going to bring this one to the right side, and I'm going to cross multiply. So we have this thing, and then I'm going to cross multiply, which will give me. Actually, I'm just going to write this by hand. So we have n times theta is equal to 2n times theta cubed. And since we know n will most likely be a positive number, I will just divide by n real quick. Because you can't have a samples of like 0, and if you can, fuck you. Then I will divide by theta for now.
The sample doesn't exist.
Actually, yeah, assume theta is a positive parameter, so they actually thought of this. Then I will divide by 2. and therefore we have, it's theta is plus or minus square root of a half. However, it's a positive parameter, so
Positive.
theta is the square root. Oh my god, 1 over 2.
The square root
And
is
it's
very first.
square root of 1 over 2. Which is 1 times square root of 1 over the square root of 2, blah blah blah, whatever. Oh my god.
Nope.
Where did I fuck up then? That's
I think
my
you
problem.
fucked up in the last step. So going from n
No,
over.
zero beyond. You can't just divide theta by theta. If theta is 0, then it won't.
Yeah, but it's a positive parameter.
Wouldn't it be easier to just invert them
Oh.
and then divide by theta?
Wait, I want to see
So have, like,
I want to see what
theta
went wrong in
cubed.
mine first. Give me a sec. So
Yeah.
so far this is where I got by just multiplying by theta and theta cubed.
I'm going to be honest. I think this, if we have a question like these, it's like 100% going to mess up the calculation.
I mean, we can just divide by theta, right? Because it's a positive parameter. It's not 0. So then we get n equal to.
Well, is
theta.
0 a positive number?
Ooh. And then I can divide by n as well.
Yeah, you need to have messed up before that because I
Yeah, because this one seems correct.
N over.
Oh no! Where? Oh no!
And see where we went wrong. It would be take way too much time to just see. Just take the hit. I mean, we won't get points for this one.
Yeah, I'll take that. I'll take the L. Wait, why is this included?
Let's check.
What?
So okay,
That
let's
makes
see.
no
They had
sense. Theta
RL
isn't in there,
was
though.
okay. So they took this thing out of the brackets. I can agree with that. And then they had this part, and then they. What the fuck?
What?
I have no word. I thought what we did make sense, but now looking at
This
this.
one was fucking bullshit. This one was fucking bullshit. This one.
I think in the separating we must have made a mistake.
Yeah.
Yeah.
I think they made a mistake by creating this.
Yeah, you know what? I would gladly take that L on the test. I would film my answer. Like, you know what? Fuck it. I'm proud of this Perl. This magnificent piece of code.
Yeah.
Okay.
Let's hope writing "fuck you" will at least give you partial points.
Yes. Exactly.
So we have the ln of C hat or whatever C line C bar plus some number times ln of mu minus blah 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 mu. So this is basically just saying. Wait, we want to know the maximum likelihood estimator. So the ln of the derivative of the first thing is equal to 0. The derivative of the second thing is equal to 537 over mu. 7 over mu minus 576. I want this to be equal to 0. I'm just going to do this one really quickly. Going to take this one to the other side. Multiply both sides by mu. Or actually, yeah, I'm just going to say this is equal to mu. Are those the original numbers? Yes. Cool.
Yeah.
Enter. Yes. Pog.
Oh shit! I didn't realize we got the socks for free. I just received them. I thought they were like a thing that you guys bought. Damn. I feel.
Yeah.
This is very big.
Nope,
Nice.
we get budget programming socks.
Yep.
You know, I used to have imposter. I used to have imposter syndrome, but after wearing these socks, it's never gonna happen again. I'm gonna feel like a true programmer.
It is clearly the solution to all our imposter syndrome problems.
Yeah.
Yep.
Get
Sadly,
bigger
that's knee
socks.
height. No, you have to wear them so much that they like wear out and you can pull them off their knees. Then they're programmer socks.
What if we commission a like a set of actual knee highs or thigh highs with the Tudor logo.
I mean, I can crochet.
Ooh.
Not very well, but I can crochet.
We could finally prove
But
that all CSC students are
crocheting isn't
femboys.
really the most powerful material for socks, so.
Oh yes, baby.
I mean, like those shops where you can like put stuff on T-shirts, probably also, and like mugs, probably also have socks.
All right. Let's see. We need to find the light. What the fuck is this thing?
Looks up programmer socks
Oh,
on
wait.
Amazon.
Fuck is C?
That's the format. So you have to multiply each of them together and stuff.
Yeah, I know that much, but okay. So, but I don't. What is this C? Like, is this C to the power of something?
No, that's a constant.
But why is there a bar?
Because it's an aggregate constant. It's just because it's the constant made up of multiple smaller constants added slash multiplied together. It's basically all the other constants you have smashed into one.
Okay, but wouldn't that just be C to the power of n?
No, because it's different constants every time.
Oh,
Yeah.
I see.
Like, yeah.
So this is a Poisson distribution.
Yeah.
And this is what we have.
They were supposed to use likelihood estimate though.
Yeah, but this is the likelihood estimate is just the chance that that x is equal to blah 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 multiplied together.
Mm.
So let's see, it's the product of these. Let's see, and then we have so it's the product of 1 over k factorial for all k's, and u to the power of k for all k's, and then e to the power of minus okay, so can I copy this?
Yeah.
Can I put bar above it?
No.
Okay, times mu to the power of and this is going to be, let's see, k is what we fill in.
So 0, 1, 2, 3, and so on.
Wait, is that true?
Yeah.
Okay, so this is 0 plus 1 plus.
You have to multiply it by the frequency though, I think.
Let's see, so we multiply this k together, and then you add the exponents. So I don't need to do this k. Yeah, okay. And then we have e to the power of minus, and this is just 7 times mu. Or no, it's not 7, it's 8.
But we have to find out what C is.
Do we though?
I think you need to use the frequencies and not the
Yeah.
Hmm?
Yeah, you have to use the frequencies and stuff.
not the numbers, not the 1 plus 2 plus 3.
Okay, so this
So-
will be
109 plus 90 plus 114 plus
No, you're
96.
multiplying.
yeah, but when you multiply the
E.
you multiply
You
this thing, the exponents get added.
Yeah,
No,
and
no.
for
Right.
E, you
but-
use the multiplied frequencies. So e to the power minus the frequencies multiplied by.
Is
Yeah.
that true though? Because in the let's see, we were doing this one. No, we were doing this one. Yes. So this is just minus mu, and mu is the parameter. We're not doing anything with k here. So this is just minus mu, minus mu, minus mu, minus mu 8 times. That's just gonna be minus, or sorry, e to the power of minus mu, e to the power of minus mu, e to the power of minus mu 8 times. That's going to be e to the power of minus 8 mu. I do appreciate that we don't have to write 1 over this thing factorial times this thing factorial, etc. But
No, because you didn't do it 8 times, you did it this many times. The outcomes,
No.
I think.
No, because this is just a multiplication of this thing with itself 8 times.
Not true.
I think that's correct.
You have to actually put a constant there, I think.
Why do this fucking? Why does it say C here instead of dot 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 then? Ugh.
Because
Whatever.
that's the format, not the answer.
Yeah, but it doesn't say A and B here either.
Oh, the C is fine.
Oh.
I'm pretty sure the C part was fine.
Yeah, the C is fine.
Yeah, I know this part is fine, but then there's a problem in here.
Yeah. Just do 109 plus 90 plus so on. 109 plus 90 plus
Don't put 113 because first don't put 113 because it's 0 anyway.
Yeah, 109 plus 90 plus 114 plus.
Yeah, but then we're like
90.
calculating the expected value. Like this is just. So we want to know the chance that P is equal to. Oh my god.
Yeah, because it's 109 times 2,
Yeah,
35 times
yeah.
38
And this
3
is
times.
okay. Yeah, I completely read this fucking graph wrong.
Yeah.
Okay, thank you guys. So this is just going to be
pretty weird.
So this will be this then, because this is just the amount of trials you do.
I think it's literally the opposite. I think you now just flip them.
That also explains why they don't want us to calculate the C, because that would be incredibly huge.
Yeah. Can you show the formula once again? Oh, never mind. Just gonna check it anyways.
Yep.
Okay.
Hell no, I'm not doing that, calculating those numbers in my head.
Okay, fair. Once you read the thing correctly, it actually helps.
Yeah.
Oh no, not this again.
Maximum likely estimate for
At least it's better than the last time.
Yeah.
The last one.
This is just a
normal distribution.
Yeah, normal distribution centered at 0. No, centered at 1. Because otherwise it would be divided by sigma squared here. Yeah, I can live it up. I can live it up. So we have L of what do we call? We're looking at mu, so we have L of mu is equal to the product of 1 over square root of 2 pi times e to the power of minus 1 half times x minus mu squared. Boy, this is going to be fun to pull apart. So first of all, we can take this one times something blah 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 pi out, because that's just what's it called? Because that's just a constant. A constant compared to u. We can also pull e to the power of minus a half out, and that will leave us with just this part. Wait, I fucked up somewhere.
Wait, no. If you pulled out e to the power of minus a half, then it would be minus a half plus x minus mu squared.
No, you can do e to the minus a half.
Yeah, let me write it like this. Maybe that will help.
Yeah.
Wait, no, wait.
No,
You're right.
It's the same. Yeah.
Damn, you're right.
You have to take e to the x minus mu squared to the power of a half of minus a half.
Yeah.
You can take that to the power of minus a half, which takes gets rid of the squared. You can do some tricky stuff here.
What do you mean?
You can take e to the power of x minus mu squared to the power of. Wait, no, you can't.
No, you can't take the power and something.
So what you can do is just 1 over.
Yeah.
The square root of e to the power of x minus.
Yeah, but I don't think that's going to help.
Because you can take.
Because.
Like
it won't add anything like writing it like that.
Fair enough.
Fair. So then all we have to do now is take the log. So we have the L of this thing is equal to the log of this whole thing. I love the fancy squiggle.
Yeah.
Okay,
Oh.
and then we could take this thing here.
And that's
Plus.
how it's literally just called L, but like written out.
Yeah, exactly.
I think that's probably the mistake that we did last time as well.
Which
ELL stands for
Probably.
yeah.
Wait, so what
ELL stands
exactly?
for extremely luscious letter.
Also, this to the power of n is actually the whole fraction to the power of n, because 1 to the power of n is 1. So we can take this n out of the ln. So therefore we get this.
Yeah.
And then we can take it one step further, because this actually says...
Make it minus.
Yeah, exactly. You guys know what I mean. So I can just get rid of this 1 over thing here. And not only that, but the square root is actually nothing more than to the power of a half. So I can get...
Oh wow, true.
Yeah!
True. Damn.
So this actually is just the ln of 2 times pi.
Big brain.
And actually, I could turn this into the ln of 2 plus the ln of pi, but that doesn't help us, I don't think.
No, not really.
But yeah, so then we have this, and then the less fortunate part. So,
Indeed.
looking at this... Oh, wait, no, never mind, this is fucking easy. No, this is like extremely easy, you guys don't understand. So what I'm going to do is this is actually equal to... So again, the ln of a times b is actually equal to the ln of a plus the ln of b. So I'm going to take this ln into the thing, and I'm going to turn this into a sum. Ln of e to the power.
Yeah, which gets rid of the e.
Yeah, so this ln of e to the power just becomes like this. And close this one out. And then we're just left with this. And let's see. Because it's now written like this, first of all I'm going to get this minus a half out, because it's just a constant. Okay. Because it's now written like this, I can do some other stuff. However, what I'm first going to do is I'm going to set it to 0, because that gives me a little bit of more artistic freedom. So when I set this to 0, I can multiply both sides by minus 2.
You can't set it to 0 yet, though. You have to take the derivative
Oh,
first.
yeah, good part.
No.
Fuck. Annoying, annoying. So...
But at least we're going to use the left-hand side, the left expression.
Wasn't it that you had to take the sum of ln so on and so forth? Oh wait, no, it's e.
Yeah, but the ln and e cancel out.
Yeah.
Yeah, this squared here is quite annoying me, so I'm just literally going to write this out as x squared minus 2 mu x.
Wait, no, why is it annoying you? It's easy to take the derivative of that.
Yeah,
you just take the outer derivative times the inner derivative.
Yeah, true. We can use the chain rule, I guess. Makes sense. Okay, so I'll do that. This thing here in the front is not dependent on mu. Bye-bye.
Au revoir.
And this right side is just the derivative of a summation, so it's derivative of the parts. That is going to be 2 times this thing. However, our thing is the derivative inside, which is a minus. Minus and minus cancel. The 2.5 cancel. So Huh.
This feels wrong somehow.
This is very wrong. Because setting this to 0 means that every x is equal to the
residuals. The sum of the residuals.
Oh, actually, no, never mind. I was gonna say, like, if we like this is equal to the sum of x from 1 to blah 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 minus the sum of this thing from 1 to blah blah blah, which will turn this into I'm going to continue, but I know I made a mistake somewhere. I just want to show what I mean, so... Oh, that's going to be minus the sum of mu. And the sum of mu thing can actually be mu to the power of n. But, you know, we can't just take the sum of this thing.
Yeah, you can. No? Oh, no, wait.
No, because this is just...
Take it equal.
yeah, so...
the n through.
Yeah, this is actually just equal to from I equal to 1 to n. So this is like the full notation. But we can't just minimize this or say this is equal to 0. So we made a mistake somewhere.
I mean, we can. It looks like an ugly expression because you could just set it.
Yeah, we
just
can
take mu
try.
over to the other side, and
Wait,
then you just have the nth root of.
Yeah, no, you're right.
of
You're
the
right.
sum.
You're right. You're totally right. This whole thing is, of course, a fucking dependent on the sum. So when we set this equal to 0, we can actually take the we can actually add mu to the power of n on both sides.
Oh,
And
why
then
is the mu
take
to the
the
power n?
Hmm?
Why is the mu to the power n?
Because this is
Not
just
true. Why
like,
is it? Wait, no. Why
oh
is it
wait,
mu to the power
this
n?
is not to
It's
the power n.
times
This is
mu.
just times n.
Good catch.
Good catch, Yella. Okay, and then we divide by n. So mu is actually.
Yeah, that makes sense, and that's the average.
Wow, did we just calculate the fucking average ourselves?
Yeah, exactly, and that makes sense for it to
I
be
mean,
the
we knew
average.
it was a normal distribution, so like. See bar x, I think that should work. Bar x
Fucking
over
sum
n.
of only the xi and then minus. Oh.
So we set this equal to 0. We get this thing to the other side, and we divide both sides by n.
Yeah, no, I thought it was just still the sum of both terms, and
No,
you just
no.
magically pulled an n out of your ass. But no.
The brackets matter, Yellow.
Always gonna pull that n out of your ass, you know.
Important.
Yeah,
important.
Might
So
be
then we have the
difficult
sum
there.
of from I goes to 1 to n of xi yeah, and then this whole thing
over n.
Yeah, I can write the divided by n here as well. That's fine.
Yeah,
can you?
same thing.
Yeah, I can.
Yeah, true. A sum over n is the same as the sum over n. Yeah.
What the fuck?
Nice.
I mean, the maximum log likelihood estimate of the average is the average.
Yeah.
Yeah. I mean, the thing is, technically, mu isn't the average; it's the expectation. It's just that since we already know that the average is super close to the expectation, we use it interchangeably. But they're technically different things.
They're technically
Like if someone put a gun to my head and said, "What is the difference between the average and the expectations?" They better be ready to pull that trigger.
Yep. Okay. Determine the maximum likelihood average. Okay, they already get. We literally just have to differentiate and set equal to. Cool. I love how we just derive this formula ourselves. That's a nice exercise.
Yeah.
So we have L of alpha is equal to n times ln of alpha minus a plus 1 times ln of the product from I goes to 1 from 1 to
Okay, but
n
can we
of
talk about
xi.
so like calculate the maximum likelihood estimate? It's just fill in the blank. What is the maximum likelihood estimate?
Yep.
What are you doing?
Yeah.
This isn't a Jackstones video.
So now what we can do is first of all I will actually. No wait, this is I made a mistake here. I put a tilde here. It should not be there. I will take this a plus 1. I will take this to a times this thing. And don't forget the minus sign in front, so this will become minus this thing, yes. And then when we take the derivative, you can see that like that minus 1 is completely irrelevant. So this thing, or this whole thing, not in terms of a. Bye-bye. Or not in terms of alpha, I should say.
Did you say completely relevant or completely irrelevant?
Completely irrelevant, because like if we have this wait, where's the top one? Yeah, okay, so here we have like this a plus 1 thing. It's exactly the same as just a, because the plus 1, like once you fold it out, it will become an extra term on the right here, like in our case this one, and this one is not dependent on a. So when we take the derivative with respect to a, it will just fall away.
Yeah, of course.
And then also here, this one is like this one here is a times a constant, so this is just, you know, the constant itself. And then the only thing we have to worry about is, or well, yeah. The only thing we have to worry about is this n times ln of a, and that's just going to be n over a. Okay, Pog. Then we set this equal to 0. I'm always like a little bit skeptical about just saying it's equal to 0 because it's not. But we can set it equal to 0, and in that case, so let's see. I will take this one. Yeah, I'll take this one to the other side. That's good enough for now. So that will become like this. Then I will flip both of them. So this will actually be fraction of fraction of 1 over this whole thing, and this will be equal to the fraction of alpha over n. Okay, and then just multiplying both sides by n will give n over the ln of the sum, or of the product. So we get n over ln of s, because they say we can substitute that. Nice. You know, I expected this grind to be a lot worse, but it's actually kind of reasonable. It's kind of doable, decent. Okay.
Muriel on the grind 24/7.
Yeah. I mean, to be fair, I play like 3 or 4 RuneScape accounts at the same time, and I play them like 8 hours a day or more. So I am practically like playing 24 hours a day, just not on one client.
To be fair though, at the same time, like I was kind of up to date with the Grasple exercises, and they're way easier than the examples that we did in the pre-lecture, the pre-exam, like the last lecture where we did like exam level exercises. They're on a completely different level.
Don't say that.
No, please don't.
No, just let me have my false hope for a bit, okay?
You didn't hear that. You never heard that.
I never heard that. No idea.
didn't
No
say
idea what you're talking
anything.
about. Okay. So the likelihood function is defined as this thing. I like that they already gave that to us, because I couldn't be asked to calculate it. So we have L of lambda is equal to lambda to the power of n times e to the power of minus lambda times n times bar x n, which is the average. Okay. Oh, I forgot a bracket. Then the log likelihood is equal to the log of all this. Okay. Log of all this, I can change this into the log of one thing plus the log of a second thing. However, the log of e to the power just cancels out. So then we end up with this. Yeah, that seems correct. And again, we can also take this to the power of n up front. So we get n times. Okay. Then I can take the derivative with respect to lambda, and this ln of lambda will turn into 1 over. Then we get n over lambda. This plus minus will just be a minus because I'm dumb. This lambda will go away, and this will just be like this. Okay, setting this equal to 0 gives us a very neat way to solve this equation. Namely, we can add this to both sides. Yep, we can invert both sides. Well, actually, realistically, there's a trick where you swap these two around. So lambda is equal to n c dot bar n. And because these n's cancel out with each other, okay, now what we have is this, but the n's cancel out. This is actually just 1 over the average. 1 over bar xn. All right. And this was... That's all of it for lecture 11. I'm going to go to the toilet. Oh, and lecture 12 as well. Let's go! I'm going to go to the toilet real quick, and then we're going to go over lecture 12, see what we're missing. Be right back.
We are missing a sense of pride and accomplishment.
Yeah. We're losing seconds here on the speed run.
Still a world record pace.
Painful.
Anyway,
Time lost,
I
time
see
lost.
at the PTS reset in August.
Honestly, we should upload these just like speed runs, and then every year, first year students kind of like try to beat them.
I think the lecture is uploaded. Their pop set is on speedrun.net or something.
Usually sets unlisted. He actively shares them with the new freshmen. They won't be able to just find them on YouTube.
How's your guys' day been? Nice story.
Mm-hmm. I know.
Just spent the entire day thinking about how I'm going to fail ability theory and statistics.
That's
But also
how it
imagine
goes.
if this was what pulled up the passing rate. If
I
this
think I think you might actually be able to legitimately see a difference in the pass rate of years with yellow and years without. With yellow,
yes,
I mean,
Yura might be doing the sessions, but Yella is the one who pulls us all together. Yella is the emotional core.
It's his presence.
Yellow.
Yura.
Yes.
I swear to God, Yoda's like a fucking CSE angel that just comes down and blesses us from the heavens with knowledge.
Instead of I can be your angel or your devil, it's I can be your Yura or your Yella.
I kind of see him. I see him as a parasite. It's kind of a symbiotic relationship. We help him by forcing him to do all this, because otherwise he would never ever do this. And he helped us by going through the material in a way that is better and more clear than any lecturer ever could.
Yeah.
Well, they could, but they just don't care.
Yeah.
My experience with lecturers.
They could, but where's the fun in that?
Yeah, I mean, some lectures are actually nice.
True.
I mean, yeah, Stefan is the best one.
Yeah, why can't Stefan just come back?
Did he leave?
No, but like as an have as a lecturer again.
I think we have him next year in the course, right?
Yeah.
He gives algorithm design.
In two, actually, yeah. And automata, computability, and complexity theory.
Yeah, they're both very fun courses.
Yes, and also, I think I've also heard that they're also hard courses, or at least like algorithm design is. So.
Algorithm design is doable. Complexity is, in my opinion, a bit harder.
I mean, it's called complexity.
Very complex.
It might be complex, so.
Yeah.
But
Not even the hard part. Complexity.
Oh shit. I haven't run Cinebench yet on my new PC.
That's very important.
That's the only reason why people won't buy new PCs.
Yes, that's the only reason why one would ever upgrade.
I mean, if you haven't run Cinebench, do you even have a PC?
No,
Clearly not.
it's a Mac until you run Cinebench on it.
Holy shit.
Fuck Mac.
I just turned on Cinebench and my PC just went.
What?
Bone Jaw, I'm back.
Well, anyways, now that he's gone, does anyone else hate Euro so much?
Yes,
No.
yes, absolutely despise.
Yo.
Maximum despise, you know.
Maximum despise.
All right, that's the thing for today. Fuck it now.
Yeah.
So we're currently in
Okay,
lecture
goodbye.
12.
Italians when there's too much spice in the food. Maximum despise.
Ha. Okay. So this
My
is
God,
the
this man is so
parametric.
funny.
That's the thing, though. I don't understand why they didn't like make any exercises about this. This is like. This seems like it would be pretty easy to make exercises about.
Because there's no exercises to do here. This is all just like let a computer do it.
Yeah, but like you can do this manually. They could even
But
ask
the
like stuff
bootstraps
about.
don't.
Theoretically, you can do anything a computer can do.
Yeah, no, but like you can
Anything
literally
you can
ask
do, I
about.
can do better.
I can do
You
anything.
can literally
better
ask
than
about like bootstrap
Yeah.
samples, like the question
Humans.
that hey,
Yeah.
this one is not a bootstrap sample because 22 isn't in the original thing, or this one isn't a bootstrap sample because this one has a different amount of entity. Like stuff like that could have been in the thing. Like
I don't understand
Yeah,
jack
they
shit.
can ask
about
theoretical
samples.
questions.
Humans are just computers with good pattern recognition.
Yes. And terrible computers.
Warren to deck.
Computers are just
And terrible computer speed, though.
No, but
Yeah.
humans aren't Turing complete. Humans are not computers.
ooh,
well, there
Oh,
was
dear.
a Turing has been made as a human, so
Well,
Oh,
no,
fuck.
for something to be Turing complete, it needs to always do the
Honestly,
thing, and a human
I'm
can
not sure
die or
Alan
just
Turing
like
was
forget.
Turing complete.
holy
I'll
shit,
be
guys!
honest with
Look,
you.
Ambi right.
The original
Oh,
It's Amber from
Computer
the
science
C
has
exam.
envy rights.
yeah. I still think we should have pronoun rules, but you know,
we're
you all
going
can't
for
have
it.
nice things.
the original
Okay.
computer Rocket is politics. a human, so
Okay, but yeah, basically bootstrap samples it's pretty easy. Like, say you have a small amount of numbers, and you want to actually get more information out of it. Then you take bootstrap samples, which is basically just samples from your smaller array, and then do shit with that.
So you randomize the data you already have.
Yeah, you take like a few samples from your data instead of from the complete space, and then estimate parameters, and then
I
from
still
there
don't
on you
get
go
how
from
it
parameters
works,
you
I'll be
can
honest.
generate
Yeah.
new data.
I still don't really get how it works, I'm gonna be honest with you. Like, how is like it giving you information on the overall set more than what you already had? I don't get it.
It isn't.
you can't get an additional information from a
You're
data
not getting
set.
additional information. You're just simulating based on the data that you have.
Right, but you're
If
not
that makes
actually
any
like
sense.
getting anything new at any point.
Right.
You're not getting
what
anything
what
new.
it's
I
doing
think
is
it's more like you're
basically
condensing it.
like this image here is a pretty good thing. So you have this expression or this distribution which we do not know. Then you have a sample from that. Then we have some data such as realization. We can get a parameter from that, and with this parameter we can generate new data, and we can get heuristics from that data where we repeat that a bunch of times, and then we can get estimates about that data even though we didn't have like a ton of data in the first place. We just kind of estimate
We
what
shuffle the data, and by basically by basic statistics, the more common ones are going to show up more, and that's like just going to positively reinforce like the data basically.
Right, but
Like it's going to
Yeah.
emphasize it's going to emphasize trends in your data.
Yeah. Okay.
sure.
It basically just gives you more of the same data, so you can see like patterns better and stuff.
exactly. So
So just
you
like
can
it's like
basically
replicating the data at a
take two
larger
points.
scale.
Until like 2 minutes ago, I didn't even know what bootstrapping is.
Guys, the way you can
Yeah.
see this, right, is if you take a coin flip and you flip heads twice, then you come to the conclusion that you only can flip heads on a coin. That's the whole thing.
Yeah, and if you bootstrap it, you only get heads ever.
Yeah. So then you say, okay, my bootstrap distribution is a uniform distribution between 1 and 1. And to be fair, not the best example because it doesn't actually.
Uniform. That's not continuous, Jure.
Hmm?
It can't be uniform because a coin flip is not continuous. Wouldn't it
Okay,
just be a Bernoulli?
it will be a discrete. Oh, let's say it's a Bernoulli trial with a P of 1.
Yeah.
I would say it would also be a uniform distribution with bounds 1 and 1.
Yeah, because you can only. Well, the thing is, right? Since it's a uniform distribution with bounds 1 and 1, the chance of getting 1 is 0.
Yes.
But. Oh, and not only that, but
the fun shit you can do with misreading data.
Yeah, not only that, but
Integrals.
the function would just be infinite. Always.
True.
And
Yeah,
to be fair,
height would be
that makes
infinite.
sense actually. That makes sense because it has an infinitely high chance to be picked at 1.
Yeah.
Well,
So it would
the
be
chance of the area under it, and the area under it is 0.
Yeah. No, the area under it is 1.
No, but like
it's gonna be a 0
from
width
1 to
and
1.
infinite height, equaling making it an area of 1.
Oh, yeah, that is
no,
right.
but
Zero
even
to
if you
infinity
put
is
in
indeed 1.
even if you put in t, like with a limit of t goes to infinity, because you integrate from 1 to 1, like you're gonna subtract the same thing that you have at the start, which means it's always gonna be 1 or 0.
Again, like the shenanigans of misreading data are just.
Yes.
If you want to learn more about information theory,
Taking wrong data is much more. Yeah, wrong data is much more fun. Doing data wrong is much more fun than doing data right.
Yep.
Unironically based.
Yeah.
Just purposely fuck up your data for shits and giggles.
Based.
I say that as someone who got a passing grade for a physics paper where my conclusion was, well, I didn't know anything, everything's wrong, but it's a learning opportunity.
Based. Okay, so I will now go ahead and go to 13. Confidence intervals.
Oh,
So, about confidence intervals.
Finally, we'll get to use the second table.
Yay.
Yes.
No, not yet, I think.
So we have the critical value.
The second table is used for confidence intervals.
Yeah. So the chance of z is being greater than or equal to a given value, or of a critical value is p. So basically, the chance of it being bigger than, in this case, 1.645 is equal to 1 in 20. Yeah. Cool. Suppose your scale weighs with standard deviation of 0.5 kilograms. Suppose one person, 3 measurements give this, which is a 99% confidence interval for this person's quote-unquote true weight. So, let's see. To be fair,
Would
this
you
is
calculate with the measurements, calculate estimators for the mu and the standard deviation, and use that to fill in the thing there?
So the thing here is they are converting it to a standard normal distribution. So here we have the input data, which is 70.03 plus or minus, and then we have the interval. So here we have let's see, what was it? We have a 99% confidence interval. So then we want to work with
0.005.
Yeah, and that's because you can get left side and right side. So because it's a two-sided system, we want to have 0.05 at the left side, 0.05% at the right side. So then that's why we take this one, and then we just have plus or minus that on both sides, and then these two are normalize it. So times.
Sigma. divided
Why
by
is it
square root of n.
times sigma divided by the square root of n?
Because normal distribution? Question mark.
Oh yeah, because so it's like
Mark.
yeah, fair.
Yeah, yeah, because that's what you divide the difference by to normalize it.
Yeah.
Right.
Okay, fair.
Again, this is one of the formulas you have to know.
Yeah. There we go. So the chance of your average being like, so basically what you're saying is the chance of your average minus the critical number of your chance divided by 2 times, you know, this factor that we just talked about.
Yeah.
Is being
Normalization.
less than or equal to the actual average or the actual expected value. Is being is less than or equal to your average plus the thing is equal to 1 minus your value a.
Yeah. Or in otherwise, the probability that your average is within the range of this like value, which is like the critical value times sigma divided by square root of n, is equal to a certain probability. So like, what's the probability within that range of the real value?
Yeah. And just actually check this out, right? So I will work this out a bit. Oh no! Ah. So we have, oh god. There we go. So we have p of bar x n minus z a divided by 2. Because a is alpha, you know. Sigma over square root of n is less than or equal to mu is less than or equal to yeah, seems correct. And then this closing bracket, and this should be a plus. Where is my? Oh, there it is. I'm gonna make it a little bit less zoomed in. So, yeah. Okay, so what this is actually calculating, and I'm going to do this on a whim, so I've not like prepared this or anything, but let's see. I'm going to subtract this value from both sides, this x bar n. Okay, and then I'm going to divide both sides by this mu, or this sigma divided by n squared, or square root of n thing. There we go.
Yeah.
Whoa,
which is basically just the.
And now it makes a lot more sense.
Stuff.
So this is basically just the standardized,
normalized,
the normalized standard distribution type thing of this value by the law of large numbers, and then you just take these values. Yeah, so you're basically asking, okay, how confident am I that it's between these values? And this is equal to 1 minus a. And you can also have like the one-sided interval, in which case it's just, for example, would be this. Cool. So that's where this formula comes from. In the above situation, it's a realization of random variables x1 and well,
That's
yeah.
gamma.
Okay, a gamma is 1 minus alpha. Then this point, so the left side and the right side is an interval. So you can be between the left side and the right side, and that's the interval that we are 1 minus a% confident that u is in there. So here, basically, what we say is, here we are 99% confident that that the actual average is between this thing minus this value and this thing plus this value, times that one weird scalar thing. And this is like an interval. So this is. I kind of hate the way they noted it down. I would write it down more like this. So. Forgot a closing bracket. So this makes it a little bit more clear because I didn't understand the question. It's from this point to this point. That's the interval. Okay. Let's see. So
It
instead
assumes that
of
we know what the variance is,
Hmm?
or like standard standard deviation.
Standard deviation is the average difference from the expectation. And
Yeah, but I'm saying that we this previous formula assumes that we know that.
Yeah, and if we don't, we can just take we just calculate it like the
Studentized mean.
quote unquote standard deviation from our sample, and because we don't know the actual standard deviation itself, we can just calculate what it is for our sample.
Yeah.
No, but it's a different formula if you're doing the so-called studentized mean.
Yeah, the studentized mean actually takes like the sum of stuff.
Uses the t distribution instead of a normal distribution.
Yeah, it uses like for that you need to know n and stuff, but you also kind of do that for that formula. So it just depends if they give you a sample standard deviation or sigma.
Also, if n is larger
how
than
you
50,
use it wouldn't
then...
change, right?
Sorry, what?
How you use it wouldn't change, right? You could still say that
No, because it's
xn
different
minus
values.
za over 2
No,
of
but because...
sn over square root of n.
No, but when you're doing the studentized mean, you're not using z alpha half. You're using t alpha half n
Yeah,
minus
because
1.
you're not using
It's a different...
the normal distribution, you're using the student
Yeah,
distribution.
exactly.
But apart from that, it's exactly the same, right?
Exactly. Yeah. Sure.
Because a normal distribution is just a student distribution with t infinity.
Yeah.
Yeah.
Which is
N
also
infinity.
why that's the row in the table on the formula sheet where it is.
Yeah.
Yeah.
It's kind of like what would they call it again in calculus? Taylor series.
Sure.
Yeah, so you get like an estimation that's better until it's like perfect.
Infinity, yeah.
Yeah.
And you can also even like look these up in the table to the left, right? These infinity values or not?
Yeah. Yeah, it's faster.
Yeah. So like for
Also,
example.
Also, if n is larger than 51, then you can just assume a normal distribution.
Yeah.
If n is larger
Since
than
it's
51,
large
you just assume n is infinite.
Yeah.
Yeah, it's basically the same
It's
thing.
basically the same. Like,
Let's write a bad proof to prove that.
yeah. Are your parents 51 years old? Sorry, they're infinite. Sorry.
Yeah, but
Yeah, so you see how this table doesn't go above 50? Yeah, it's
sorry,
infinite after 50.
Your parents are the concept of infinity now.
They've transcended physical limitation.
Yeah, your parents are imaginary. Ooh.
Okay. I am.
Okay. Confidence interval
Can be
for the mean of a
imaginary
normal
and
distribution variance
infinite. You can have infinite I.
Same thing.
Let's see. So, yeah, this again, instead of using the critical value of z here, they're using the critical value of t of n minus 1.
And -1 comes back again
Also,
to bite us in the ass.
Exactly. Yeah. That's an important thing to remember. The degrees of freedom are n-1.
Yeah, so if
always.
we have like 6 things, we need to look up we're like
P5.
yeah,
Yeah,
n is 5.
5 degrees of freedom.
Or m is 5, yeah.
Yeah.
Yeah. But yeah.
As you can see, this can be rewritten
Wait,
as, which is like literally what we just
guys.
did.
Guys, so 51 is technically still not infinite.
Exactly. So it's
52
larger than 51, yeah.
And you know what 52 minus 10 is?
No, but like as soon as you turn 51, you're slightly older than 51 years old. Because you're like 51 in a couple of minutes, so you're already infinite.
Yeah.
Oh,
The moment your age even approaches 50 from the left, you're fucked.
Yeah.
Or from the right, if you look at the number line. Yeah, you're fucked. You're infinite.
But like after you're 13, it all turns downhill anyways.
Okay, suppose we have the independent distributed parameters, blah blah blah. So then we have this. So this is basically saying the same thing, but then with realizations instead of instead of just the actual numbers.
Yes. This is the same thing.
Yeah. Okay. Cool. Cool. Ooh, confidence interval for proportion.
To be honest, I don't remember much of that.
Yeah, it's a different formula, but it's like it's basically for binomial instead of normal distributions.
I see. This slide is a little bit more formula heavy than the other ones.
Yeah.
Like,
but wait, can you go to the formula sheet again for the binomial, because P1 of P is the variance, so it's literally the same formula, just with variance as it's the same formula, just
with variance filled in.
Yeah.
Yeah.
And then this is the quote unquote chance. So this is like the expected. Yeah. So this is our x. This is our x and
Yeah, it's the same formula. It's just changed clothes and put on some makeup.
Exactly. Determining sample size.
But also because of binomial distribution, you often get like. Oh wait, no. You often get like like a binomial expansion you have to do, and then you can just use the quadratic formula to get like either the lower or the upper bound. Not often when you apply these formulas.
Fair.
So remember the quadratic formula. Like the joke's always, oh, I don't need the quadratic formula anymore. You do need the quadratic formula. It's actually quite useful.
Yeah, like I think the quadratic formula
So minus b plus or minus square root b squared minus 4ac over 2a.
Yeah. I think it's literally the formula that I've used most often.
Yeah, exactly. I was about to say,
of my life.
It not necessarily reflects to remember it, because literally everybody here remembers it. Like, I am willing to bet that at least 95% of people in this in like the university remember the ABC formula.
Bro, you can't pass if you don't know it.
Exactly.
I'll be honest. I think Pythagoras might be used more.
Well, yeah, but
not in computer science.
Not really for us, because we don't really do trigonometry.
We've almost never done
yeah.
trigonometry or anything like that.
Yeah.
Not in computer science, but like
in general.
Yeah,
sure.
Yeah. In like a lot of engineering, more focused stuff. Yeah, obviously. And I love 3D trigonometry. It's so much fun. Anyways, back to statistics.
Well, yeah, this is just this is literally what we're talking about. So it's like the margin of error. This will just be like our mean from our sample plus or minus the critical value times the sample standard deviations over the square root of the sample size. This is just the formula that we've seen 20 times so far. just written again. Cool. No.
Time for the fun part.
To be fair, everything after that, like, there's what, 5.
Yeah, I
then
mean
a
we
few
could.
more.
Yeah, we can. I mean, we might even finish lecture 14 today. Then we have barely anything left tomorrow.
Yeah, I think we can finish in an hour tomorrow. I
And
can't
then
like.
maybe do an exam or something.
Yeah. Okay. Suppose you have constructed a 81% confidence interval to estimate sigma. Sigma? Theta. This individual sigma balls confidence
Sigma
interval
theorem. All
has an
group letters are
81%
sigma.
probability of covering Huh.
No.
I think actually this might be.
False.
And why is that?
It's false.
The confidence interval tells you how often, if you repeat it, how often, if you repeat it multiple times, what proportion of it is gonna contain the real value.
I see. Cool.
Not how likely stuff is going to appear in that value, in that range.
Yeah.
Like the other way around, basically.
Okay. Oh yeah. Well. Okay. So here we have the average minus the actual average over the studentized mean, or over the studentized standard deviation divided by the square root of n, which is just it follows the standard normal deviation distribution. Wait.
No.
Oh yeah, because there's an s here instead of
yeah.
Fucking hell.
Gee.
I hate the fact that we're working so much with like the actual value versus what we think the value is, and then there's like 20 different fucking names.
Yeah, a massive difference between the two of them.
Yeah, indeed.
It's so weird.
You have to construct 80 confident intervals, capture the value of sigma, theta, and I keep fucking it up, man. I swear to God.
Yeah.
And each is constructed at the 95% confidence level. So then 5% will not contain them. However, let's see. Yeah, 2.5 of each percent. So 5% will not contain them. 5% of 80 is 4.
Just don't bother calculating. Just do 0.5. Yeah, or just write the number.
Okay. Suppose distribution follows the standard normal distribution. The critical value can be derived from the right type probability, which can be computed as follows. The critical value is z of p. So this is the standard normal distribution, this is the critical value, and this is the chance that belongs to that critical value. Okay. Suppose, suppose you construct a 97% confidence interval. From this, it follows that significance level alpha is equal to 1 minus gamma, which is 0.03.
Over 2. Yes. No, never mind.
I was about to say, on either side it's over 2. But the whole thing is just this, yes.
Yeah.
Okay, next one. Suppose you take a random sample from a normal distribution. This thing has a... well, I mean, this one is true as well. But they want to know this one. But this one is true as well.
Well, theta and sigma, mu and sigma were predefined. So they're not generic.
Oh, yeah. Anymore. Yeah, damn it. I didn't see that they were predefined. That's fair.
Yeah.
Okay, cool. Next one. Woo! Okay, so these are practice questions. So we are actually doing the right ones. Give me about 10 seconds. I'm very aggressively clicking something. And the aggressive clicking is done. Thank you very much for your waiting. Practice now. Okay, suppose you're giving the following information about the critical t-value. What are the degrees of freedom? 46.
No.
What?
No,
No.
no, the
45.
degree of freedom is actually n
46
minus
is
1.
the sample size.
Yeah, that's true. I messed it up. That's my bad. Which follow? Okay, the degree of freedom is sample size minus 1.
56, which is basically infinity.
Compute the upper limit for this. Okay, this
Well,
is an
this is
80%
not
confidence
interesting.
interval. We only need the upper limit, so we will use a 10% critical value. So we want to have P of. Oh, it's actually given. Lovely.
Yeah.
So we have P of.
They like to give everything, so yeah.
So we have 82.
You can't just do the formula though.
It's P of. T.
Why don't you just use the formula?
Yeah.
Why are you doing P of something? Just use the xn plus z alpha over 2 times sigma over root n. You give all of those, you can't just use the formula.
That makes sense.
Just put them in. 82, yeah.
It's 88 over. Yeah. Yeah, I was gonna like do this, but you know, you don't have to. It's the lower limit. Oh no, the lower limit. That's so hard. So here, instead of having p values or like critical values, we use the t value, which is like this.
Functionally the same.
Which is functionally the same, indeed. 12 over square root of 30.
Where is the 80%?
They already gave us the
critical value.
Yeah, the critical value, or the t value, or whatever it's called, and because they already gave that, like usually we could look it up in the table, but we didn't have to because it was already given.
Okay.
No.
Yeah. What is significant level A? And this is a two-sided test, so that means it's 0.03.
No, wait. That significance level, not. Oh wait, alpha. Never mind. I was stupid.
Yeah, you were thinking about gamma.
Our significance level, you must be meaning the critical value.
I mean, the critical value itself is
based off of it, but not it. Also, we couldn't even calculate the critical value from it because we don't have 52 in the table. 52 is basically infinity, as we stated.
Exactly. Essentially.
Ooh, okay, so this is an interesting one. This is basically the same of this is basically asking the question we did before, but now we have to look up the value ourselves.
Yeah.
So I'm going to delete this because I don't want to cheat.
No peeking.
So we want to have the lower limit, right? And what that basically constitutes is the average minus p is, or what is it, z of p times the fraction of 112 over square root of 30. The thing is, we need to calculate z of p, the critical value. And to calculate this critical value,
you just read it off the table.
Yep.
Read it off the table. Read it off the table.
And because it's actually, let's see, so we have n is 30. We want to have the 90% confidence interval, but that means we have 95. So, or sorry, we have like 10%. A is 10%, and therefore A over 2 is equal to 0.05. So we can use 0.05 with n minus 1 degree of freedom. So 0.05 with 29. Ha!
Nice.
Nice. So
better than 1.96.
I fucked up. It's 1.699.
Nice.
Check my answer. Let's go. Okay, that was easier than I expected. Like I looked at this thing, I was like, no, and then I did it. I was like, oh, that's easy.
This is like this. I like this formula. It's easy to apply.
Yeah. Let's see. We have 30 sets. They weigh 80 grams each. The average weight is 82. The sample standard deviation is 34. You can assume blah 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 blah. Compute the upper limit of an 89% confidence interval for the expected weight of a set of tools. So that is what we got, which is 34. No, 82. My bad. Plus, and then the number that we will calculate in a bit, and then times the fraction of the sample standard deviation 34 divided by the square root of 30, and then we just have to calculate the critical value. However, let's see. Yeah, it's just a two-sided test because that's given. Because that's like, that's what you assume.
Yeah.
Unless something else given. Still recording. That's good.
0.02.
Yeah. So
0.01.
Yep. So we take n minus 1, and we also take the 2% here divided by 2, so it's 1% and 29, which is this one, 2.462. 2.462. There we go. Oh wow, it's just gonna be this a bunch, huh? I don't mind.
Yeah, it is. It helps you remember the formula.
Exactly. So for a second I thought that like they said that the average was this much and we got an average of this much. I was like, nah. Compute the upper limit, so that is what we got, plus our cool number times the fraction of our sample standard deviation. Or well, in this case, yeah, this is the actual standard deviation which is given. And otherwise we could have calculated the student dice sample thing. The water should contain 750 milliliters. Alright, wait, I can take the square root of the sample here. I'm not sure if the water bottle should contain blah 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 is actually like relevant at all, but we'll see.
No, not really.
No, that's what I thought.
That's kind of like what you want.
Exactly. So we have infinite degrees of freedom. It's not infinite. It's more than 50, so it's infinite. And we have we need to find the.
And also you give them sigma.
Actually, it might be.
So you give them sigma, not as n. So you just straight up assume you take infinite because otherwise they give you sample standard deviation and not sigma.
Yeah. You're right. So then we have. The thing is, I'm thinking this might be relevant because it might be a one-sided test now instead of a two-sided test. However, no, that's bullshit. So,
it's the same thing still.
Herring?
Hmm?
Isn't it just a giant red herring that water bottles should contain?
Yeah, it is. So, let's see, this is 1%, and we need to have the 0.05.
The 1%.
Or 0.005. And then we take this one to the infinite, and then we have 2576. Then we have times 25.
You were so close. 576, not 67. I know it's annoying. Why can't it be 567? Why does it have to be so close yet so far?
Yep. Okay. Next one. Pog. So this is our average plus square root of plus the fraction of standard deviation times over the square root of our number times, and we have 99, which is infinite, and we have a 1%, so infinite 1%. Let's see, 1% infinite. 2326 times 2.326. If you told me I would be greening on this fucking lecture, I would have told you.
Okay, before you do any formalization, just look at the.
Yeah, compute the sample mean for this data set.
Wouldn't that be the average? Or the,
it's just the average of the upper and lower limit of the confidence interval. That's it. It's just the average of those two numbers.
Yeah, it basically to make you truly realize that the interval is a number plus or minus something else.
Yeah.
So we could just say 38.
Man, why can't we use browsers, the browser calculator in the exam?
Yeah, you can just paste shit and it works.
Yeah.
Okay, back to lessons. So that is the. Wait, that was all 3 of them already? Huh.
Yeah. Now one-sided.
Okay, so we have, let's see, 1, 2, 3, 1, 2, 1, 2, 3, 1, 2, 3, 4. Wait, these are just the same thing. I'm only gonna do one of them. So that gives us 1, 2, 3, 4, 5, 6, 7, 8. 8 to go. This is not too bad.
Yeah.
And it's only 4 o'clock. We still have like, what, 2-3 hours before I have to go eat?
In Mirror, is it 3 o'clock? My PC is installed wrongly. So
Yeah, your
what time
PC is installed wrongly. Congrats.
Yeah, you have the wrong time. Go fix your time.
Your PC is British.
Yeah.
Shit. Just like your wife.
Someone needs to update their clock.
Synchronize your clock. Sync now. 4:06.
Oh,
Yeah,
sync,
it's
not
better.
sing.
Okay. If you have sample statistic ln such that the chance of ln is less than 0 is equal to your confidence interval thing for every value of parameter of interest theta, then ln to infinity is called the either the yeah or
Being my Steam folder, 875 gigabytes. See y'all tomorrow.
Okay.
That might be the socks. I'm gonna be honest.
Yeah, like this one, I didn't even think about this one. It's just like they are using the letter gamma, and gamma is what they would place here. So it definitely could have been this one, but like it would have been really sneaky.
Yeah.
Anyway, how do you formulate the 100% upper confidence interval? So we want to be 100% sure.
No, it's not about being 100% sure. It's 100 times gamma.
And gamma is like 0.9 or something.
Yeah.
Oh yeah, okay. So I've got this gamma in there.
That's the
So
logic.
this is basically the 1 minus a. So this is like the percent that we want to have for interval.
100% confidence interval in reality can't exist.
Yeah, well, yeah, it can. Minus infinity to infinity.
Yeah.
Yeah.
It doesn't exist. It's right there.
It's right there.
That is the same as a 0% confidence interval.
But yeah, how do we formulate an x upper confidence interval? Well, I mean, you know, if it's between the lower part and infinity, then
the last one. Yeah.
If it's
between. Showed us this in the last one. Oh, wait, what?
Yeah. It's an upper.
Oh yeah, okay. Fuck off.
The last was the lower limit, and also it has UN in it.
I see. Makes sense. But this means we basically like 100% of the time it will. This will be
below that number.
Yeah.
100% of the time it works 96% of the time.
Exactly.
100% of the time it works 100 gamma percent of the time.
Yeah. Suppose you're given the following 95% confidence interval. However, you're only interested in the probability that lambda is above a certain value, so you decide to calculate the 95% lower bound confidence interval. What happens to the lower bound if you compute a one-sided interval versus a two-sided interval? Well, the thing is, right now you only have 0.25 or 2.5% of leeway on both sides. However, if you do it this way, then you have 5% leeway on the left side. So this one will be lower. If you have a one-sided interval, it will become lower versus a two-sided one.
But it becomes higher because their terminology is weird. It's
the lower bound
so it becomes higher. I think. Oh wait, no, because you put all the confidence on the left side, so it can be closer to the actual value. So it becomes closer, therefore higher.
Or geometrically, you can think that you have like two areas, and you take the area from the right and you glue it to the area to the left.
You shift it by alpha over 2, basically.
Yeah. I see.
Either the right or the left. That's essentially what happens.
Compute the lower bound of the confidence interval. Give your answer in. You want to calculate the one-sided lower bound confidence interval. All right. So what we do then is we have 10 minus 3.4 over square root of 22 times, and they've already given.
Yeah.
Yeah. So this is just. Like this is the lower bound of the confidence interval of 95%. Yeah, this could also be the lower bound of a two-sided interval of 90%, but you know it's one-sided. So
I mean, this is 90%. Oh wait, no, it is never. It is not. Never mind. I'm stupid. Forgive me for my sins.
Isn't this the same question that we had before?
Yeah.
Cool.
They sometimes repeat the ones you got right as well.
Fair. How do you formulate this percent upper confidence interval? So from minus infinity to the upper.
Yeah. And because we repeated one, we're gonna get. Wait, what? How did you get 2 wrong? Oh yeah, the one. Oh yeah, we got that one wrong.
Okay.
Suppose
you're given the following interval. However, you're only interested in probability. That is. Holy shit! Hey, is this literally the same question?
Yeah, I think you clicked on do again.
Yes.
I think so too.
You clicked on yeah.
Practice.
Okay. You want to be 99% certain that it's lower than a certain value, which makes sense because this one is 0.01. If it was on both sides, then it would be 0.005.
Yeah.
So it's 70 plus fraction of 15.8 over 4 times 2.62.
And I thought you simplified root.
And that's it. That's it. We're done.
Root 100 to 10.
That was fast.
Wait, sorry. Can you just come back to it? I zoned out for a second.
Maybe instead of
man zoned out, missed the entire exercise, the entire part. So we're asked to calculate the upper bound of a one-sided confidence interval. Give your answer, blah blah blah. So this is basically, you know, as we know the formula by heart at this point. If you because you guys are not writing this down, by the way, I was writing this down on a piece of paper a few times or do these exercises.
Write all the formulas down on a piece of paper and just rehearse them. Learn them, and then don't take the thing with you in the exam. Just know them, and when you start the exam, when you're allowed to write stuff down, just write them all down.
Yeah, that's actually what I do for most of the stuff where I have to remember things. I just go really hard at them, and then I write them down, and then I just like forget them the moment the exam starts.
One time we had like a guy at our school who was like, "Oh, this is how you can learn effectively," and apparently, he did like for his history exam, he like learned the entirety of like all history as like a diagram, and then just drew it down. Which is like,
yeah, and then
you get a sad move.
But yeah, so for basically,
honestly, fuck history.
Yeah. Okay, yeah. It's just I got like I literally zoned out. Yeah. I know the formula. Just
cool.
It in. Wow. Yeah.
Next subject.
It's just I zoned out and I heard we're finished. I'm like, wait, what?
Okay.
Not with the entire thing. We're not that good.
I know, but like still.
So they're asking about the minimum sample size. Oh, that's here. Sometimes an accuracy requirement is set, the maximum width of the interval is fixed, and you have to determine the sample size to achieve the requirement. Well, okay, then it just makes sense. We're basically just transforming the formula. So, yeah, you know, we are given this, then we can just calculate. Wait, can I just... No.
No, it can't be this easy.
It can be. I don't think this is this easy, but it might be. Wait, no, actually this might be a fractional number. No, oh fuck. Wait. See if Wolfram Alpha really is that good. Yeah, so the answer is 97.
Yeah.
Yeah, that's the trick. True.
Yeah.
There we go. That's
the annoying part. They're like,
Gotcha. I mean, to be fair, if I asked
thought
someone
you
how many
could just
times do I
copy
have to
and
do this,
paste,
and
but
they told me 96.04, I'd also fucking get pissed off at
I
them.
think the smallest sample size would be X because it's it's less precise.
Let's see. You have two random variables. Both follow a normal distribution. You want to construct a 95% confidence interval around a mean with a maximum width of 2. So again, we know the width of the confidence interval.
Right, but
question
it's
is-
affected by the variance.
Yeah.
Right? So the bigger the variance, the more data you need.
Let me write this down because
We
know
the
that
smaller
like
variance,
the
more
confidence
data you
interval
need.
is a number C
Oh, wait,
plus
no,
or
it's the opposite.
minus
Well, times, okay.
P of Z
Just
times
forget what
fraction of sigma over square root of n. And this is like the confidence interval. And if we know that the confidence interval has a size of 2, we know that this right side is equal to 1. Because if you have any number and then you go 1 to the left and 1 to the right. So if we have a bigger, and also the PZ is written in stone. Actually, that's not true. But if we have what requires the smallest sample size, I'm actually going to divide by the square.
Actually.
I'm actually going to multiply by the square root of n, and then square both sides. So the square root of n, and this is not exact, of course, because I just striped away some constant shit. But these two are the only things that are reliant on the variance. So a higher variance will mean a higher sample size. Therefore, a lower variance has a lower sample size.
Yeah.
There we go.
Yes.
Because for a higher variance, it's more spread out, so you need more points of data to encompass the same like breadth of data, if you know what I mean.
Yeah.
I think per unit it's about the same. So it's fairly linear if you widen your thing, margin of error. No,
Yeah.
something like that.
Suppose you have a random variable x which follows this distribution, and you want to compute the required sample size for a 95% confidence interval and a 99% confidence interval. Both intervals cannot exceed a width of 3. What happens to the required sample size when we compute a 99% confidence interval instead of a 95% confidence interval?
Your screen's scribbling again.
I will restart my stream.
Well, I mean, this question is fairly obvious.
Yeah. So like we've already written this down, right? So let's see. The thing is, the only thing that matters what happens with it is the P of n, and we want to know if we have a higher, or in this case then a lower a, because we have a higher gamma, a lower a. What happens to the thing? So a lower a, then the number becomes bigger. So this thing becomes bigger, and therefore n becomes bigger. So it's a.
Oh, it goes from 95 to 99.
Yeah. So a 99% interval has a lower number, or a higher number than a 95% interval. So we go from 99 to 95. You go from the higher number to the lower number. So it becomes.
No, you go from 95 to 99.
It's going from the small
from
to the
95 to 99.
Oh.
99 instead
okay,
of 95, not 99 to 95.
Yeah, it's
tricky.
It's just
they're
a
very
weird wording,
tricky.
so then it increases.
Yeah.
Yep.
Which makes sense because now your data only fits into a slimmer margin, so you need more data to get the same amount of data within that margin.
Yeah.
A lot of those you don't have to, for the sample size thing, you don't have to calculate if you don't need it exact, you can just reason.
Yeah, true.
Mark needs a larger sample here because he wants a smaller width.
Let's see. Emily wants a 95% confidence whose width cannot exceed 4. Mark wants a 95% confidence whose width cannot exceed 2.
He wants a smaller width.
So if I go
more data.
Yeah.
So we have here, if we have a bigger width, that means there's going to be, oh yeah, so we have like, let's say W for width, and square root of n here. I know you can also intuitively reason about it, but I want to be a little bit exact.
Like the more information you have, the narrower your window gets.
Yeah, so this W gets bigger, this square root of n gets smaller. So
yeah, like if you were able to get infinite amount of data, you would be 100% sure about what the mu is. So your confidence interval would be would have a width of 0. So if with infinite it has the smallest width, then the higher it goes, the smaller the width goes.
The bigger the width goes.
None of them. I just thought it said none of them both need a sample size n. Like, you just take an n, you know. They're you know.
Just take n.
Yeah. just look at n. It's not hard.
Trust me, dude.
Yeah. Okay. What's the correct formula for
Years
the
of
width of a confidence
statistics done,
interval?
yet no real world use found for n.
What's the correct formula for the width of a confidence interval? Well, we just discussed, right, how this thing was.
It's literally just upper limit minus lower limit, so it's 2 times the thing without the
yeah, exactly. Mean. So this is the interval. So we know the width of the interval is 2 times this thing.
Yeah.
Yep.
Also, I used PZ here. It should be ZP, not PZ.
Yeah.
P's Jack.
Yeah, I'm a little bit. I do a little bit of dumb sometimes, but it happens. So then we have 2 times this thing. Next subject. Practice question.
Practice question.
Suppose you want to test the volume of water bottles before they go into the store. The volume should be 500 milliliters. Based on previous measurements, we assume the standard deviation of a volume measurement is 14 milliliters. How many bottles would you need to sample to make a 90% confidence interval of the mean that is not more than 2 millimeters wide? And this is a 2-sided interval. So again, we know that 2 times this thing cannot be more than 2 millimeters. So, you know, we can just strip away the 2 here. Let's see, we have our n. Let's see, n is what we want to know. We know our sigma is equal to 14, and we have. Let's see. I'm going to multiply by the square root of n on both sides.
We're not given an n. Wait, no.
The only annoying thing here is like ZP is dependent on n as well.
How do you know if it's
no, it's not. It's not if you take infinity.
Oh yeah.
Yeah, so you just need the 0.05.
Real quick, somebody else asked a question. What do you say?
Yeah, where are you setting it equal to 1? So earlier, where you said that ZP times sigma divided by square root of n is equal to 1.
This thing should be equal to 2.
Equals 2.
Yeah.
But, like, you know, I can divide by 2 on both sides, right?
Wait, how do you know that it's equal to 2, though?
Because it cannot be more than 2 milliliters wide.
Oh!
And it's both sides.
Oh, okay, I see.
Like it's 2-sided, so you take the half of it, and the half of 2 is 1.
Yeah, no. I didn't see the 2 milliliters wide part.
Yeah, okay. Then it makes it a lot harder. I can understand that.
But why can you just take like the infinity?
Yeah, that's what we're doing. I didn't realize that they're saying like a standard deviation instead of studentized deviation.
Yeah.
And even if they would, you know, we're not actually sampling something, so we can just take infinite.
Yeah, I mean the purpose of finding the width, the sample size is so that you get one that is functionally a perfect normal distribution.
Yeah.
So obviously you want to use the normal distribution one.
So let's see, we have 9% confidence interval. It's 2-sided. So then we have let's see, 5% of this one. We go to infinite. This is the value. So then we have 1.645. We know our sigma is 14. And keep in mind, here they say the standard deviation, not the variance, standard deviation. Then I multiply square root of n on both sides, so then we get, instead of fraction, it becomes c dot. And then I square both sides, and then we get this number squared. However, keep in mind, you cannot just enter this. Oh, fuck. You cannot just enter this. You actually have to enter 5. Is it? Yeah,
5, 2, 3, 4.
5,
But
2, 4.
But again,
Yeah.
why can you take infinity?
Because we
We-
like you can only not take infinity when you have a like a sample size like n, and
Which
here
we don't have.
we do
We're
not
trying
have.
to find one.
Yeah, we are trying to find one, but we can just because we are here given a standard deviation instead of a studentized deviation. It's basically like it's basically almost as if we were working with a standard distribution and not like some kind of estimation of a standard distribution. So we can just take yeah, these values, and these values are also, by the way, like this is all for t tests, and is it or not t test? That's the wrong yeah, t distribution thing. And this one is actually for a standardized normal distribution. So this one already assumes like this one strives to perfection, to say it like that.
Yeah.
I believe it
And you
should
can
be
only
1, 6,
you can
4,
only
5.
calculate how many you need for a confidence interval using
Thank you very
a
much.
normal distribution, because if you have a t-distribution, then you don't know what the value is that you're multiplying it with.
Yeah, we'll make it a lot harder. So it's actually 531. Good eye for the person that just said that. We just got that. So what is the sample size? So okay, this is the maximum width of the interval. I'm going to write down the formula again. So we get 2 times z of p times the fraction of sigma over square root of n is equal to the width. So we compile. Oh, it will complain probably. Oh, it didn't pog. Okay. And then this width is equal to 0.5, or basically 1 over 2. Multiply it by 2 gives me 4 here. Let's see, this ZP is actually Z A over 2 in this case, which is 2.325. The sigma here is given to be 4. I will multiply both sides here by the square root of n. This will give me, there we go, and I will square both sides, which will give me this whole thing squared. And that's going to be our estimator for n. Or, well, it's not an estimator, but like our minimum required n. Did I fill in all my values correctly? I think so. So 1384. There we go. Oh, Pog. Ik voel me echt een
Wait,
wiskunde
does
steer,
LaTeX have
jongen.
a stealing function?
Hmm?
Does LaTeX have a stealing function?
Yes. Like this?
Yes.
Because then you could just say the ceiling of the
I don't
value.
think Grasple recognizes it though.
Okay, yeah, fair enough.
I think it's like this. I'm not sure though. Let's have a look. No, it doesn't. Then I don't know. But yeah. You assume the time it takes to make challenge from a normal distribution, variance to this thing, challenge need construct blah blah blah, minimum width blah 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 blah. So it's 2. Good, it's 2-sided, yeah. So then 2 times the fraction of let's see, the variance of this thing. Oh, the variance of this thing divided by the square root of n is equal to 0.5, and we also have to multiply by the p of z, z of p. We want to have a 95% confidence interval, so our a divided by 2 is actually equal to 0.025. We are not giving a sample size, so I'm going to assume infinite. 0.025, infinite is 1960. So we get c dot 1.960, c dot. Let's see, okay, now I'm going to multiply both sides by 2, which will give me 1 here. I will multiply both sides by the square root of n, which will get rid of this fraction for me. And then I square both sides. Teachers should be writing their shit in LaTeX. Change my mind.
Yeah.
I think most of them
Everyone does.
do even.
Nice.
I mean,
Oh no, it's 70 though. Oh no.
No.
No. What?
What?
Oh,
Try 69 anyway.
Damn it. Okay.
Oh.
Establish Z of A over 2. So I think I fucked up my.
I think I fucked up my soup.
I think I fucked up myself.
No, this. So 1.960. This one's
Is it
correct.
two-sided?
Is it the good one? What's the confidence you want?
Wait, why is it 0.025?
95%.
Oh yeah, 95. Sorry, I thought it was 90.
Yeah.
It should be good.
With a maximum width of 0.5 minutes. Oh.
Maybe it's like a second to minute thing? No. I don't think so.
Don't make.
What do you?
Yeah, that would
You just skip
be...
it?
Yeah, it says in minutes. So it should all be minutes.
Motherfucker makes a challenge on the e-learning website take half a minute. What the fuck? Oh no, okay, never mind. It's yeah, okay.
Oh! Variance 1.06. Not
Yeah.
standard deviation.
Ooh, fuck.
Oh, you square root. Ah.
Fucker. Fuck.
Ah.
I even warned people about this one multiple times.
Yeah.
What was it?
It's a variance, not a standard deviation.
Isn't standard deviation? One is the other squared. I don't know which one.
The variance.
Variance is the square
it's the
of
one squared,
STD.
standard
Yalla,
deviation
Which
is
one
the
is
not
sigma?
Standard
Everyone gets
deviation.
it at the same time.
Okay, clear.
Yalla.
Standard deviation.
Yalla.
Yeah.
Normal distributions parameter is the variance, and it's sigma squared, and sigma is the standard deviation.
Yeah, var x equals
Yeah,
sigma
var
squared.
x is
It's
sigma
literally
squared.
said there.
Yee. Okay.
Cool.
Yeehaw!
So the variance is without the square,
So
right?
should it be then 66? Yeah. Okay.
Yeah.
Execute order 66.
I did this one already.
Literally
Wait,
already.
Yeah, have we done this one already?
Wait, guys.
Yeah, and the answer was something maybe I don't remember. Yes.
I
There
think
we
this
go.
one. I think this one.
Yeah.
Let's go.
Let's
Let's go.
Imagine
That's smart and
memory.
not harder.
No way. Imagine memory.
Okay.
You have to do it again now. To get
Next
the
subject.
all.
No, fuck you. I'm not
Should
doing
you all
that.
green percent? Should you all green percent later?
No,
Yes,
please,
otherwise the
God,
speedrun is
no.
not complete.
It's gonna turn the speedrun to
Okay.
14 hours.
Let's see. I mean, to be fair, once you've done it once, you can just copy the answers. Green percent does not take.
Yeah.
I'd say green percent takes like 20 to 40% longer than knowledge percent.
Yeah, we can't waste those frames. We have to.
No, exactly. That's a time waste.
Frame perfect run.
Listen to me. I think what this speedrun should be is blind. You should this speedrun only counts if you're doing it blind.
Yeah.
Oh
You know
yeah,
what I
so I
mean?
should just turn off my monitor and start mashing on keyboard until I
that's
get the
not-
answer.
No,
Yeah.
put a big
No,
fall
no,
on. Put a
that
big
one I
fall
can
on.
approve of.
You know what? We're gonna direct your mouse, and we're gonna direct you. Just put a blindfold. We'll tell you what's on screen.
Put a big fall on and turn on your screen reader.
No,
Should be fine.
This is a great idea, you guys. You could tell me what I need to enter, and I enter it, and I can
Oh,
just press
yeah.
enter. Okay.
I've never heard a better plan.
Okay. So this one is still literally just as easy. So this is just 2 times the p of the z of p times the fraction of let's see, standard deviation of 10 over square root of n is equal to 5. Our zp, well, we are not given anything like that, so we have to assume infinity. And let's see, we have
That's my favorite kind of
99%,
infinity
two-sided,
is
that's
infinity.
0.05. Or, yeah, 0.005. That's 2 points. So in this case, it's c del 2.257. Is that correct? Oh, that's 5.6. Wait, I wrote it wrong. It's 2.576. Yes.
Right there?
Numbers get a lot harder the longer time goes on. This becomes 2 over 5. And this is Cedal again. So then this becomes 1, then I multiply everything by the square root of n. It's almost as if this stuff is very repetitive.
Yeah.
I don't
I mean,
mind
it
though.
helps you learn it probably, yeah.
I
It
mean,
just hammers it into your brain.
yeah, I mean, to be fair, I really don't mind that it's this repetitive because it's just like... Like, I was really, really afraid of this part of the Grasple speedrun, but it's just literally all the same.
First I was afraid.
I was petrified.
We are not doing stand-up singing in my...
You by my side.
Well, you've got the wrong group in this chat.
You got the
But
wrong
then I
group
spent
to
so many
remind me.
days thinking
At
how you did it
first I was
wrong.
afraid. I was petrified.
No! You restarted! No, you should have kept singing.
Okay, guys, there's a bit of an issue here. They are wrong. They say round your answer to the nearest integer, which would have been 106, but the answer is 107.
Yeah.
That's an implied roundup.
Yeah, well, it's not. It's like implied, but you know, fuck that. Okay.
Yeah.
Ooh, okay. Compute the sample size that is needed if you want to construct a 99% confidence interval. The interval is not allowed to have a width that exceeds... I'm thinking of maybe like thinking more about what I'm about to write down, but I really don't. Right.
No, never think. Only
I
write.
really don't want to.
Thinking is bad. We don't do that.
So we have this is 5 is equal to it cannot exceed 1, and I also take the square root of n here. I just multiply both sides by the square root of n because I'm going to do that eventually regardless, and I can't be else. So then this becomes 10. Now this set of p is actually it's a two-sided interval, so we have 0.05. It's almost as if it's nice to learn these. 2576. 10 Cedal 2.576, and then we square this, and we're done. Okay. Am I still recording? I just check that like obsessively every few minutes just to make sure that I still am, because I once just didn't record for half an hour and that was annoying. So 664. Oh, 2 more, and I would have been edgy. Sad. Somebody sent me, but somebody sent me like a thing with like the formula already rewritten, which, to be fair, it's probably gonna be nice to remember, but I'll just like keep rewriting it because I'm very lazy. But yeah, like you could just rewrite the thing to be, you know, we're given this formula where we have 2 times z of p times the fraction of sigma over square root of n is greater than or equal to the width. Then we can multiply both sides by the square root of n first of all.
I mean, yeah, you can just rearrange, but that's like
divide both sides by w.
I'd rather just have to remember one formula and rewrite it than remember multiple formulas that derive from the same thing.
And square the whole thing. So indeed, like you can start remembering this formula and use this formula, but honestly, it's just I don't necessarily mind rewriting it.
But to be fair, I'm the guy who for fun after physics tests would try to like find like connections between formulas, like rewriting them to do something else and stuff.
Yeah,
which you can do a lot of times.
Ooh,
yeah.
A true/false question.
Ooh.
Suppose you investigated blah 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 blah. The answer is true. Damn it. It's false.
I mean, it's a 50-50 chance.
It would have been cool. It would have been cool. Yeah, you computed that the.
Technically speaking, you are you could say you are more likely to get it than not get it right, because you're given some hints.
Well, yeah, but I just kind of,
You
like.
didn't even read properly the thing. did
No, I
you?
didn't even read anything.
Yeah, right. So no, that doesn't work like that.
Yeah, that's right.
Come on.
Honestly, I disagree. It does work like that.
Damn it! I even get another one. Why can't it just give me the same one again?
You wanna throw hands?
Just skip until you get the same one.
wait, I want to see if that's possible.
No,
Yeah, of
you'll
course.
have to redo all of the ones you skipped.
Yeah, but then bam, false. Whoa, damn!
Let's go!
I'm so good at this.
But the other ones will count towards it.
It's like you want to know how?
I
It's
mean,
quite obvious that it's not, if
you did
think about
maximize
it.
your speed. You
But
did
you can,
maximize
like,
your speed.
Fucking, you can be like, hey, I have pulled 566 samples. All of them have given me the value 5,000. The constructed average is now 5,000. What is the 1% interval that the true value is in there? Or what's the chance that the true value is in there?
About a half.
I don't think it's very high.
2%, take it or leave it.
Ah, shit.
50-50. It is either in or it isn't.
Oh!
Don't forget to do the basics before the practice.
Yeah, I saw it. So we have a confidence interval for binomial distributions, which is basically the same thing, but you just replace the variance with the variance and the average with the average. Woo! Woo! God, this is university level math, ladies and gentlemen. Keep in mind, you are like one of the best universities in the fucking world, and you're watching some kind of like, I wanted to say 18, but I'm actually 19. You're watching this kind of 19-year-old do assignments on overleave LaTeX editor while they have their Minecraft coding tab open. Suppose we want to construct a confidence interval with. I'm literally playing RuneScape. I'm literally playing RuneScape.
That's
I was
you
gonna
don't
say
get
that,
it.
yeah.
That's the reason why this is the best university.
Yeah.
Based.
All because of you.
Also
thank
free
you,
programmer
guys.
socks.
And free programmer socks.
Yeah.
Free programmer socks does
Not
come
every
big fun.
university can pride themselves on having such unique socks, right?
Yeah.
I
And
hope
we're all
mine
pretty
arrives soon.
autistic and queer.
Yeah.
And I mean, TU Delft automatically gains like 5th place in the ranking just for having Stefan.
I hate to be a
Yeah.
gatekeeper, but if I have to be fair here, they are stocks for programmers. They are not, in fact, programmer socks.
Yeah,
That is true.
They're not programmer stocks,
Yeah.
but
They're
you know,
not like programmer socks. At least come to your knees.
Yeah, programmer socks are knee high.
Budget programmer socks, aka just normal socks.
And
No,
also,
no,
programmer socks have to be
programmer socks are
worn with a
completely different.
skirt. You don't. There's
And
no
they
clothes
have,
there.
and they have to be they have to be objectively cute.
True.
And yes,
Yeah.
that's very.
Can't be
progress.
programmer socks otherwise.
Yeah.
Let's go back to calculating confidence interval.
Okay.
I
The most
am
efficient
confident
way to
when I wear
program is
programmer socks.
in a cute fanboy outfit. Okay, like that has been scientifically proven probably
guys,
somewhere.
let's just
sometime.
go away from the fanboyish, because I know
Look.
like there at least going to be some conservative people leaving the stream.
Just automatically.
Goodbye to those people.
If you can't handle the programmer shocks, fuck you, log off.
Yeah, maybe.
Suppose you want to
Handle
construct
us
a
being
confidence
cute.
interval for the probability of success P based on the number of successes X. What the correct notation of such a confidence interval? This has nothing to do with the binomial thing. Whatever.
It's the left one.
Yeah, the chance of it being within these two
Yeah.
is equal to 1 minus A. Suppose you collected results from an experiment with 100 students who did or did not pass last year's statistics course. Damn it.
That didn't.
Real.
75%, 73 students passed the last
That's
year's course.
unrealistic. That's unrealistic.
That's not realistic.
I won't fucking measure.
The amount of students that passed is completely accurate.
Yeah, there's a sample size.
The total is just not.
Yeah.
One, I think. Oh god, I'm thinking back to the names.
Okay. I might just want to Okay. Let's see. The confidence interval, the probability of success, blah blah blah. This year, the same number of students passed the course. The same number of students passed the course, but this time we have 500 students. God damn. Like,
Divide this-
for the
divide
people who
that
don't
number
know
by
at
two.
home, right? This fucking course has a 38% confidence interval, and that's up from 2 years ago. That is up from 2 years ago. I was talking to in year 3, and I was like, did it really have a 38% thing? And like, oh wow, that's better than our 35%. I was like, what the fuck?
Confidence
Pass
interval.
rate.
Pass rate. Everyone knew it was talking about pass rate, dude. Come
I
on.
know. I was just like,
People pass.
Yeah.
You guys pass?
Clearly not.
If you smoke 5 meth,
You guys are getting passing? Wait,
if
no,
you smoke
that's
if you
fine.
smoke like 5 fucking kilos of meth before the first test and get like a 10 for that, it might be possible to pass the course.
yeah.
Yeah, like
Yeah.
I only need a 4.2, but
Maybe.
even then I'm not quite 100% sure I'm gonna get it.
What did you get on
Yeah.
the midterm?
I got like a
You're 42%
7.3,
sure you
I
get
think.
it.
I got the Bodhi
You're
number,
40
which is a reference only like 5 people will get in there.
Actually,
And literally no people who microdose speed for exams. EU. It's possible.
You can
You
see
guys
that we're at
know
the end of the
microdose?
stream because everyone's just talking about random shit.
Yeah. There's absolutely
Yeah.
no people who took drugs before doing this exam.
If you're not doing an exam higher, you're really doing an exam.
I mean, if you take drugs before SQT, remember, you've got like what? 3 hours to.
It just might work.
Like SQT in 3 hours, I'm gonna be done in 1.5 and spend the other spend the other 1.5 hours doing drugs. So,
I mean, SQT is only
That's
one
the
half
fun
hour,
thing.
so-
That's the fun thing. We're 18. We can actually smoke it now.
Yeah.
Soft weed quality and testing.
Soft weed quality and testing. Yeah,
Google
it's actually just a
is the
full course on
nearest-
the quality of weed.
Yeah.
I love
Google
it.
is the nearest coffee shop.
Guys, how about we go back to the subject at hand?
To the coffee shop.
University of
Technically,
Face.
that is impossible.
Good idea, good idea.
Okay, the same number of students passed the course. You want to add this year's student to the experiment, which makes total number blah 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 blah, which happens to the width of confidence interval when you add this year's student. So basically, we're looking at the same formula as before. When we add more total students, the width becomes
The confidence
smaller.
becomes smaller.
Yeah, because we had this
we
we
have
had this
more
factor
data.
on the right, which was like square root of n times w. Left hand stays the same. Square root of n goes up, w goes down. Which inequality needs to be solved to obtain a confidence interval for a binomial distribution. So, let's see.
The
The
difference
expected value
is-
minus the actual chance minus this thing times. Wait, what's the difference? Oh, okay. So here it is a plus, and here it is.
The bottom section has plus and the upper section has bigger.
Greater than, smaller than 0.
Greater,
Ah,
yeah.
yes. Okay.
It feels so weird. It's missing the fourth one where it's.
Yeah, no. You
Plus
see,
and, and
these two both
bigger.
have minus signs. These two both have less than. So this is the answer. Fuck you. If we're in a fucking statistics course, I'm going to be doing statistics on your ass.
Yeah.
That's not even statistics. That's just fucking exam strats.
Yeah, no. I've done this in exams before and gotten it right. Suppose we observe
I've
a
done it
random.
so many times, bro.
Suppose we observe a random variable x with a binomial distribution in an experiment. 30 observations are made. What scenario will lead to the widest interval? Okay, let's actually write it out now because. So we have this this thing, right? There's 2 times the p, the z of p, times the fraction of the sigma over sigma balls over the square root
I mean,
of.
I can already tell you something. It's not 0.5.
Yeah.
Buffer.
Actually, I'm pretty sure it is 0.5.
Oh, okay.
Is it?
It says which one has the widest interval.
Right.
Okay, so let's see. This sigma is actually equal to the square root of the variance here, and for binomial, the variance is equal to n times p times 1 minus p. So here this becomes.
Oh shit! It might actually be 0.5.
Oh shit! Get it.
Let's see, and we want to have
The
95%
widest.
confidence. So that is exactly when we calculated a constant. Fuck you. then we multiply both sides by. Let's see. Oh, wait, actually, so we want to know what the
I love how
highest
you're just not
number is,
even
right? We
compiling the
want the W
logic
to be the
anymore.
highest. This 2, irrelevant. The square root
And
of
don't
n,
forget the square root
irrelevant.
of the variance. You currently have variance, you have to do square root of np1 minus p.
Okay, cool. I take the square root. Now I square both sides.
Yeah, you can do that too.
Against
so
absolute value.
This n also irrelevant. So basically, the W depends on. I'm not saying equal. I'm saying depends on. I'm not
Yeah,
using the right
I
sign
just
here.
read
Whatever.
like proportional.
I think this is right.
So 0.5
So basically, we
is
want
the
this
right
thing to be
answer.
as high as possible.
Ah.
So we have 0.5. This will be 1/4. When we have 0.1, this will be 1 times. Actually, let's just write out the case. So we have 1 over 4. We have 3 over 10 times 7 over 10, which is 21 over 10, or over
You just take
100, which, is arguably less than a fourth. And we have 9 over
It's
100.
25, 21, and 9.
Yeah, so basically we're
Well, it
asking,
is
is
0.5.
25 bigger than 21 and 9? Yes, it is.
Yes.
Bop.
Yes. So
Bop,
You're
okay.
wrong.
I'm so tired. Like you have no.
Yeah, I understand
Or
what
you
we're
could.
talking about, Drug.
It's also the maximal one.
Yeah,
If you
like
take
it doesn't
the
get higher than
derivative
that.
of p times 1 minus p, you
Yeah,
get p equals to a half. And if you set it equal to 0.
yeah. Suppose you're given the following inequality. Simplify the left-sided inequality in the following format. What is the... We just have to simplify shit?
Yeah.
Apparently.
Hey, you know what? Fuck it, I'll take the W. So then we get
Let's go.
153 over 401 squared minus 2p times 153 over 401 plus p squared minus 1960. Is that like opening bracket fraction closing bracket squared, or is it just top
Oh,
squared
I
over
think
bottom?
it's the top squared, because if you look at the line, it goes below the 2.
Okay, so then we have this, and then we have times p times 1 minus p. Let's see if this is approximately correct.
I think it. No.
It is correct so far.
Oh wait, right, yeah.
Okay, then
Yeah,
I'm going
that's
to
good, that's
multiply out this one, so this is actually going to be equal to
Minus,
minus opening bracket this thing times 1 minus this thing times p. And again, because there's already p here, this becomes p squared. This minus and minus cancel each other out, so this becomes a plus.
Right. What the fuck is this kind of question? This is algebra or like
know.
calculus.
Literally.
I don't mind.
Why do you p squared thing p?
Yep. So
Oh yeah, that's what I think of.
so then we can move everything with a p up front, so that becomes p squared times 1 plus this fraction plus p times this fraction. I fucked that up. It's minus this fraction minus 2 times this fraction. And then we have plus this thing. And just to check for myself, did I include everything? So we have this term, we have this term, we have this term, we have this term, and we have that term. Yes. Okay, now the value of b is totally dependent on whether or not this number is actually the top squared or everything squared, and I hope it's correct. So then we take this number, plug it in, plop, check my answer.
Swap the signs. It can't be negative, I think.
What?
Oh, never mind. It can be negative. I'm not sure what you got wrong then.
Maybe then it's the whole thing squared instead of just the top squared.
Oh,
I mean, you didn't actually write B. You didn't actually write P. Oh, what's the value of B? Never mind.
So then it
Then
should
you
be
just
just
want to
one.
be.
What the fuck? You know what? Fuck
They
them.
wanted it at a
Fuck
decimal.
Fuck it. Fuck them.
Yeah.
And we still got agreed.
It's just simplifying. and
How
then
many
we
more do we have to
fail.
do for this lecture?
Challenging.
One.
This one and this one. So 2.
I mean, honestly, if we want to push to the end, like, how much is there left anyway?
Like there's like what? 6 here, 3 here, 3 here, 1 here. However,
Yeah,
like I
I'm
think
not
it'll be almost 6 o'clock by the time we've done this one.
Yeah.
I think we're just gonna have like a 1 or 2 hour
everything
session tomorrow.
Yeah. Maybe also have time to check out a past paper or something.
Yeah, exactly.
Yeah, okay, fair enough. Let's just finish this
Yeah,
lecture.
we'll
and
finish
call it
this one,
a day.
then I'm probably going to make dinner, but we'll see. What is the proportion of success found in your experiment? Okay, well that's just okay. So let's start out by saying that we have the mu plus or minus the p of z times the fraction of sigma over square root of n. This is a confidence interval, right? So I'm not going to bother remembering any of the binomial specific shit. That can go fuck itself.
Exactly.
So what we can do now is this sigma, right? This is actually the square root of n times p times 1 minus p. However, as you can see, I've actually pulled a sneaky on you. Because if we once this shit compiles, you can see that it's actually this can be broken apart like this. I swear to God, I changed one thing. And we can actually stripe away the square root of n. So this is not dependent on the amount of samples you have at all. Ha ha ha! So then you see that it's actually only this. I said q minus b. It should be 1 minus b. My bad. The mu, the expectation of a Bernoulli of a binomial is actually equal to n times p. So we have n times p plus or minus the square root of the chance of z times the square times or plus or minus the chance of z, the critical value. Let's say like that. Times the square root of that thing.
And because we give the confidence interval, we can't find the thing.
Yeah, we are given a confidence interval. We can scroll down. Also, it is okay. Also, I fucked this one up. This is not p times z. I'm gonna change this back to mu.
Z, yeah.
Yeah, this is something else, but I'll come back to that in a bit. The p of z, when we have a two-sided 98% confidence interval, is actually 0.01, so that is 2.326. Actually equal to 2.326. And this mu actually is not equal to n times z. It's actually equal to p divided by. Wait. Let me see here, because. Yeah, here. This p is x divided by n. Actually, does this help us? A realization x.
No, because
I wanted to say something. So like in a confidence interval, we know that these two values are symmetrically around.
Yeah. That's 400 IQ, my man.
So if we take the average between the two of them, you're going to get the value that's right in the middle, which is going to be the proportion that we had.
My man's got IQ.
765. Ooh, nice.
Ooh.
Oh, and not only that, but like, let's see. So we know that this is actually to the confidence interval. Oh, and this mu can go away now. But looking at this thing, the difference between this and the right side here, so I can say that 0.9 minus this thing is equal to the right side here. Therefore, I can say that this thing divided by 2.326 is equal to the square root of this. Therefore, I can square both sides.
Can you recompile it real quick?
Yeah, sure.
Oh, okay, perfect.
It's automatically recompiling, but sometimes I need to just click because I'm typing so fast and so much. Alright. Then we can say, okay, this is actually p minus p squared. Does that help us at all? Yes, it does. So then I can add p here, p squared here. Then I can subtract p, add this one. This will be equal to 0. And look, it's a quadratic formula that I really don't feel like doing. So I'm going to take this, fill it in here.
Wolfram Alpha.
I was an alpha. The chance is 1? No, okay, the chance is 99. Somehow I kind of doubt that.
Yeah. So just to be certain here, when they're asking for the proportion of success, are they asking which proportion we measured?
I'm not sure. If that would be the case, then it might be the middle value. But
Exactly. Yeah. That's what
Just
I
give
meant.
the middle value.
Yeah, I might be way overcomplicating things.
Yeah, I feel like you're taking them. Yeah. I feel like that's what's happening.
But like, what is this p then? Is that like the actual value?
No,
Yeah,
the
that
p.
is 0.765.
Yeah.
Wait, what?
The p is 0.765. 0.765 is the
p
value
in the root,
that you
not the p
measured.
hat. Not p hat, I think.
Yeah, like this is p
Actually,
hat.
what you're writing as p is actually supposed to be p hat. Because p is unknown.
That makes a lot more sense, thank you. Suppose you have an experiment where you look at the probability of throwing 6 with a special die. You throw the die 330 times, throw a 6, total of 106 times. Use this. What is the lower limit of your confidence interval for the probability of throwing 6? So let's see. We have the realization divided by the total time. And we have the lower limit that's minus 2.580 times the square root of the square root of the variance over the square root of the what's it called?
Number of times you threw the dice.
Yep, thank you. That's 330.
Sample size.
And the square root of the variance is actually equal to square root of 330 times p times 1 minus p, but p times 1 minus p is actually equal to.
Wait, where are you getting that? Where are you getting the second square?
No, that's not what p1 minus p is.
Is it not? Because I thought.
You don't know p. You have to solve the inequality of. You have to solve that inequality. Look at the slides again. I forgot what it exactly is, but there's like an inequality you have to solve for p before you know what p is.
Look, you have to just put in square root of p times 1 minus p, which you already have. Like p as in the approximate, the relative frequency.
Yeah, so that's what I had. So then I had this.
No, but you're multiplying it by the square root of 330. For what reason?
Look at the formula again. It's not n. It's not there. It's like.
Wait, why is there no variance here then?
It's like, I think there's some weird stuff going on in there, but I'm not sure. Oh, because it's
Oh.
I don't know.
Yeah, no, they did like they did the thing that we did at somewhere at the start, where it's basically just they rewrote x to be like this, and then they converted it to this, which is not the same as just using the formula that they have, which is kind of annoying because it's like almost the same. The only difference here, I guess, is that now I'm curious where they got their thing from then, though, because let's see, our formula was. Let me see if I can do a p-hat, by the way.
I think they got it from a Bernoulli distribution. Because that would be the variance of a Bernoulli distribution. Because if you're asking for the proportion, you're not trying to estimate the expectation or anything. You're trying to find what the percentage is, what the proportion is, what the p is, which happens to be the expectation when you're talking about a Bernoulli distribution.
Yes.
And for that one,
yes, thank you.
The
There we go.
is p times 1 minus p.
Oh, there we go. There we go. So instead of this top 330, it's actually just the square root of
that times 1 minus that.
Times 1 minus that. Okay, so it makes sense because you're like, yes, you're working with a bunch of probabilities, but all of them are just a single. I mean, it's not quite Bernoulli.
Yeah,
wait, it's
yes,
you know,
it
you
is.
either throw a 6 or you don't, so that makes sense.
Like, this is probably a d3 plus 3 dice. D3 with 5 and 6 on the sides.
But yeah, no, that makes sense. So I either throw a 6 or you don't, and in that case, then it is exactly a Bernoulli distribution.
You could actually make a D3 with a D3
so it's like relative
with organic
frequency
shapes.
minus thing times square root of relative frequency times 1 minus relative frequency divided by total of divided by the square root of n.
Yeah.
Sorry, can you repeat
What should be
that?
wrong? Okay.
What did you say, Conrad?
You could theoretically make a D3 that is fair out of organic shapes, like
I mean,
non-Euclidean shapes. Yeah. D1 is the difficult one.
Yeah.
Actually,
I mean, D1 is a ball.
That's just the Mobius.
Yeah, just make it a ball.
I know it's a Mobius strip, but like, it's still fun to think about.
Okay, suppose we have a random
D0.
variable x with a binomial distribution using a set of 65 observations. Proportion p is estimated to be p hat. Use central limit theorem to construct a interval. What's the upper limit of the confidence interval? 0.67 plus. We use central limit theorem, so that's like the infinite thing. And we have 9.5. It's the upper limit, so that's actually 0.025. So that's this one. 1960.
We should know it at this point, honestly.
Yeah.
The only annoying thing. Oh wait, never mind. We do. So then we have the square root of 0.96 times 0.33 over square root of 56. 65. Shit.
You alright now?
Yep. There we go.
Cool.
Back to lessons, and now we only have the last one left.
Oh, that's
because
true,
this
yeah.
one is a dupe, so we're doing this one.
Why is the other one a dupe?
Because there's like one.
Because there's another university showing the same Grasple set.
Yeah, because here it says TU Delft and here it doesn't, and here it says CLT and here it doesn't. So I
There's
think.
another university
Isn't CLT
sharing
just
this
central limit
Grasple
theorem?
set.
Ooh. That might be it. I'll check. So this one we already did. Which one will lead to the narrowest? This one we already. I misunderstood then.
0.1.
Not widest, narrowest.
Largest.
Yeah.
A confidence interval for the probability of success is this.
It's literally the same thing.
Yeah.
It's the same thing,
It's
just
the same
one
thing,
question
just
different.
worded differently.
Yeah. Challenging question. Continue practicing. Suppose you run for the school presidential election. You want to know what the probability of winning is. Your friends say that 80 supporters and sample of 200 students. construct a lower bound for the corresponding blah 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 3 decimals blah blah blah. So our relative
You even
frequency is
shit
this.
about decimals anymore.
Yeah, no.
I
You
feel
3
you're
decimals.
in a hurry.
Fuck you. So we do this, and then we do minus, because it's lower bound. Then we have, let's see, 95. We have infinite students when you ask the PFZ or ZLP.
Actually, we have 200, but yes.
No, we have infinite. So it's a two-sided
200
interval.
is basically infinity.
Yeah,
More
exactly.
than 50 is infinite. Come on, guys.
Yeah, more than 50 is infinity.
Start understanding.
Like, come on. Count with me. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, blah, 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 blah. 50, infinity. There's also no number between 30, 40, and 50. That also doesn't exist.
Yeah.
So,
It's the PSYOP created by the CIA.
Yeah, actually, what are we supposed to do if we get like 35 or something?
We won't.
You won't.
Pray.
Pray.
They
Cry.
could give us 31.
Let's see. So 95%, that's 0.25, so that's 1.960. 1.960.
They like that
times
95% confidence
fraction
interval.
of
I know that one by heart because they
square
use
root
it so
of
much.
80 over 200. C
Also,
dot,
it's so close to
20 over
perfection.
200 over the square root of 200. Wow. I thought it would be hard and stuff, but not really. What's the width of that confidence interval? It's let's see. Does it say it's no? It's two-sided. So it's 2 times P of Z times.
Careful. It's 43 people that indicate that they do not love it. So it's the negative here, and you're looking for the probability of loving.
Yeah,
Good
but
call.
when you do the width, you don't care about the first P, and the second one is P times 1 minus P, so it doesn't matter.
No, because I was looking at
Yeah,
the
but
calculation to
even
actually look
then,
at the question.
it's a good thing to say. Thank you. So we have square root of 43 over 250 times C dot 43 over 250, or 1 minus. So that is 207 over 250 divided by the square root of 250. And PZ is, we have a lot of people. So 90%, two-sided, 5%, 1645. So that is 2 times 1645. Oh. Times 1.645 times this thing. Enter.
Wow, that was really hard, guys.
Nice.
Yeah, wow.
Wow.
Back to lessons.
So, no.
I'm surprised we were already finished.
Something about stopping the time.
Yeah, I was about to say, so realistically, that's it for lecture 14. We only have
This was
lecture,
way
or
faster than the
lecture.
first half.
I didn't wait.
To validate the split. Yeah.
Yeah. Okay, so we have these left, these three, and this one. So let's see. Tomorrow we are going to start at let's say 12 o'clock. It might be a little bit later because I have to get my corona jab, and maybe it takes a little longer. But hopefully it should be like a 5-minute in and out adventure.
I so absolutely love the fact that all Dutch people call it a jab.
I mean, all British people call it a jab too.
Really?
Isn't that just the entire world that calls it a jab? Except for those few outliers?
Jab is way faster than calling it an injection or vaccination.
Yeah.
I've always heard it called a shot.
People
okay, sure, I can also.
When we speak different languages. So like if you're speaking English, sure, but like it's nice that they're gonna inject to you corona.
Yeah. Anyway, I'm going to stop the recording now because I need to upload it for people that need to watch it by tonight. So first for the recording, thank you everybody. Next part will be online tomorrow in a bit. Not if you're from the future, then it was online at the 23rd. And yeah, good luck.